happy to have you among us, sir, and we thank you for organizing this session. This session is chaired by Professor Anna K. Panaroska, who is also a professor in the Department of Mathematics and Statistics at the University of Nevada, Reno. Her works are in the areas of mathematical statistics and probability theory and its applications. Her applied interests are in the areas of finance, ecology, environment, hydrology, and climate, and she has co-authored over 50 research papers in theoretical and applied journals. We are extremely grateful to you for chairing this session, Professor Panaroska, and I welcome you to chair the session and I request you to introduce the speakers. Thank you. Professor?
Anna,
Professor, please.
Okay, I forgot my, so sorry. So thank you very much, Dr. Nair, for a very kind introduction, and my thanks also go to all of the organizers of the conference and the session. And without further ado, I'm going to start the session. Our first speaker is Mr. Amos Natido, and Mr. Natido is going to talk about uniform Laplace mixture distributions. So, Mr. Natido, please take it on.
All right, thank you, Dr. Panoska, for the kind introduction. I'll start sharing my screen, and then I'll take it from here.
You need to press on this button with an arrow. Okay.
I think it's coming.
Oh, right.
Okay.
Oh, it is fine. Yeah, you can continue.
Okay, so am I good to go?
Yes, absolutely. Thank you very much, Amos.
Okay. So one second, before I start, my name is Amos Natido, and my presentation is on uniform Laplace mixture distributions. So this talk project is a joint one with my advisor, Dr. Thomas Kozibowski, and I want to thank him for him assisting me throughout the entire project. And also I want to thank the entire organizers of this important conference, and I'm honored to be a participant. So the outline of my presentation will take the structure as follows. I'll start with the introduction, the methodology, the parameter estimation. I'll discuss some results, and then the conclusion. So the goal of my talk is to develop a probabilistic distribution model that models symmetric data that exhibits long and heavy tails and has a lot of outliers and it are not accounted for by any of the standard distributions like the Laplace distribution or the Gaussian distribution. So as a motivation, I'll use the data example displayed on the screen. It is a 1 year span daily change in solar power output by a solar plant in Nevada that records the megawatt power output at 9 a.m. So as we can see, the histogram plot here shows that this distribution is symmetric. It has a sharp peak, a high peak, and it has some outlying observations, and then heavy tail. So in an attempt to fit such a data with any of the standard distributions, like the Laplace or the normal, that didn't go so well. These distributions tend to have problem modeling the entire features of the data. So they have trouble capturing special features of this data. So because of the previous issue that I just discussed, we proposed a new model called the uniform Laplace mixture model. And then the reason being that the choice of Laplace is basically because it may be a good choice to model the high peak of the data, and then the uniform component, and then the uniform of the model component of the model is to help us capture the outlying observation, or what we call the outliers. So equation 1 defines what the uniform Laplace mixture distribution is, which is a linear converse combination of two component distributions which are actually univariate. The first component is a uniform distribution, and the second component is a Laplace distribution. So the uniform distribution has a proportion of P, and then the Laplace distribution has a proportion of 1 minus P in the mixture distribution. An important statement we need to note here is that anytime you take the absolute value of the uniform Laplace distribution, we end up getting another mixture distribution. And this mixture distribution is a mixture of uniform distribution supported on the positive side of the real numbers, and then the exponential distribution. We would denote the uniform exponential distribution as UEM, while the Laplace distribution as ULM. So on this slide shows some simulations or random samples from the two distributions. The top row is the uniform Laplace distribution, and then the bottom row is the uniform exponential mixture distribution. So when we take the absolute value of these, the observations on the top row, we will end up getting the distribution which is at the bottom row here. So these are some basic properties or characteristics of the uniform exponential mixture distribution. Yeah. So I'm talking about two different distributions, but I'll proceed with the uniform exponential mixture first for some reason. So here, these properties are for the uniform exponential mixture, which are not so difficult to derive. So in this slide, I would like to mention what we call the stochastic representation of the mixture model. Okay, so I define the mixture model in terms of PDFs, but it is also worth knowing that we can represent a mixture model in terms of random variables. So over here, equation 3, we have X, which is a uniform Laplace mixture has a uniform Laplace mixture distribution, and that is a mixture of two random variables, X1, which is the uniform component, and then X2, which is the Laplace component. And for equation 4, we can indirectly derive the uniform Laplace mixture, the uniform random variable X1 by symmetrizing a uniform which is supported on 0A. So in that case, when we symmetrize a uniform supported on 0A, we will end up getting a uniform that ranges from -A to A. And for X2, when we symmetrize an exponential distribution by multiplying by this indicator, we will end up getting a Laplace distribution, a Laplace random variable. So that's proposition 1. And then for proposition 2, here this one says that if we have a random variable y that has a uniform exponential mixture, and we symmetrize this mixture, we will end up getting the same X, which has a uniform Laplace mixture. Sorry. So these two propositions are very important in the sense that we can derive uniform Laplace mixture either by first symmetrizing a mixture, or first by symmetrizing a mixture model, okay, or we can derive X by first mixing a symmetrized distribution. And here the distribution is the component distribution. So we first symmetrize the component distribution and then you mix them, or we first mix and then we symmetrize. So the next slide talks about that. So the operations of mixing and symmetrization is a general phenomenon, and they commute. So the order of operation does not really matter. So this proposition talks about what I just explained in the previous slides. So the left-hand side of equation 8 talks about a mixture of symmetric versions of the random variables x1 and x2. And then the right-hand side talks about symmetric version of the mixture of x1 and x2. So I'll proceed with the parameter estimation of the uniform Laplace mixture. Yeah. So to do that, I'll first, what we did was to first convert a sample from the uniform exponential mixture, from the uniform Laplace mixture to a uniform exponential mixture by taking the absolute values of the observations from the ULN. And then the strategy we use is the EM algorithm. So let's say we have y1 through yn that has a uniform exponential mixture, and then we have z1 to zn, which are some latent variable that determines which of the components the y1 through to yn comes from. So if zi is 0, then yi comes from the exponential component, and if zi is 1, then the observation comes from the uniform component. So this equation 9 represents the full, the PDF of the full data, which is the bivariate pairs of the actual observed data and then the unobserved data Z. So this slide talks about the general framework of how the EM algorithm works with respect to the uniform exponential mixture. So the strategy is that you first write down the complete data likelihood, and then the goal is to maximize that and using the EM algorithm. So we first choose the starting value theta naught, and then we generate sequence of estimates theta r that will converge to the true parameter theta in 2 steps. We have the E step and then the M step. So for the E step, we take the expectations of the complete log likelihood with respect to the conditional distribution of Z given Y. And then for the M step, we maximize the resulting function that we obtain in the E step with respect to the parameter to obtain an updated parameter theta at the next iteration r plus 1. So we repeat this until our current estimate stabilizes. So equation 10 depicts or represents the log likelihood, the complete data likelihood of the uniform exponential mixture model. So we want to maximize this. We want to first find the expectation of this log likelihood with respect to the parameter, with respect to the expectation of Z, expectation of Z given Y. And the expectation of Z given Y is given by this equation 11. And so given this, we will replace these zi's with CIR. And with that, we will maximize equation 10 with respect to the various parameters in this equation. So in doing that, we need to take notice of some points. So the first one is that if the initial guess for the parameter A falls within any two order statistics, then the MLE for the parameter A is always equal to the observation to the left of the initial parameter, that's YK. And this is true for all iterations. So what happens is that, so whenever our current observation is YK, then the MLE in the next iteration also results in YK. So in view of that, the MLE of A does not update. It gets stuck between two other statistics. Whilst the other parameters, P and sigma, continue to update. So that is an issue. And in effect, the algorithm maximizes the log likelihood over some subspaces of the actual subspace of the actual parameter space. And we call this subspace DK, which is defined as this. Then also, if we consider these other statistics and this initial value of A happens to fall between 0 and Y1, then we only have the exponential component. And in that case, the proportion of the uniform component is 0, and then the estimate of our sigma becomes easy, which is just the average of our observations. So because of the above issues, we adopt these strategies. We first break the parameter space into n+1 subspace, and then for each subspace, we run the algorithm with the initial value as A0 of A to be A0, such that A0 is between two other statistics. To obtain our MLEs A, K, A sub A hat K, sigma hat K, and P hat K. And where the estimate for A hat K is always YK. And so once we obtain the MLEs in each subspace, we evaluate the log likelihood at these MLEs using equation 12. And this is only true for parameter spaces from 1 to the second parameter space to the last one. But for the first parameter space, that is a special case. In that case, the estimated log likelihood is derived by equation 13. So now we will compare all the estimates of the log likelihood and then select the largest of these likelihood to be, we select that as L sub M. So we then select the parameters that corresponds to this log likelihood, the maximum of all the log likelihood, as our unique MLE for the parameters in the uniform Laplace mixture. So this proposition talks about the estimate for our parameters. Okay, so when we have a random sample from UEM and then we run EM algorithm for each subspace, starting with the current values, the updated values in the EM algorithm is always given by these equations. So we look at how the model performs through simulations and then data example. So for illustrative example, we perform we use the parameters A to be 2, P to be 0.3, and sigma to be 0.2. And we perform simulations from these distributions. And then we run our model. You run the EM algorithm on the simulations to estimate these parameters. And as we can see, the estimate tend to converge to the true parameter as n increases in size. And these are some trace plots or the EM iteration plot for various initializations of our parameters. So for the top row, we have when we start with P is supported on 0.1. So let's say we start with 0.1. The algorithm tends to converge to the true parameter 0.3. Then the sigma was initialized by taking the average of the samples, and that also converges to the true parameter. Yeah, so the same applies to when we use P to be 0.9. So in this example, so for on this slide, I'll talk about how the model performs on the real data example, which has 365 observations of daily solar power output. And when we take the daily change of this, we will end up getting 364 observations. So now we run the EM algorithm on this actual data. And as we can see, this tries to mimic how the algorithm works. So the first row represent the parameter estimate in the first subspace. And then we have the last one row represent the parameter estimate in the last subspace. So we'll compare the log likelihood estimate here. We pick the maximum one, and then we choose the parameters that correspond to this as our estimate. So with this estimate, we try to assess how the model perform or fit the data. And as we can see, the density estimate shows that the uniform Laplace mixture tends to model the data very well compared to the standard Laplace and then the Gaussian distribution. Then the QQ plot also shows that the model performs well. Yeah. So in effect, the uniform Laplace mixture is more flexible to capture the various features in this particular data. Thank you. And then these are some references. So thank you for your audience.
Anna, your microphone is off.
Thank you, Professor Balakrishna. I seem to forget it all the time. I apologize. So thank you, Amos, for a very interesting talk. Good job. And let me ask if anybody has questions.
Can I ask a question, Amos?
Of course.
Yes, please.
Can you go to your proposition 1?
Okay. Okay.
Where yes. If I am not mistaken, you have to implicitly assume that your parameter A is outside the range of your sample. You cannot have A inside the sample like you have done in your estimation method. I will tell you why. If you have A in the interior of your sample, then you cannot have this mixture representation. So can you go to the previous page? Okay. The previous one, where you introduce the mixture model. The previous page. Yes, let us stop here.
Okay.
What I mean is, let us say you have a sample, okay?
Okay.
Suppose it goes from -5 to +5. That is the range of your sample. So the minimum is above -5 and the maximum is below 5. Let us take it to be -5 and 5. The problem is, in this construction, if I take A to be equal to 3. So your uniform random variable goes from -3 to +3.
Yes.
So suppose you tell me you have a realization of 4. Then the probability that that realization comes from exponential is 1. It is not 1 minus p.
Correct.
Your original mixture model will remain with probability p and 1 minus p only if the range of the two distributions are merging in some sense. Suppose uniform goes from -3 to +3, the data goes from -5 to +5. Outside the interval -3 to +3, I don't need any EM algorithm. I can say with probability 1, they are coming from exponential. So in your EM implementation, one of the reasons you ran into problem when you looked at K in the interior of the sample is because of this phenomena. So if I look at A as -2, that particular observation could come from uniform or could come from exponential. You could give probability P and 1 minus P. Once you go outside the range of -A to +A, the P doesn't exist. 1 minus P should change to 1. So the EM updating will change automatically. You see what I mean?
Yes.
So the mixture that you went actually will be modified depending on the range. So what I would do, actually, if you go, can you go to your simulation result? Because that is a very clear example in the end. Why your method, your simulation worked here. Let us focus on this simulation. What do you have here? A is 2. Correct?
Yes.
So your uniform component goes from -2 to +2. Your
Yes.
Laplace random variable is with sigma equal to 0.2. Sigma equal to 0.2 compares to A, it is 10 times sigma. So the entire Laplace sample that you would have generated will be sitting inside the uniform interval. So you have no problem. In this particular case, you have no problem. But I bet you, $1. I am not rich, so I can only give $1. I bet you change your sigma to 20 and run the simulation. Your simulation will crash because in this particular case, the EM cannot work. Because if sigma is 10, it will be outside the range of -2 to +2. So you need to change your EM depending on the range you are in. If A is in the interior of the sample and A is in the exterior of the sample. You follow what I mean?
Yes, I'm following.
Yeah.
Thank you, Professor Balakrishnan. And I think we will need to settle that bet.
Well, it's $1 Canadian, not even an American dollar.
Okay.
So it's not even worth settling the bet. No, but I
Well-
think you can modify your code very easily. I see how the EM updating is done. So what you do is you divide the data into in the interior of uniform and the exterior of the sample. Exterior of the sample, P will become 0. 1 minus P will become 1. In the interior of the sample, you will keep P and 1 minus P. It's the same updating, except with a small change.
Yeah,
So-
one comment.
Amos, okay. So
Yes, Tomat, please.
Yeah, just
No.
make well, basically when you run the algorithm, you don't assume that you know anything. So you don't know what this A actually is. And you can't say, I guess, when you compare your data with A, you don't know your A, right? I mean, you can assume A, but you never know what it really is.
That's a correct point. But whatever it is, in the numerical procedure, you evaluate the likelihood at a specific value of A, right? Estimate of A.
Well, A is one of the values that participate in the EM algorithm.
Correct. But if that A is in the interior, the way the likelihood is calculated is not correct. That's what I mean. If A is in the interior of the sample, P will interpretation of P will change, I think.
We'll have to evaluate this. So Amos, you will send Professor Balakrishnan your comments and your simulations.
He is going to prove me I am wrong. I owe him $1.
We'll
But
see.
I have a very easy way to challenge this is to do the same simulation, but change sigma to 2. You will notice that the problem arises in your implementation.
So Amos, you double check it, please.
Yeah.
Thank you for your comments.
Yeah.
So I would say, Amos, you need to run the simulation just as Professor Balakrishnan says and settle
The bet.
the bet. Okay. On
Okay.
your side, I would assume an American dollar.
Okay.
Yeah.
Thank you. Now, Professor
But it is
Kumar,
Amos, but it is easily fixable. If you face a problem in the EM, just like you indicated before, it's easy to fix by dividing the range. I think I can see how the EM could work in this case.
Okay. Yeah. Thank you for the great insights. And,
Nice. Enjoy.
yeah. And
thank you.
okay, sorry.
Next question, I think, is coming from Professor Manoj Kumar. Has a raised hand. Would you like to ask a question, Dr. Kumar?
He is muted. Manoj, you unmute yourself and
Yeah.
ask the question.
Yes.
Please.
Okay, sir. Really, Bala sir, your question is very nice question, sir. Really, I am very thankful to Bala sir and presenter Professor Amos sir. And there is, sir, one of the for concept point of view, sir, you have. There is some special assumptions to use for EM algorithm. There is some special assumptions required. Is there?
Please can you come again?
Can you hear me?
Hello. Yes, I think it is better now.
Is there a special assumptions required for EM algorithm? And how to choose the initial guess to obtain the solution of these nonlinear equations?
Okay, yeah, thank you. So there are some assumptions for the for EM
yes.
algorithm, and
Is there
specifically
some
choosing
special assumptions required for EM? Yes.
so you mean with specifically to my model or in general? Hello?
Yes,
Please,
yes.
I want to understand your question. Okay. Yeah. So
Okay. Once again, so I repeat the question.
Okay.
Is there some assumptions required for EM algorithm to obtain the estimate or a solution of the normal equations of the unknown parameters?
okay, if I
Do you
understand
hear
you,
me?
yeah, I can hear you. I can hear you. Yeah. So you mean if there are some special assumptions that are required for this procedure to work, and then specifically with regards to the initialization. Yeah, so there's no any special assumption here, apart from the fact that you need to look at in choosing your initialization, you need to actually study the behavior of the log likelihood. Okay, and then there are various methods methods that are available for us to choose a correct initialization, and also check if our algorithm actually converges. Okay, but with this we didn't make any special assumption apart from the fact that when we studied the log likelihood function with respect to our parameters, it tends to the the log likelihood suggests that there is small change in the log likelihood per iteration. So we tend to just use the assumption that for the parameters to converge based on any initialization from within the parameter spaces, the difference between the log likelihood between successive values of the log likelihood should be small. Yeah, so that's basically what we considered in making sure that the algorithm works.
All right.
Okay. It's okay. Okay, Professor. Okay. Very much thank you. Okay.
I have a short question. Amos, is there some reason why this solar energy data is coming, sometimes from a uniform, sometimes from Laplace?
Yes, I can't provide specific reason now at this moment, but I think it is based on my readings and research in this area. Most observations from maybe renewable energy, being it solar or wind, tends to exhibit this shape, but such observation could best be explained by engineers in this field. But at this moment, I can't. Yeah.
All right, thank you, Amos. Any other questions for Amos? Well, then let's introduce the next speaker. Our next speaker is Mr. Henrik Bengtsson, and Henrik is going to talk about clipping, switching, and geometric divisibility. Thank you for coming, Henrik, and please take it away.
Thank you so much. Just to check, can everyone hear me?
Yes.
Then I will try to share my screen. Of course,
there
will always be technical difficulties, but hopefully you will.
Is it a Scandinavian name by any chance?
Yes, I'm actually based in Sweden. So I'm at Lund University with Krzysztof Pokowski, who is my supervisor. Can everyone see my screen?
Yes.
Perfect.
No, it disappeared.
My presentation. First of all, my name is Henrik Bengtsson. I'm working at Lund University. And please forgive me for being a bit tired, as in Lund, the clock is currently 06. It's 11 past 6 in the morning. So I was up at 4 a.m. this morning. So forgive me for being a tad tired, so to speak. But today I will be talking about clipping, switching, and geometric divisibility. And I should also mention that this is work in collaboration with Krzysztof Pokowski, who's my supervisor. And I would like to thank Tomas for both the invitation, but also the many helpful results and discussion comments. I should also mention my PhD thesis. So let's move out to the outline. I will talk about a bit about why clipping, switching, and geometric divisibility is important. I'll move on to some main results, and I will give an at the end, and hopefully draw some conclusions. I think your mic unmuted, perhaps.
I think everyone other than the speaker should mute their microphone. There is a lot of static noise.
Yes. Yeah, thank you, anyways. So let's talk a bit about exceedance time distributions. So essentially the time that the stochastic process moves above some line and then come back. And the reason for studying these types of distributions are many. There are many applications. In this talk, I will have a specific application in statistical physics. And there's also, perhaps the biggest use of exceedance time distribution is to amuse mathematicians and probabilists throughout the last decades. However, there's one problem with these 16 times distributions. Explicit representation of them is non-trivial. It's quite a hard problem, as we will see later. In statistical physics, the concept of persistency is of importance since it describes the tail behavior of this exceeding time distribution, which is important to know. So the talk is clipping, switching, and geometric divisibility. So let's talk about clipping. And hopefully you can survive my very, in my mind, beautiful hand-drawn figure here. And so say that you have a stochastic process. Here we have this set of t, and it squiggle a line along in time and space, or in time. And at some point it will cross some level. In this case, it's the 0 level. And let's just record these crossings. And then we take the sign of this process. So when the process is above 1, above this level, in this case 0, we take 1. And when it's below, we take -1. And then we obtain what we call the clipped stochastic process. It's kind of like clipping it with scissors. And one should always keep in mind that the properties of the original stochastic process we're clipping will be reflected in the clipped process. However, so we have talked a bit about clipping, so let's move on to the first type of switching. So I would like to talk a bit about the stationary switch process. So suppose you have a stochastic process. It takes values 1, -1. And the length of time we are in 1 or -1 are IID. You can construct this as a stationary process. It will be stationary. And therefore, the defining feature of this will be the covariance of this. And there exists a relation between the distribution of these intervals and the covariance. And this is quite used in the so-called independent interval approximation framework. For overview, you can see this paper published in 2013. And as this is essentially a method to approximate persistence, this tail behavior of the exceeding times distribution. However, if you just take a clip process, it's quite hard. So we use, in statistical physics, they do not assume independence, but they use independence to do this approximation. And here you can say that you have the covariance of the clip process, and here I should emphasize that A of t is the covariance of the process we're clipping. So you have a relation between the stationary switch process, SSP, and the distribution of t. So the main idea is essentially that you clip a stochastic process you're interested in, and you substitute this expression with the covariance expression in the stationary switch process, and then you use that to draw conclusions about t. However, is this a good approximation? Well, yes and no. For persistency, it produced some actually decent approximations. So Sire in 2007 obtained a persistency for the 0 level diffusion into dimension case. And he obtained it through IIA numerically to be 0.1862. And this is quite good. It's quite good. And in 2018, the true theoretical value were derived for this persistency to be 0.1875. So it's very close, but this paper published in 2018, it is quite a technical paper, and it only considers diffusion in 2 dimensions and for the 0 level crossing. So, and this is one of the few known persistency coefficients that are actually solved from a theoretical point of view. We kind of emphasize how hard and the need for approximation methods in this case. However, since I will just assume that all of you here are statisticians that have at least taken some elementary probability theory course, think back when you were first introduced to the fundamental properties of a cumulative distribution function, a CDF. And then I want you to consider the following approximated CDF using IIA for diffusion dimension 2. And you have kind of several problems here. The first is that the CDF dips below 0, which is, well, it's not good, to say the least. So it dips below 0, and I should also add that this figure is obtained by doing a series expansion of the covariance in the Laplace domain, and then do numerical inversion. And the dotted blue line at the bottom here is the first order series expansion. So one might think that, okay, but when we take more and more terms, it will become better. And yes and no, because if you take a sufficient amount, you come into the problem of getting decreasing CDF. And I'm not really sure that that is in the properties of the possible properties of a cumulative distribution function. And it has also been shown that for at least Gaussian processes, this approach will not produce proper distributions, which is important to keep in mind. So we need to consider a different approximation method here. And with that, I want to move on to the second switching, the switch process, which is closely related to the alternating renewal process for those of you who know. It starts from 1 at 0, and then you are in the state of 1 for some time, some random time. Then you switch, hence the name, to -1. You're in some time in -1, then you switch back. And since we start from 1, this will of course not be stationary, but perhaps we can use the expected value of this process instead to do some nice conclusions. And there is also a relation here between the distribution of the intervals and the expected value. So perhaps a good approach would pair this process with the Slepian process, which essentially describes the crossing behavior. When a stochastic process cross some level, it describes the crossing behavior. And here you have a form. U is the level. So for the case we're interested in, 0. R is the big R is a Rayleigh random variable, and R is the covariance of process we are investigating, so we can delta this Gaussian process. So if in the IA framework you took a stochastic process, you clip it, you compute covariance, and then match it to stationary switch process, we can perhaps do something similar here. We take the Slepian model, clip it, we take sine of it, and we match that expected value to the switch process and see if we can draw some conclusions there. But however, we always need to ask ourselves, will this have the same problem? And to investigate it, we perhaps need to be a bit more formal than we have been up to this point. So let's move on to the main results. So here we have a more formal definition. So we have a counter-renewal process, sequence of TK, IID, non-negative random variables. And here I should emphasize that you have no atom at 0. So you can have no positive probability at 0. And then you have this counter-renewal process, which is essentially just the number of events up to time point t. And as you can see here in the definition, x of t is -1 to this power. And for notation's sake, I will use e of t to denote the expected value of this process. And since we're matching expected value, it's of course interesting to look at the properties of this. So let's do that. Of course, it will be between -1 and 1. At infinity, the effect of starting at 1 will kind of diminish. So on average, at infinity, we'll be going to 0. And of course, since we're kind of starting at 1, the limit should intuitively, and you can show this, to be 1. And under some conditions, you have the derivative be well defined. Essentially, if you take the probability density function of the intervals, and you can find some number small n such that the repeated convolution n times of this is finite or bounded, then the derivative is well defined. However, one should consider what can we else add for characterizations to E, or perhaps the set of E to define this set of expected values. So perhaps, and most of the proofs for this is, or the natural domain to work with this is in the Laplace domain. And here you can see that Laplace transform of the expected value. And here phi of S is the Laplace transform of corresponding to distribution. So I think it actually might be a typo here, but please forgive me for that. So we have done clipping, we have done 2 times switching. So let's move in perhaps to some geometric divisibility. And let's start with geometrically infinite divisibility. It was introduced in the by Klebanov in 1983 and some others. And essentially, if you have a random variable and you can write its distribution as a sum of IID random variables, where the number of terms that you summate is geometric distribution. And this can be done for any p, for all p, between 0 and 1. And here I should also say that geometric distribution in terms of the geometric distribution starting from 1. So we will always have at least one term. If you can do this, we say that the distribution of y is geometrically infinite divisible. And this has been a well-studied object. I think Thomas has worked a bit on this. And if you're dividing something, I think it's kind of natural to talk about the divisor. So for notation's sake, let's f x tilde be the p geometric divisor of f, where f is the distribution of y. However, this needs to hold for each p between 0 and 1. So perhaps can we consider a similar concept, but not exactly that? So let's talk a bit about geometric divisibility. So if this property holds, at least for some p, not necessarily all p, we said that it's R geometrically divisible, and here R is p is equal to 1 over R. And I should also comment that on the notation here, it's essentially due to being a bit more natural in its interpretation of being the expected number of terms in the sum. So GD2 will have a p of half, so we expect to have 2 terms in this sum. It's a larger class than geometrically infinite divisible distributions. And you can also see that there are some expanding subset properties as well. So, but if to see if the distribution is geometrically divisible.
Henrik, should R be greater than 1? Yeah, right?
R should be, yes.
Okay.
Otherwise, P would be 1. So yeah, yes.
Thank you.
So let's consider a condition for geometric divisibility. So distribution f is geometrically divisible if and only if this expression is a completely monotone function. And that essentially means that it's a positive function. The even derivatives are positive and the odd derivatives are negative. And essentially this corresponds to Bernstein's theorem, saying that if the Laplace transform is a completely monotone function at and 1 at 0, it corresponds to the Laplace transform probability distribution. Of course, this can be hard to verify because you kind of need to compute every derivative. So this is more easily used to providing counterexamples. So you can construct a counterexample quite easily by taking summation of uniform, geometric summation of uniform numbers. So we have talked clipping, switching, geometric divisibility. So how are these connected? So now we have moved on to the main theorem of this presentation. So the switching time of the switch process, the switching time distribution, is geometrically divisible of degree 2 if and only if the expected value of the corresponding switch process is non-negative and decreasing for all t. And I should also mention that the proof is done by properties of the Laplace transform using limits and is, yeah, the proof is not straightforward, but it's kind of a nice proof. See the paper coming out hopefully soon for the full proof. However, this theorem is nice, but what are its implications? So let's talk a bit about what follows from this theorem. And as I said, the divisor, the distribution divisor, will have an explicit representation. It's 1 minus the expected value. And the very good thing of this is that the condition of the expected value to be positive, to be decreasing, those properties are kind of easily to verify for most functions. So if you can verify them, you have explicit representation of the divisor. This also gives the very nice implication that you can verify that the Slepian-based approach can be used and will give proper distributions. And if you recall from the approximated CDF of the independent interval approximation, which does not give a proper distribution. So, and also you have the set of functions that are positive and decreasing is quite large. So they will correspond to proper distribution if they're the expected value of a switch process. So perhaps we should consider some examples. And let's investigate diffusion in 2 dimensions, a classic problem. And also, as I said, it was theoretically solved in 2018. So using the Slepian framework, we can easily see that the expected value is, has the properties that we need from theorem 1. So we get an explicit representation of the distributional divisor. And you have to still numerically obtain persistency here, but we get a similar estimate to previously obtained approximations. The kind of hard thing is that you will still not have an explicit CDF, since the Laplace, you usually do this in the Laplace domain, and the Laplace transform of this expected value is not that neat to work with. But the very nice thing, the very, very nice thing is that you know that it will correspond to a proper cumulative distribution function with all the properties that we expect of it. So it's quite nice. So let's summarize. Geometric divisibility, which is quite an interesting concept, appears in the context of the switch process, which at first was kind of not expected. You can verify the Slepian approach and know that under some easily checked conditions, you obtain proper distributions, which is quite nice. And then the question is, what is to be done in the future? And perhaps the most interesting for those attending this session, I would say, is the full characterization of the set of geometrically divisible distributions. How can we characterize this in some nice way and derive the properties, essentially, of this? You can hopefully also extend this to see if there is a relation between the stationary switch process, the covariance for that process, and the geometric divisibility. And early findings indicate that it might be some nice connection there. Another thing you can do is to extend this result to asymmetric switching time. So i.e. that the time you spend in 1 is independent of the time you spend in -1, but it has a different distribution. So that's one thing you can investigate as well. And with that, I would like to also mention that I have some references here for those of you who want to check them. And with that, I would like to thank you all for listening. And I would like to thank Thomas for inviting me and organizing the conference. And thank you very much for listening.
Henrik, a quick question, if you don't mind. Hello, Henrik.
Yes?
Yes.
Henrik?
Professor Singha actually, I think, raised his hand first.
Sure.
Professor Singha, would you like to ask your question?
Do you mean me?
Yes.
Okay. I'm Satish. That Singha is.
No, it says
I'm Satish. Okay.
Uranga Singha.
Okay. So you said a subclass property for GDR.
Mm-hmm.
But this GDR is true only for a fixed R, right? You are defining GDR for a fixed R.
Could you please repeat the question?
You are defining the GDR class of distributions for a fixed R, right? The class of GDR distributions you are defining for a fixed R. Am I right?
Yes, it's a fixed R. Yes.
In that case, how can we have a subclass for that, for the same? Yes, less than R, it becomes a subclass. That I do not understand. One thing. And another point is, basically you are considering here a compound geometric distributions, right?
A compound geometric distribution?
Yes, and for verification, you are considering a kind of geometric inverse that is familiar in Cox and renewal processes. So basically, I think that that characterization, that phi divided by p plus 1 minus p into phi, that reduces to verifying whether the process, whether the distribution is a geometric inverse that we usually consider under Cox and renewal processes. I think so. I'm not sure because I do not have the reference right with me, but I think you please check that. Okay?
I would like to thank you for that comment. I'm just noting things out. Yes. If I remember correctly, it's the subclass property is derived from noting that the summation of geometric is geometric.
Yeah.
So it derives from that, and you can actually produce a counterexample, which is so you can construct an example which is divisible for 2, but it's not divisible for 3, 4, and 5.
Yeah. That part I didn't understand, and the other one was just a comment that what you are looking at is basically the interval distribution in Cox and renewal processes. Yeah. Okay. Thank you, Henrik,
for the very insightful comments.
Thank you. Perhaps the next question would be Professor Srinivas Ravi.
Thank you, Anna. Henrik, I just wanted to ask you if you have any intuition as to why the order is 2 in your theorem 1.
It's a really good question, and it was kind of surprising to find too, because I at this moment do not really have some intuition why it's 2, but it seems to be some sort of, I would not say criticality point, but it seems to be quite an important point for this class of distributions. So that is an open problem.
Okay. Thank you, Henrik. Thanks, Anna.
Explore it. So thank you for your question.
Thank you.
So maybe that has something to do with symmetry of this construction.
Yeah.
Probability half, when
I was going to comment that on the +1 and -1,
right,
you are giving identical distributions. So the probability of switch will be half-half.
That's probably something to do with that.
Something to do with that. So one way to check will be to change the distribution of F2, for example. And then probably the order will be different. It's a guess. We don't know whether it's correct or not.
I think you're onto something because this is part of a larger physics project I'm working on, and when we were investigating this non-symmetric case, you have very similar structures in the Laplace domain, but for different values than 1/2. So there is something there. It only needs to be formalized.
But Henrik, if you change it to -1 and 0, things will change? Instead of -1, 1, you change it to -1, 0.
I believe some properties will change, yes. But I'm not exactly sure, to be completely honest.
Okay, thank you.
But thank you for the comments.
Thank you.
Are there any other questions or comments? I guess not. So thank you, Henrik, for a very interesting and stimulating presentation. And I will now announce the last speaker of this session. And our last speaker for this session is Mr. Francesco Zuniga. Francesco is going to talk about a new trivariate model for stochastic episodes with a generalized linear model. So thank you, Francesco, for coming to the conference, and please take it away.
Thank you, Dr. Panosca, for...
Just 1 second, Francesco, 1 second. Satish, your microphone is on. Can you please turn it off? Mute yourself.
Thank you, Dr. Balakrishnan, for the point, and thanks, Dr. Panosca, for the nice presentation. So let me share my screen with you. Okay, can you see my screen?
No.
It's loading.
It's loading.
Yeah.
Okay.
Okay. It sounds good to me. Okay, perfect. Yep. So just a second. You see my screen, correct? I'm moving slides now. Perfect. So welcome everyone. My name is Francesco Zuniga. I'm a PhD student in statistics and data science at the Department of Mathematics and Statistics at UNR. And today I'm going to introduce you to my research field. So as Dr. Panosca introduced, we are going to talk about a new travariate model and a generalized linear model for extreme events. So some of the ideas that we work in the last 2 years of research. I really would like to thank the organizer of the Wsta 2021 International Conference and the organizer of the session Advances in Distribution Theory, the Department of Mathematics and Statistics at the University of Nevada, Reno for the support, my advisor, Dr. Panosca, and Dr. Kozobowski for the kind invitation to the conference. Now, let's start with a brief overview of my presentation. We will, in the first part, we will talk about the trivariate model and its characteristic and the motivation behind it. Then we will talk about this generalized stat-leg model and the new idea, where stat-leg means trivariate distribution with exponential, truncated logistic, and geometric margins. The interpretation of the Hurdle geometric model as waiting time, the properties of our generalized stat-leg model, and the parameter estimation. Then the testing and the illustrative data example. Then we will discuss about the main setup of this generalized linear model that we will call GLM for the stat-leg, the estimation and existent uniqueness of the MLE, the model validation, and the distributional assumption. I just would like to let you know that some of the topic may be familiar for some of you if you already attended Dr. Kozobowski talk on Monday. And the topic is similar because Dr. Kozobowski talked about the stat-leg model. This one is a more generic model, but similar concept. Now, let's talk about this generalized stat-leg model. Our research is focused on modeling extreme events in what is called peak over threshold scenario. So we observe, record, and measure a process value x1, x2 that happen above or below a certain threshold. The model describes the duration n, the magnitude x, and the peak value y of such event through the random structure x, y, n. And the duration n is modeled by a counting variable like a geometric or Poisson that is independent from the x-size. Application to this model can be thought as flood, drought, deluge, that are huge precipitation events, financial growth and or decline, insurance claim, and heat waves. So the Tetlec model, for the Tetlec model, we consider the xi with I greater than 1, greater than equal to 1, that are independent and identically distributed exponential random variables. N for us is going to be a geometric with parameter p independent from the xi, and the magnitude x is exponential with parameter np, and magnitude y is the truncated logistic. Now, the practical issue that we found when we were doing our research is that we observed that while looking at the heat waves data, we were observing too many ones for the geometric model. So providing a fit that could be considered not optimal. So the solution that we discussed is that to modify the geometric model in such a way to include this excess or lack of ones, as we can see in a minute. Now, the Ardel approach, in order to do that, in order to account for this excess or lack of one, we use a mixture model of geometric with a point mass at 1 and our regular geometric shifted, so starting from 2. While the geometric random variable NP follows a geometric distribution P with probability of success P, and you can see the PMF here, our Ardel geometric model that we refer as HGeo with parameter P and Q as the parameter P between 0 and 1 and Q between 0 and 1, and to be where Q is the desired probability of ones, and consider the geometric distribution starting from n greater than or equal to 2. It's important to note that depending on the relation between P and Q, we can have different scenarios. We have the Ardel geometric PQ model may be overinflated, so the number of may overinflate the number of ones if P is less than Q, or underinflate the number of ones if P is greater than Q. And in the case where we have P equal to Q, we have that the Ardel geometric PQ reduces to simple geometric with parameter P. Now, another important point is this interpretation. So the Ardel model is a mixture where the components are the point mass at 0 with probability Q, and the geometric random variable truncated below at 0 before mixing with probability 1 minus Q. So another important contribution to the Ardel area that was given by our definition of the Ardel geometric model as a waiting time for the first success in a sequence of independent Bernoulli trials, IJ. So consider an independent and identically distributed sequence of Bernoulli trials that is the probability of success that is Q on the first trial, and the probability of success changed to P from the second trial on. So then the number of trials till the first success will have the Ardel geometric distribution. Now I would like to discuss with you about this generalized Tetlec model. So given the original Tetlec model, we have developed theory for a new generalized Tetlec model where the duration is this Ardel geometric. In our model, we have a random vector x, y, n, where the xi are IID exponential random variables with a mean 1 over beta, and n is the Ardel geometric with parameter pq, independent to the xi. So it's safe to have this generalized Tetlec that we will call GT distribution, denoted by GT with parameter pq and beta. And we know that here, when P is equal to Q, our GT model, it reduces to the Tetlec model that also Dr. K was discussing in this presentation. Now, I would like to talk about some properties of this distribution. For our first paper, a new trivariate model for stochastic episodes, the following properties were established. So the marginal and conditional distribution, bivariate and univariate, needed for fitting the model to the data, the moments, the characteristic function, the covariance matrix, and the stochastic representation. This was pivotal in proving many of the properties for the GT model. Then we talk about estimation, and using the maximum likelihood estimation method, we calculated the estimators for the parameter of the GT model, P, Q, and beta, and we proved that the vector of MLE is consistent asymptotically normal with covariance sigma MLE, and as in equation 7 on the slide, and asymptotically efficient. That is, the asymptotic covariance matrix coincides with the inverse of the efficient information matrix. Then here we talk about the testing, and we test if it was a geometric or a hardware geometric. So for testing, for the main test, we check if the null hypothesis, the duration, comes from the regular geometric, as we said, or from this hardware geometric. That is, the null hypothesis is P equal Q, so it's from the Tetlag model. So computing the log likelihood ratio test, so the log of lambda, we calculated several cases. So therefore, we have calculated the limiting distribution of the likelihood ratio test statistic when the sample size increases. We studied if the limiting chi-square distribution with 1 degree of freedom is a reasonable approximation to the true distribution of the 2 log lambda. And we noticed that this depends on the speed of convergence of the true value of P. To check that, we perform a Monte Carlo study, and with the result reported in the table in this slide, and we simulated 10,000 samples of size K from a geometric distribution with parameter P and for varying P, and found that the smallest K for which the empirical distribution of 2 log lambda can be assumed to be chi-square distribution with 1 degree of freedom, we check using the Kolmogorov-Smirnov goodness of fit test. So finally, we conclude that for P that was between 0.1 and 0.9, the sample size needed for using this chi-square approximation is below 100. And when P is close to the limit, so to 0 or 1, the sample size K is growing at a big pace. Now, let me show you the data example that we use for this research. So we illustrate a potential application of this GT model using the S&P 500 index return data. The data was downloaded from the Yahoo Finance historical data archive, and the initial data were the daily closing prices for the S&P 500 index, covering the period from December 30, 1927 to April 17, 2020. So these were converted in about 23,000 daily log returns, where the log returns are the logarithms of the ratios of the closing prices from 2 consecutive days. Now, finally, we converted this data to the growth periods where the daily closing prices increase from one day to the next one, so that the log returns stay positive. And we had about 5,540 observations. So in this case, the NI are the duration in days of the growth period, while the XI and the YI are respectively the magnitude and the maximum of the daily return for the ith growth period. So note that in this case, P was less than Q, so it was like 1 underinflated. And so we have that the example of underinflated ones, and this may reflect that the fact that S&P 500 is a composite index, which is more stable, that is less prone to a change from growth to decline, that is compared to an individual stock. So the fit of this GT model to S&P 500 data is observed in this figure. And although we did not aim at a formal goodness of fit analysis, we wanted to present some visual evidence of the reasonable fit of the model. We fitted the marginal distribution of X and Y and the conditional distribution of X given M and Y given M for N equal to 1, 2, and 3 consecutive days. So all the QQ plots shown reasonable to very good fit. Note that the marginal of maximum is particularly impressive given that the values of the maxima of the episode did not play any role in the estimation. Now, I would like to talk about the generalized linear model that we built for this Tetlag. So we are introducing this GLM to model events depending on covariates. For example, geographic location, altitude, or something like that. So that the parameters of the model depends on the covariates, which make the model more flexible. So in this slide, we formally define the new GLM and later discusses estimation of its parameter. We define x1, x2 to be a IID exponential with parameter lambda and n to be a geometric distribution with probability of success p. The PDF of the TET leg with parameter p and lambda is from Dr. Kozobowski et al. Paper from 2011. So to build a GLM, we allow the ith observation of the xyn to have parameters p and lambda dependent on covariates zi and wi. Since p is a value between 0 and 1, we decided to use a logit function to describe the dependence on p on its m covariates, and we formulated this in this link function in formula number 8 in this slide, where beta is a vector of parameter, and this is the vector of real value unknown coefficient, and zi is the vector of the covariates for pi, with I that goes from 1 to m. Then, since lambda is a parameter greater than 0, we model the dependence of lambda on its k covariates using an exponential function. And so here, this is described in formula number 9, and we know we have eta, that is the vector, again, of the real valued unknown coefficient, and wi, that are the vector of covariates for lambda I. And the covariates for p and lambda may be the same or different, it doesn't matter, actually. And our method is described for more general case of possibly different covariates. The choice of the covariates should be driven by the knowledge of the application. For example, for our example in this paper, we talked with an expert in finance. So now let's talk briefly about the estimation setup. So in this part, we explain the estimation process for the coefficient beta and eta. So to estimate the parameters, we perform numerically maximum likelihood estimation. And because of the functional form of the likelihood function, we can estimate components of the vectors beta and eta independently from each other. So you can see the log likelihood function in equation 10, and we note that this function is easy to split in function of eta and function of beta, so it was possible to obtain two different functions, g of eta and h of beta, and optimize separately. Now, here we prove the existence and uniqueness of the MLE, the two results in this slide, and show the condition that ensure the existence and uniqueness of the MLE for eta and beta. So please note that n is the sample size and k is the sample size and k is the vector of w covariates associated with the parameter eta, and m is the number of z covariates associated with the parameter beta. As we can see from the first result, there is always a unique MLE of eta as long as we have enough data n greater than k, and the covariance matrix W is of full rank. However, as shown below in the second result, the situation with the MLE of beta is not quite the same. Its existence and uniqueness is not guaranteed even when we have enough data n greater than m, and the covariance matrix Z is of full rank. In addition here, there must be enough data where the Ni values are greater than 1. Then we talk about the model validation that we use. So our goodness of fit procedure is a mixture of known and often used standard methods for the validation of a generalized linear model, and a new method based on checking distributional fit of the marginal and conditional distribution of the model to corresponding empirical data. Since in a typical GLM, the observation of the response variable are not identically distributed, standard analysis of the residual does not apply. Thus, typically, the distributional assumption of the GLM are not verified. So we propose a new method to check this assumption for our GLM, and the method rests on the idea of transforming the independent observation into independent and identically distributed ones. So then I would like to talk about the simulation and accuracy. In this slide, we present a snapshot of an extensive simulation study. we will assess the accuracy of parameter estimation and model validation. We simulated 2,500 sample of size n equal to 500, 1,000, and 2,000 observation of xi, yi, and I that comes from tetleg with parameters p, I, and lambda I. So the distribution that we see here, we see that the values of all covariance were simulated independently from the standard uniform distribution on 0, 1. We tried also to simulate from other distribution, but standard exponential and normal, and all of them works. We are just showing the result for the standard uniform, just to let you know. So then the MLEs of beta and eta were derived for every simulated sample. The distribution of the MLEs are presented as box plot and for all sample sizes in the figures for beta. So in this figure, exactly, you can see the beta 0, beta 1, beta 2, beta 3, and beta 4, where the BI stands for betas, and for different sample sizes, n equal to 500, 1,000, and 2,000. The horizontal red line shown in the figure is the true value of each betas. Then in this example, the error size that we found, the larger percentage error was for n equal to 500 and for beta 0, and it was less than 3.5%. Then I would like to talk with you about the application. So in this slide, we briefly mention an application of the GLM to the S&P 500X index. So we modeled the growth periods to the log returns between January 2nd, 1948 and April 17, 2020 here. So the covariates that we consider were inflation rate and unemployment rate and 10 years treasury bond. We found that the model with only inflation and unemployment rates performed the best. And the second part here, you can see that in this part, in order to decide which model was performing better, we compare the various models using the likelihood ratio test. So I really thank you, all of you, professor and colleagues, for your attention. This is an example of my bibliography used for the research. Do you have any question? I cannot hear anyone. You should unmute yourself. I'm sorry about that.
Yeah. Thank you, Francesco. Nice talk, and thank you. Do we have any questions or comments for Francesco? That may be a good thing, because we should have started the next session 10 minutes ago. So, Satish,
Hi, madam.
is it all right to start the next session?
Okay, let us. Okay, thank you so much. The speakers of this session, for your nice presentations, and we would like to extend our gratitude to Professor Anna Penarowska for chairing this session, as well as to Professor Kusmowski for organizing the session in a nice, very good, very excellent session. Now let us move to the next session. Next session is also, in fact, it is a continuation of Professor Kusmowski's session, and we split it as another session because to help the chair. And in this session also there are 3 speakers. I invite Dr. Satish Sridhar for chairing this session, and Dr. Rakhi Ramachandran to co-chair, to support him as a co-chair of this session. This session is also concentrating on the recent advances in distribution theory. Thank you, Professor Kusmowski, for having your association or your support to our webinar in this way. Okay, thank you. Welcoming all. Raki, kindly introduce Sadish to them and thereby hand over the further proceedings to Dr. Sadish.
Okay, sir. Thank you, sir. Good morning, all. Welcome to the new session. The present session is chaired by Professor S. Satish, who is the professor in the Department of Mathematics and Statistics with the Academy of Science and Technology, Thrissur. He is an eminent researcher having more than 55 publications in several reputed journals like Statistics and Probability Letters, Communications in Statistics Theory and Methods, Metron, etc. His special areas of interest in research is distribution theory. I humbly invite Professor Satish to chair the present session. Welcome, sir.
Thank you. Thank you, Dr. Satish Kumar, and also in this session, we have three speakers here, Dr. Matthew, Dr. Charles, and Dr. Elijah. We have 15 minutes for the presentation and for about 5 minutes for discussions, questions, whatever. So let me invite Dr. Matthew for his presentation on Pareto normal distributions. Dr. Matthew, please.
Okay, hello everyone. Please, I hope you can hear me.
Yes.
So I'm not yet, I'm not yet a doctor. So let me clarify that before I proceed. But then let me see if I can share my screen. Let me see a window.
But you are way on your way.
Yes.
Well on your way to becoming a doctor soon.
Please, I'm sharing my screen now. Can you see?
Yes, yes.
You are ahead of time and have given your doctorate.
Awesome. Okay, hi everyone. So my name is Matthew Ohiming, and then I'm from the University of Nevada, Reno. Today I'm talking about the Pareto normal distributions, theoretical framework, and computational issues. Now I must point out that this is a joint project with Dr. Tomasz Kozubowski, who is my PhD advisor. The outline of my presentation is as follows. I'll talk about the motivation for this project, and then I'll move on to the random summation scheme, talk about multivariate Pareto normal distributions, multivariate skewed Laplace mixtures, then we just narrow it to the one-dimensional case of the Pareto normal distributions, and then a Pareto normal parameter estimation. And finally, we present some estimation results, and then we look at the summary. Yeah, that'll be the final thing. Okay, so now, as you all know, the normal distribution is of cardinal importance in probability and statistics. Among its many roles is serving as an approximation to sums, deterministic sums, which come up in a lot in applications. Now, this is possible because of the central limit theorem, right? And some of the limitations of the normal distribution serving as an approximation of a deterministic sum is it lacks flexibility in terms of distributional tails. It also lacks flexibility in terms of symmetry, because as we all know, the normal distribution is symmetric, so it doesn't account for a case whereby a data set is asymmetric. And then it also, the normal distribution is also light-tailed, so it's not a very appropriate fit for a data set which has a heavy-tailed distribution. So a natural question that comes up is, if the deterministic n is replaced with a random n, does the data set, or in such cases, does this sum, which would be a random sum, be modeled using a normal distribution? Well, I must point out that this question is important because it comes up in applications too. For example, in insurance, we can look at the random sum being representative of the total claim for a period. Now, the n in this case is random because we don't know the number of claims which will occur, or which occur in a period. Now, another instance is in finance, a change in an asset value over a time period is also a random sum because we can see that to be a cumulative effect of random number of changes over a time period, right? Okay, so, give me a sec. Okay, I think that should work. Perfect. Okay, so now to demonstrate that a normal distribution is not always an appropriate fit for a case whereby the n is not deterministic, we perform an experiment whereby we are summing over a sequence of S sub I, random IID random variables which follow the uniform distribution on -1 to 1. And for this, we try to obtain kind of like an estimate of the empirical density plots of the distributions, right? So the first row illustrates like the histogram plots, histogram density plots, and the first row, and then the second one represents the respective box plot. So each box plot can be found underneath its histogram plot. For example, for this 100 that you see here, this matches to the histogram plot right here. So now, for this, the goal was to try and get an idea of how the distribution will look like, whether it will take the bell shape, in which case a normal distribution will be a good fit, or when we change the n from a deterministic n to a random n, whether it will also take the bell shape. Now, looking at this plot, for the first one, we chose a deterministic sum, right? So that one, we are summing over 100. And as you can see, using 10,000 simulations, the density plot and then the box plot all bear witness that a normal distribution will be a good fit because it takes the shape of a bell curve, right? However, when we change this n to a random n, which is geometrically distributed, then you can see that the data is much more peaked in the middle at 0. And then in this case, the normal distribution won't be quite an appropriate fit because this was really peaked in the middle, right? So you can probably do better with a different model. Now, for the third one, I use a random n, which is discrete Pareto, from the discrete Pareto distribution. And then this is similar to what we get in the second case where the n is geometric. But one very stark thing that comes up is you can clearly see that between the second plot on the histogram here and the third one, this one has a lot of heavy, very large values from where a chunk of the data points are concentrated. That means that this accounts for heavy tail. So the takeaway from this experiment is that changing the n from a deterministic, changing it from a deterministic n to a random n could help for what? Accounting for heavy tailed data. Now, so the approach is we are changing the deterministic to a random, and we hope that this will be an extension to the normality in the sense that it will allow for heavy tails and it will also allow for asymmetric cases. Now, we are assuming that we are looking at a family of a random variable n sub p, where the p is in 0 to 1, right? And such that the np gets large as the p approaches 0, and then the p times np will converge in distribution to also a random variable w, which is a non-negative random variable as also p approaches 0. Now, what we are saying is for a random vector, a sequence of random vectors s sub I, which are IID with finite variance, and a random sum converging distribution to a random vector y as the p approaches 0, then the stochastic representation of this is given by y, the random vector y, which is equal in distribution to the constant vector m times the random variable w plus the square root of the w times the random vector x, which is multivariate normal with the mean 0, the 0 vector, and then the covariance matrix, which is capital sigma. Now, I'm pointing out that this is with dimension d, right? Now, what you're saying is when we consider such a case, then it is possible that the y can be skewed and heavy-tailed, right? Now, when the n sub p is a family of geometric random variables, then the limit that we obtain is a multivariate asymmetric Laplace, which has been extensively studied, and this is the reference for that. And in fact, the graph that I showed you on the previous slide in the middle is a case of this. Is such a case, right, where the n, which is the random variable, is geometrically distributed. So that's what you see there. So in this case, the Laplace distribution will be an appropriate fit for such a case. Okay. So now a limitation of this is as you can see, we can do better with the tails, even though it allows for asymmetric cases. We can do better by extending it to more heavy-tailed data sets, and that's what leads us to our proposal that we rather use an n sub p, a family of distribution n sub p, which is going to allow for a tail, which is going to follow the discrete Pareto distribution, whose probability mass function is given by this, right? Now, the point is that using the same scheme, the same randomization scheme, in this case, as the p approaches 0, then the p and then p times n sub p will converge in distribution to a random variable w, and then the random variable w in this case will follow the Pareto distribution of type 2, also known as the Lomas distribution, right? And the survival function is given as follows, right here. Now, a point of note is as this alpha approaches 0, then we run into the geometric exponential dual pair, since the Pareto distribution here will converge a distribution to an exponential, and then the geometric and then the discrete Pareto will converge will become the geometric distribution, right? Now, following the same scheme as we saw in the previous slide, the stochastic representation is just identical. It's just that in this case, the W is what? The random vector W is Pareto, and then the X stays the same. Okay, so now we proceeded to decompose this random variable W into some independent components, which are the exponential, the standard exponential, which is E, and then the capital E, and then the capital T, which follows the gamma distribution with scale and shape parameter, which is given by 1 over alpha. Now, the motivation for decomposing it is if you replace this W in the stochastic representation expressed on the previous slide by this decomposition, then we can see this to be then conditioning on T. We can see the new limiting distribution to be a conditional a mixture of what skew Laplace. Right? So when you condition it on T, you get like asymmetric Laplace. So with the T, not the T as a random variable, you get a mixture of skew Laplace distributions. Now, the importance of this is because there has been extensive study on the properties and other features of this asymmetric Laplace. We can just condition on T and be able to derive several properties along those lines. Now, one thing I want to point out is because the PDFs and the CDF lack explicit forms, it makes parameter estimation a bit challenging, as you will see on the coming slides. Now, this is just showing the PDF, some PDF plots giving some combination of parameters, and then the CDF plots using Monte Carlo simulation. Because as I said earlier on, we don't have a closed form for the CDF and the PDF. Okay, now narrowing it down to like the symmetry case and the 1D case. For the 1D case, this is going to be of heavy tail of order 2 over alpha. Now, I must point out that if it exists, if the moments exist, then the expectation is 0, and then the variance is given by sigma over 1 over 1 minus alpha, right? And then to try and estimate these two parameters, which are alpha and sigma, we looked at two approaches. So the method of moments estimation and then the EM algorithm. Okay, so now narrowing it to the MME approach. Now, for the MME approach, we understand we are comparing theoretical moments and observed sample means. Now, because a lot of these means do not exist, we fell on using logarithmic and reciprocal square root of absolute moments. Right. So solving these two equations, we obtain the estimates for the sigma, which is sigma hat given by this, and then the alpha hat is a solution which is obtained numerically, also given by f of it's just going to be the alpha hat, which we will plug in the function f to make it equal to r. So it's just we use numerical approaches for this. And now the alpha hat is given the f of alpha is given as follows. We have the r given by this, and then the constant c sub 1 and c sub 2 also are given as follows. And in this case, I must point out that the psi of something is just a digamma function of that value. Now, following through with the EM algorithm, the approach is as follows. Now, we were able to observe that the bivariate model has the joint distribution is what? It has a closed form. So that was a very good motivation for following through with the EM algorithm. So now the log likelihood of this is given as follow. And then with the two steps that we looked at for finding the maximum value for the parameter estimates, look at the E step and the M step. So for the E step, we are just replacing, because we looked at the Y being the observed and then the T being the latent variable, we are just conditioning on Y and trying to obtain the conditional expectations of the variable T sub I in the log likelihood. Right. So, for example, for the T sub I here, we replace with what the expectation of T given Y equal to Y sub I. For the log of T sub I, we replace it with what expectation of log of T given Y sub I, and then given Y equal to Y sub I. And then for the square root of T sub I, we replace with what the expectation of the conditional expectation of square root of T given Y equal to Y sub I. Now, for the M step, we just maximize this, and then we obtain several values which will stabilize in the long run, in the sense that the current value, the difference between the current value and the previous value will be very, very small. Okay, so now this is just the general, the two expressions for obtaining the estimates, right? So for the K+1 step of the EM algorithm, we get a sigma estimate to be given by this expression. And then the alpha estimate for the k+1 step will be the solution to this equation given over here. Okay. So now, given the challenges, these were some of the results we obtained for the simulation studies. And given all the challenges, I'll say it's working pretty okay. Okay. And then this is just a snapshot of the ongoing projects. So in the long run, we hope to obtain a flexible univariate and multivariate probability distribution that incorporates skewness and heavy tails. And we have a solid theoretical justification using the random summation scheme. We know that we'll gain Laplace-like distributions, which will be heavily peaked at the mode, right? And then we have a new class of Pareto normal. We expect computational challenges because even with the 1D case, there's a lot of difficulty getting you don't have a close one for PDF and CDF. So even getting the shape of the densities and the CDF is a challenge. And then because we know that if we condition on T, we get we get the asymmetric Laplace. This is an extension, right? So we can extend this as a Pareto case in the random summation scheme. So that's all for today. Thank you very much for your attention. And here are some references.
Thank you, Dr. Matthew. It was a very nice presentation. Are there any questions?
I have one. May I ask to Matthew?
Dr. Matthew?
Okay. Matthew, means I just wanted to know you to initialize the EM algorithm. Are you using the initial values from method of moments or some other method?
Yeah, precisely. Yeah. So you expect the estimates to be around the same values, and the method of moments is quite direct. So yeah, those were the initial values. Yeah.
What if the estimator's method of moment estimator doesn't exist, or if you don't able to find? And
so given the conditions, the method of moments when obtained will always exist. Okay. But then that would be a good thought to put into it to consider something. Yeah. But then if it doesn't exist, we just pick any random value, just that probably it will delay, like maybe the process will delay a bit because it may not be, the method of moment gives us a range where to be close, converge quickly. So maybe it will delay more or something. That's what I'm thinking. Yeah.
Okay. Thank you.
Yeah, thank you.
Dr. Matthew? Hello?
Yeah, hi.
You were discussing about the assumptions behind the random summation scheme, right?
Hello?
You were discussing the assumptions behind the random summation scheme.
Okay.
There you assume that that integer valued indexing random variable goes to infinity in probability, right?
Yes.
Do you need that such as strong conditions for the transfer theorem?
Please, could you come again? I couldn't hear the last part. I'm letting the NP.
Do you need that strong condition?
Yes.
For the existence of the limit. The usual transfer theorem do not demand that condition. Usual transfer theorem of Nedenko do not demand that the indexing random variable should go to infinity in probability.
Okay.
Here you are assuming that perhaps you are using the version of SAS theorem, SAS 1972.
Okay.
My question is, do you require that strong condition in this context?
Okay, yeah. So in this context, what I would say is, what I know about that is, with the central limit theorem, we are assuming that as the n becomes large, then we are approaching the normal distribution. So we want this n sub p to become large.
That I understand. My question is whether you need that stronger condition that NP goes to infinity in probability.
Do I need the assumption?
Yeah.
Okay, yeah. So under this condition, I'll say yes. That's what I'm looking at.
Okay. Thank you.
Yeah.
Thank you, Dr. Matthew. Thank you for the nice presentation.
Okay.
Let me invite the other speaker. I think we are running out of time.
Okay.
So I am a bit rushing. Once again, thank you, Dr. Matthew. Next speaker is Dr. Charles.
Okay, thank you.
Dr. Charles?
Yes.
A general statistic model for bivariate episodes. driven by a gamma sequence. Are you ready?
Yes, I'm about to share my screen. So share entire screen. Okay. Share now.
I think Matthew has to stop sharing his screen.
Okay, Matthew, can you stop sharing?
Yes, please. Are we good now?
Yes.
Okay.
So do I share entire screen or I should share the window?
Yes, right.
Okay.
Right. You are now you are to share your screen. Now we can see you only. Please share your screen and welcome Dr. Charles.
Okay,
to this
thank
session
you.
of the conference. Please.
Okay. Do you see my presentation?
No, not exactly.
Okay.
I think it's coming up.
Oh.
It was coming. You have to go to that screen, I think.
Okay. Do you see that?
Yes.
Yes, yes. Now we can see you. Thank you.
Okay. So
there. It's there.
Okay, so thank you very much. My name is Charles Amponsa, and thank you for inviting me to give a talk on a general stochastic model for bivariate episode driven by a gamma sequence. And this work is a joint work with my advisor, Dr. Tomasz Kozbowski, and my committee chair, PhD committee chair, Dr. Anna Panowska, right? So I also want to thank the organizers of the conference, the University of Kerala, the Indian Society of Probability and Statistics, Kerala Statistical Society, and Dr. Panowska and Dr. Kozbowski for everything. And also thanks everyone who is watching and listening to this presentation. So the outline of this presentation is going to be, we start with the introduction, and then we do a quick review on some of the bivariate models that are in existence. And then I dig deep into the general bivariate model, which I'm going to talk about today, and then provide some references, and that's it. So let's get started with the introduction. All right. So the focus of this talk is going to be models of this form. You have a bivariate vector X, which is a continuous random variable, N, which is discrete. And then on the right-hand side, it's stochastic representation. That means that the X is a random sum of Xi's, and then of course, N is N. Now, what we are going to assume is that N is an arbitrary discrete random variable on the natural numbers. And then Xi's are IID gamma variables. And then also we're going to assume that this sequence Xi's are independent of N. Now, here are some of the motivation of this model, right? Suppose you are an investor. You have an investment in some asset or whatever you have an investment in, that the value of the investment changes over time. And so as an investor, you may be interested in the duration and then the total return of the growth episode. Now, if we get back to the graph, I can explain the growth episode well for you. So if you take a look at the graph, on the right-hand side, on the y-axis, we have the log returns. On the x-axis, we have time, right? So if your log returns are positive, then it's an indication that the value of the asset is growing. And if the log return is negative, then it's declining. Now, the focus of this study is interested in the situation where we have growth. So where we have decline, it's not considered, right? So how do we come out with that growth episode? Because it has to do with finance, we call it financial growth episode. So this Xi in this graph correspond with the daily positive log returns, because it has to be positive for you to experience growth. And then of course, it's just the logarithmic difference between the current and the previous value of the asset or the price, right? So how do we do it? The N is counting the number of days in which the asset keep growing, because if your log returns stays positive for a certain number of days, it means your asset is growing. So And then X represent the sum. So in the first case, we have X1, X2, X3. N tells me N is equal to 3. And of course, N can be measured in days, month, or whatever period. But for the purpose of this study, we consider daily returns. So here we have 3 days in which the value of the asset is increasing, and then the corresponding sum, which is the cumulative log return, right? Once it declines, we stop. Once it starts growing, and we count again. And then, so with that scheme, that's what we call the financial growth episode. N is the duration, X is the magnitude. In finance, the magnitude is the cumulative log return. So putting the X and the N together, we call it what? Episode of growth. Another motivation is in the insurance industry, where the XIs could be explained as the individual claims. And then the N could be the frequency. In that case, the X becomes what? The aggregate claim random variable, right? So these are the two motivations. There are other areas in which you can apply this model, but for the purpose of this talk, I'm just looking at these two. Now with this, we just want to do a quick review of the existing model. Because of time constraint, I pick these two models. There are several of such models, but I picked these two models so that which is relevant to the talk. So if we look at the table, if we assume that the sequence xi for the first row, xi's are exponential, and then the n is geometric, then we have what we call the Berg model. And the Berg is simply bivariate exponential geometric model. Of course, this model was proposed by Kozbowski and Panofska. And then a natural extension of the Berg model was done by Barreto Souza in 2012, where he assumed gamma variable. In that case, alpha could be any value, and then n is geometric, and he called that as the BGG model, which is the bivariate geometric model. Okay, so with this, just a quick review, let's now focus on my general case. And what makes it general is a sense that, which I'll talk about in the next slide, is I will talk about the PDF of the general case. I'll talk about the basic properties of this model, estimation and application in a situation when the distribution of n is heavy tail. So let's start with the joint PDF. So it is general because I'm assuming that n follows an arbitrary discrete distribution on the natural numbers with PMF f of n. Of course, the distribution could be Poisson, geometric, or any discrete distribution which is defined on the natural numbers. Okay, Xi's are, as assumed already, is IID gamma independent of this. If you have that, then the joint PDF is always of the form. So if you specify the f of n, you get the specific PDF, right? So I want to recount some of the properties of this model. And the first one that I want to talk about is the Laplace transform. And it turns out that the Laplace transform, which is basically an expectation, can be obtained if you know the probability generating function of n. So all you have to know is just give me the probability generating function of n, and then I throw in whatever is in here and I get my Laplace transform. So I just provided a remark which has to do with the BGG model. In the BGG model, n is geometrically distributed, and so the Laplace transform is given by the equation here. And so once I throw in this whole expression for s in this equation, it simplifies nicely into the BGG case. And that's one property. The next property is the moment and tail behavior. We know the distribution of n could be light tail or it could be heavy tail. So if it happens that the distribution of n is light tail and all the moment of n exists, then of course the mixed moment, which is expectation of this, also exists, right? We have a problem when n is heavy tail. If it is heavy tail, then we expect that the survival function of n should behave like a power law. In that case, the joint moment may not exist, and the proposition below provide a condition in which the joint moment will exist. It says that if you want to compute the mixed moment all you have to look out for is look for the exponent in this power, in this function, and then you, if the sum is less than that, then the mixed moment is going to exist. If the sum is greater than or equal to, then you are not guaranteed to have joint mixed moment. The next is the covariance and then the correlation. And the condition that you require is that the variance of n should be finite. If the variance is finite, then the covariance matrix is given by this, and then the correlation is given by this equation, which is that. And in the case of the BGG model, and the Berg model, the n is what? Geometrically distributed. So the mean expectation of n and the variance, they are all exist. So if you compute that and you plug in this, you get a very nice formula. For the Berg model, you just have to set alpha equal to 1 in the BGG, and then you get the correlation to be square root of 1 minus p, which is pretty nice. Now, the other property which I want to talk about is the infinite divisibility. So I will just do a quick recall of what infinite divisibility is. So let me use a random variable y. And so we're going to say if y is infinitely divisible, then it should have this stochastic representation for each natural number n. So what it means is that you can then break this y into IID random variable such that the distribution of y is equal to the distribution of the sum. If it happens that way, then we say y is infinitely divisible. Additionally, if y is an integer value random variable defined on n0, n0 is a union of 0 and natural numbers, and then also the sequence yi and y1 to yn are also defined on this n0, then we say y is discrete infinite divisible, right? So that's what I wanted to point out in this case. Now, it turns out that our vector, or the distribution of our vector, will be infinitely divisible when two conditions are satisfied, and that is given in the theorem. We require that the sequence of IID should be infinitely divisible. That's one condition. And then for the arbitrary n, if you shift it to 0, if you shift the distribution to start from 0, if that distribution is discrete infinitely divisible, then you are guaranteed that the distribution of our vector is going to be infinitely divisible. That's what this theorem is saying. So we require two things. An example which I provided in this corollary is that if you look at the Berg and then the BGG, the IID sequence are gamma, and we know that gamma is infinitely divisible. The n is geometric, and if you shift the geometric to start from 0, that geometry starting from 0 is discrete infinitely divisible. So because of that, the Berg and the BGG are automatically infinitely divisible. Now, the next is look at the conditional distributions. So the first conditional distribution is when we condition on n, x is the sum of NIID gamma. So if you sum IID gamma, you get gamma. So that is pretty straightforward. Now, the next is that if you condition on x equal to x, of course, that is not well-known distribution, and it has a PDF which is given by this equation. Of course, C is the normalizing constant, n is the probability mass function of n, and of course, this function. So this function appears in here, and this function is defined by this function given here when lambda is equal to beta x. It turns out that this function that is defined here is a generalization of a Poisson distribution. So I just wanted to point out that it has a generalization of Poisson distribution in it. And then we also have a conditional distribution of n given x is greater than little x. And so it has this PDF. Now, one of the usefulness of this conditional distribution is that you can use to assess the goodness of your fit of your model, the bivariate model, to the data. So if you fit it to the data, you can check the conditionals. If they fit well, that will be a good assessment, which I will provide at the end of this talk. Then the last conditional distribution I want to talk about is related to the SS random variable NU. That is, if you look at N greater than U, the difference between N and U, SS random variable. And if you have a sequence of IID gamma, which is independent of this SS random variable, then the conditional distribution of our vector, given that N is greater than U, has a stochastic representation of this form. Very nice stochastic representation. The next that I want to talk about has to do with parameter estimation, right? And so what we're going to, since N is an arbitrary distribution, we're going to assume that N has a k-dimensional parameters with PMF given by f of N, and then we have the parameters in there. It turns out that the log likelihood function can be written as sum of three terms. We have R of alpha, beta, and then Q of what? Omega, which are the parameters from the N, distribution of N. And of course, we have minus this. Now, this term is independent of the parameter, so this term do not play any role in the estimation. Now, we can see that Q of alpha, R of alpha is given as here, and then Q of omega is given as this function. Now, Q of omega is based solely on N. What it means is that the estimation of alpha and beta is independent of estimation of omegas. So since we don't know the distribution of the omega, I would then focus on the estimation of alpha and beta, which is coming next. And it turns out that, yes.
We are running out of time.
Okay. And it turns out that, so how many minutes do I have?
5 minutes.
Okay. And it turns out that the MLE exists and it is unique, and the MLE of alpha solves this equation. The MLE of beta is given by this, and under regularity condition, the MLEs are consistent asymptotically, normal, and efficient. Now we look at the case where N is discrete Pareto. So if N is discrete Pareto with PMF, this discrete Pareto is studied in Budana. It turns out that this discrete Pareto is heavy tail because this discrete Pareto is the discrete version of Pareto type 2, right? And the special case is if the delta is equal to 0, the discrete Pareto becomes a geometric in a limiting sense. And the joint distribution and the property follows from the general case if you specify the properties for the N. And this distribution is denoted as that one. Here, I just want to mention that the parameter dimension is 2. And one suggestion for estimating this parameter, which has been developed by myself and Dr. Kozbowski, you can have a look at it. I'm not going to talk about that one because of time constraint. Now we take a look at an application to data set, which was obtained from investing.com, and it consists of daily closing prices of Bahrain All-Share Index from May 24th, 2010 to February 2019. And we computed the daily log returns and then computed the growth episode from the daily log returns, and we had 508, assuming that these vectors come from IID from a bivariate model with discrete Pareto N. We estimated alpha and beta, and then of delta and P, we use the EM algorithm that I developed with Dr. Kozbowski. And then we assess the goodness of fit of our model to the data set. So we check the conditional distribution of X given N. So when N is equal to 1, N is equal to 2, that means that you have 2 days in which your value of asset is increasing. So we check the histogram, then QQ plot, and it shows a reasonably good fit. Now we go ahead and use a Kolmogorov test statistic, and again, the p-values with 5% alpha significant level also indicate that you do not reject. That means the distributions are identical, and that's a reasonably good fit for us. The last conditional distribution is N given X is greater than little x. And so we plotted the empirical probabilities versus the theoretical. and it shows that all of them are aligning on a straight line, showing a reasonably good fit. And also we did a chi-square test for that. And also at 5% or even 10% significant level, you do not reject. That means that the distributions are identical. So it's a good fit to the Bahrain all-share index. And this, we get to the references. Here are the relevant references that I mentioned in the work. And thank you.
Thank you, Dr. Charles, for a very nice presentation. We have time for one quick question. A minute, please. Questions, please. We have 1 minute.
So what are the next steps with this?
Okay, so the next step with this is one of the next step that I want to look at is dig deeper into the conditional distributions, and also look at, and I can, because we look at just maybe Bahrain, we can also look at multivariate version of this model. Well, I mean, when you go on the stock market, we have several stocks or several financial products. We can also extend it to a multivariate version. Yeah.
Okay, very good.
Okay.
Thank you.
Okay, thank you, Dr. Charles, once again for the nice presentation. Now let us go to the next speaker. Okay.
Thank you.
Speaker is Dr. Ilaria. He will be speaking on a truncated Pareto distribution. Dr. Ilaria, please. Are you there?
Yes, give me 1 second.
Yes,
I'm sharing my screen. Can you see my screen?
Yes, it's visible.
Sure.
So you have only 15 minutes, okay?
Okay.
Okay.
So welcome everyone. My name is Ilaria Vinci, and today I'm going to introduce you to my research field, truncated Pareto models with the real valued tape parameter. First of all, I would like to thank the organizer of the Wsta 2021 conference, the Mathematics and Statistics Department at the University of Nevada, Reno, in particular my advisor, Dr. Anna Panorska, and Dr. Kosobowski for the kind invitation. During this presentation, I would like to present some topics that I'm working on for my PhD dissertation. We will discuss about a new version of truncated Pareto distribution with the real values for the tape parameters. And I'll give you an introduction on the subject and explain why it is an interesting and an important research. Then I talk about some properties and the calculation of the moments, following a brief introduction about the meaning of stochastic order, since we use this property together with an interesting statistic called the Greenwood statistic to prove some new properties and test for this distribution. We will discuss about the testing hypothesis procedures using the Greenwood statistic and the likelihood ratio test approach, and how we built the confidence interval, the estimation for the parameters of the distribution, and then we will conclude with a relevant example. Before starting to dig in the statistic, this is a brief introduction of Vilfredo Pareto. Pareto was an Italian civil engineer and economist, best known for the 80-20 rule of income distribution that states that roughly 80% of wealth is owned by 20% of the richest people. We are interested in Pareto distribution, which is known for its power law tail. Some of the most known applications for this distribution are in income finance, hydrology and climate, engineering, and ecology. First, I would like to give an overview about the truncation concept. Consider a random variable x that follows standard Pareto distribution with the following PDF. If we truncate or limit the value of x between gamma and nu, then we obtain the truncated distribution with this PDF. Why is important the truncation? Standard Pareto distribution has an infinite right tail. We are interested in truncated Pareto with domain on an interval gamma nu. And the question is why we truncate? This is because many practitioners don't like to work with models with infinite variance. Engineers don't care about the details. They work with the main body of the distribution. And also there are often natural bounds on the value of certain processes, like in hydraulic conductivity. At last, it is important to notice that truncated Pareto model contains standard Pareto distribution as a limiting case. And this is when nu, the parameter nu, goes to infinity, approaches to infinity. In this slide, I introduced the work that was already done about the truncated Pareto in Aban, Merschert, Panarska paper from JASA 2006, called Parameter Estimation for the Truncated Pareto Distribution. Here the author studied the case where the parameter alpha for the truncated Pareto distribution assumed only positive values, so alpha is greater than 0. A random variable x has a truncated Pareto distribution with parameter alpha greater than 0 and the parameters gamma less than nu, and those are between 0 and infinity, if its PDF is as present in this equation. Please note that the power law behavior of the function f of x, because the PDF is a power law of x with alpha, that is the tail index, and gamma nu are the endpoints of the domain of the distribution. The main results of the JASA paper were on parameters estimation that was performed using the MLE, maximum likelihood estimation method. The MLEs of gamma nu are sample minimum and maximum, and the MLE of alpha is the solution of this equation. Note that there is not explicit formula for the estimation of alpha. The main result shown that the MLE for alpha exists with probability 1, and if it exists, it is unique. So we built on this result my work. My work starts here with the extension of truncated Pareto to a distribution with the tail parameter being a positive or negative real number. The PDF has the same form of the power function of x. When alpha is equal to 0, we obtain the PDF as a limit at 0 of the PDF for non-zero alpha. Okay. Here we present the PDFs of truncated Pareto for several examples of alpha. We have a negative alpha on the top row and positive alpha on the bottom row. Note that for alpha equal to -1 here is a special case of the truncated Pareto that is uniform. Typically, we are interested in the right tail of the distribution because the big events are there, but we found some data where the left tail was interesting. In such data, the majority of the data is somewhat large, and there are just a few of the smaller observations, which are the ones where we are interested in. One such example is the baby weight at birth. The case to study are the babies with low birth weight. Another example is the age at death. Here we are interested in case of people dying young. Our work included the derivation of properties and moments for the truncated Pareto. Two are the important transformations that we studied for the truncated Pareto distribution. This property, so the first one is useful in proving results on estimation. The first one is related to x to the power of p. When x is truncated Pareto, then its powers also is truncated Pareto. As for moments, all of them exist since it is a bounded distribution. In order to use the truncated Pareto in practice, we develop a good and practical method of estimation for parameters. This resulted difficult since there is no closed form for the estimation of alpha. A lot of testing procedures are based on the estimators of the relevant parameters, and that is a problem for the truncated Pareto because there is not a closed form. So we looked for testing that does not require the estimation for alpha. Why alpha? Because it's the most important parameter to estimate. So we work on developing the testing procedure that does not require the estimation of this important parameter. Then we have applied the likelihood ratio test to compare the performances. Finally, we calculate also the confidence intervals for the parameters using the classical procedure of inverting the test to derive the confidence regions. Okay. In our work, we use two stochastic orders, the usual and the star-shaped order. On this slide, we review the definition of those two orders. The first, the usual stochastic order, says that X is stochastically smaller than Y when the probability of large events is larger for Y than for X, which translates to CDF of X is greater than or equal to the CDF of Y. The definition of the star-shaped order, stochastic order, we say that X is star-shaped less than or equal to Y when the quotient of the quantile function of X of t divided by the quantile function of Y of t is not decreasing in t. A family of distribution indexed by a parameter theta is stochastically increasing or decreasing with respect to that parameter theta when theta 1 is less than or equal to theta 2, then the random variable x with the index theta 1 is stochastically smaller or greater than the random variable x with the theta 2. Similar definition for stochastically decreasing family, and also the same definition can be used with the usual and star-shaped stochastic order. As test 1, we use the Greenwood statistic, T sub n, in testing and construction of confidence interval. Let x1, xn are IID positive random variables of a sample. Then the Greenwood statistic T sub n is the sum of the square divided by the square of the sums of the observations. The main theorem that we are using in this work is from Arendarchik et al., which connects the stochastic order of the observations with the stochastic order of the Greenwood statistic. In fact, if the family of the observations is star-shaped ordered, then the Greenwood statistic is stochastically ordered with respect to regular stochastic order with respect to the parameter. As the test 2, we use the likelihood ratio test that has the average of the log of xi as the test statistic. The result is that both tests have test statistics that are stochastically ordered, decreasing with respect to the parameter alpha. We show that truncated Pareto family is stochastically decreasing in alpha with respect to star-shaped order. From this theorem, it follows that the Greenwood statistic and the likelihood ratio test statistic computed on a random sample from a truncated Pareto with parameters alpha, gamma, and nu is stochastically decreasing with respect to the parameter alpha. This property is pivotal in construction of tests and confidence intervals correctly.
Dr. Ilaria, we have only 3 minutes.
Okay. Now, in this slide, we move to testing. We test alpha less than a specific value for the null hypothesis versus alpha greater than a specific value. The goal is to design a test delta of size tau for that hypothesis. Remember that Greenwood statistic and the likelihood ratio statistic are stochastically decreasing with respect to our parameter alpha. Then small values of the test statistic point towards large values of alpha as specified in the alternative. The rejection region for the test is when the test statistic is smaller than an appropriate critical number, and the critical number is selected so that the probability of type 1 error at alpha naught is that the required size of the test denoted as tau. The test construction method for the first hypothesis I presented is used for other hypotheses, for example, testing alpha equal to alpha naught versus alpha greater or smaller than alpha naught, and also for two-sided test. So all these tests are also of size tau and unbiased, and all the tests work for the case with gamma and nu are known, and in the case where gamma and nu are not unknown. Then we are also able to construct the confidence interval for the tail parameter alpha using the classical procedure of inverting the test to derive the confidence sets. Important is the estimation of the parameters. We consider two cases, gamma and nu are known, alpha not known, and all the three parameters are not known. Here in this first theorem, we have the first case. In the next slide, we have the second case. In both cases, we are able to prove mathematically that the MLEs always exist and are unique, which is stronger results than the corresponding ones in Aban et al. In 2006. This is an example of modeling with the truncated Pareto. We consider a sample of 1,450 birth weight records from California in 2001. In my research, among 15 variables, I analyzed the birth weight in grams. And we are interested in fitting our truncated Pareto model to the left tail of the birth weight because it contains high-risk cases for low birth weight babies. So I have selected the upper truncation level at, as you can see, in 3,500 grams. Why I choose this truncation? Because this is the average weight of a newborn according with the CDC, Centers for Disease Control. So you can see here the histogram of the truncated data that shows the frequency of the birth weight from 0 to 3,500 grams. In this slide, after the truncation, we obtain a data set of 917 observations. We apply the transformation to our data, studying 1 over the data and obtaining similar case in the example in Aban et al., where alpha is greater than 0, so it's positive. We present here the plot for the log of the survival function versus the log of the data. Look, the dashed blue line is corresponding to the standard Pareto fit, where alpha is estimated with the Hill estimator. And the red line is the fit of our truncated Pareto, which seems to fit much better. What else? In the figure on the bottom, you can see the QQ plot of the theoretical quantile and the versus the sample data for the truncated Pareto. It's really important to say that when gamma and nu are known, the truncated Pareto as a PDF that can be written as the canonical form of the exponential family. It's important that our distribution belongs to the exponential family in the case where gamma and nu are known, because we can use the properties of the exponential families, especially for the derivation of the maximum likelihood estimation for alpha. Note that the MLE of alpha is we found the asymptotic distribution that is the same as in Aban et al. In 2006. However, in our case, the MLA always exists and is unique, which is a stronger result comparing with the result with the theorem in the Abban et al. In 2006. Thank you for your attention. Here I put some references, so let me know if you have any questions. Thank you.
Thank you, Dr. Ilaria. Thank you for the nice presentation. We will have just one question, please. Just one question.
Yes.
One question, please. Or any query, any comments on the presentation of Dr. Ilaria? It seems that nobody is asking any clarifications. Dr. Ilaria, then thank you very much. I also thank. Okay. I also thank all the three speakers in this session, and as also Professor Kusbowski for organizing this session. Thank you, Professor Kusbowski. Thank you, Dr. Satish, for inviting me to chair this session. And okay, please let us go to the next session.
Thank you, professors. Thank you, Professor Kusbowski, for organizing this session and for your support and blessings to our attempts, our webinar. And also, we extend our gratitude to Dr. Satish for chairing this session in a nice way. And now let us move to the next session. Once again, thanking you all. Next session is a special invited session in which also we have three speakers. And to chair this session, we have Professor Sheila Mishra is here with us. Yeah. And Dr. Mahesh Kumar Yadav is also with us. Sorry, Dharmendra Kumar Yadav is also with us to support Professor Sheila Mishra to chair this session as a co-chair. Dr. Dharmendra Kumar Yadav is presently working as a faculty member of Department of Statistics and Demography of National Institute of Health and Family Welfare, New Delhi. He is a very active researcher. He has more than 25 research publications. Apart from that, he edited 2 books. And also he participated in several international level committees and in fact, research collaborations. He is an expert, we hope, in the area of sampling theory, computational statistics, machine learning, health informatics, etc. And Professor Dr. Dharmendra Kumar Yadav is a student of Professor Sheila Mishra. So it is a good opportunity in this occasion. I invite Dr. Yadav to come forward and support our chair by first you introduce the chair of the session and thereby support the chair to for the further proceedings of this session. Yeah. Thank you. Thank you, Dr. Yadav. And thank you, Sheila Mishra.
Thank you. Thank you so much. And namaskar to everybody who is present here in YouTube or on the Google Meet. And it is really an honor for me to again see you all in this 5th international webinar on recent trends in statistical theory and applications. And today we are going to have the 32nd technical session. And we are going to have 3 speakers as we are told. And I'm really very happy to see my co-chair, Dr. D.K. Yadav with me. So if he has joined, because I saw that he got left due to some reasons. So if he is there and he can just follow the instructions.
Joined.
Yeah. So if he is joined, then he may please follow the instructions of our organizer, Professor Satish Kumar. So, Dr. Dharmendra Yadav, up to you.
Sir,
Are you there?
Can you hear me, sir?
Yes, we can hear you.
Actually, I'm not able to listen all of you. Is there any?
We are starting the session
in my device.
Yeah, due to network issues, Professor Sheila Mishra mentioned, some you left due to some network problems. Now we are starting the session in which you have to act as the co-chair and support Professor Sheila Mishra, the chair of the session. So first you introduce Professor Sheila Mishra and then hand over the mic to Professor Sheila Mishra for further proceedings. Can you hear me, Dr. Yadav?
I think he's having some issues. So let us not delay the session because we are already short of time and all speakers are also ready here. So let me introduce myself. I am professor in Department of Statistics, University of Lucknow. And I have been an associate with all of you, especially Professor Satish Kumar, for so many years. And we have been meeting together and we have been conducting many academic activities on various platforms. And it is an honor for me to be with all of you. So with this, I would like to invite Dr. Dipesh Bhati, who is going to speak on 2 new ratio tests of fit for log normal distribution. And as the time is there, we have to distribute it like 25 minutes. I expect you to complete your presentation and then 5 minutes we can have for discussion. So I would now like to invite you, Dr. Dipesh. You may please start your presentation.
Just I will share my screen.
Yeah, it is not. You please try again.
Yes.
Now yeah.
I think now it's visible.
Yeah, now it's visible. Yeah. Yeah.
So a very good morning to all of you, and myself Dipesh Bhati. I am working in the Central Institute of Rajasthan. I am first of all very much thankful to the organizers of this conference, Professor Satish Kumar, who has given us an opportunity to present our work. And I am also thankful to Professor Sheila Mishra, who is chairing this session. And the work which I am going to present today is basically in the field of statistical inference. In this work, we have present 2 new tests for fit for the log normal distribution. This work is a joint work with my PhD student. And the outline of my presentation is as follows. I will introduce the problem, and then we will introduce 2 new estimators for the log normal parameter sigma square. And later on, we will use these estimators to construct the test of fit for log normal distributions. And I conclude with references. So as we all know that a log normal distribution is a very popular and classical distribution in the field of distribution theory, which has a transformation relation with the normal distribution. So if X is a log normal distribution, then log X follows the normal distribution with location parameter mu and the scale parameter sigma square of normal distribution. The density of log normal distribution is given in equation number 1. And it has many applications in many fields like lifetime in the survival analysis, in the field of astronomy. Particularly, it has applications in finance, where we discuss about the log returns in the stock markets, and economics and sociology. And it is convenient and useful models for measuring in exact and engineering science as well as in economics. So to begin with the procedure, we have defined 2 new estimators for the sigma square parameter of log normal distribution. So as we all know that the maximum likelihood estimator of the parameter sigma square for log normal distribution is given in equation number 2, where mu hat is given as the mean of the log of the observations xi. So the another estimator which we are constructing here is based on the first Thiel's index. So the Thiel's index for a random variable, the first Thiel's index for a random variable x is given by the expectation of log of expectation value of x over x. So if I simplify this term, I'll get log of expected value of x minus expected value of log x, and by Jensen's inequality, this difference in fact ensures the positivity, and we will have once if I assume x follows log normal distribution, then we will get this expression as sigma square by 2. So the first Thiel's index is simply reduces to sigma square by 2 for log normal distribution, and this gives us an idea, just similar to the moment estimator, that we can construct a estimator out of it. And if I have a sample x1, x2, xn, then the new estimator sigma tilde square of sigma square is given as 2 by n summation I runs from 1 to n log of xn bar over xi, where xn bar is the sample mean. So this is the first estimator which we have proposed, and the second estimator we in fact propose as the sum of the first two indexes of the Thiel's indices. So for the log normal distribution, the sum of the first two Thiel's indexes also reduces to sigma square, which means, as we see previously, that the first Thiel's index is sigma square by 2. In fact, the second Thiel's index is also sigma square by 2. So if I take the sum of these two, I'll get sigma square. So if you see the left hand side of equation number 5, this can, on simplification, this can reduces to a very nice form, which is the ratio of the covariance of x and log x to the mean of the log x, mean of the expected value, means mean of the random variable x. So this again, if I replace this covariance and expected value with the empirical covariance, which is sample covariance, as well as the sample mean, the estimator for sigma square, we denote it as sigma prime square, is equal to the ratio of the sample covariance and the mean of the observations. So now we will discuss so these are the two estimators which we define in this work, and let us now see the large sample properties of these proposed estimator. So the first estimator, which is in fact obtained from the Thiel's index, first Thiel's index, is a strongly consistent, which we have proved as follows. So if I have observations x1, x2, xn, and these are NIID copies of random variable x follows log normal, and if xn bar and yn bar are the empirical mean of random variable x and the random variable log x, so we, as I mentioned in the beginning, if x follows log normal, then log x follows normal. So we have the expected value of x, which is expectation of log normal, and expected value of log x, which in fact is the expected value of normal. So we get this mu. And according to strong law of large number, we know xn, the ordered pair xn bar comma yn bar almost surely converges to e to the power mu plus sigma square by 2 comma mu. So if I define a function g of x1 x comma y, which is 2 times of log x minus y, which is a continuous at these points, continuous at the mean point, then by continuous mapping theorem, we will get our desired result. So this proves the strong consistency of the parameter sigma tilde square. The next result says the asymptotic distribution of sigma square, which in fact says that if I have x1, x2, xn random variable from log normal mu comma sigma square, then under root n sigma tilde square minus sigma square converges asymptotically normal to normal with 0 comma tau sigma, where tau sigma is a function of sigma square, which is given in this form. So we can simply prove this result by using the multivariate central limit theorem as well as in conjunction with this Slutsky's theorem, and the proof is as follows. So if I have a bivariate vector xn minus theta 1 as well as yn minus theta 1, this converges asymptotically to bivariate normal with 0 mean vector and sigma xi square, where xi square is a variance covariance matrix of these terms xn bar minus theta 1 and yn bar theta 2. So if I assume a if I am interested in the asymptotic distribution of sigma tilde square, then let us assume a function g one xn bar yn bar, which is as follows: 2 times of log x minus y. Again, by multivariate version of the delta theorem, one can refer this Das Gupta book in 2008. We have under root n sigma tilde square minus sigma square converges to normal with zero, bivariate normal with zero mean vector and tau sigma square. And this tau sigma square is obtained as the matrix product of G1 dot theta 1 theta 2 variance covariance matrix, and again G1 theta 1 theta 2 transpose. This G1 theta 1 theta 2 in fact is the first derivative with respect to theta 1 and the first derivative with respect to theta 2 evaluated at the point theta 1 and theta 2. So in our case, this theta 1 is the mean of the log normal distribution and theta 2 is the mean of the normal distribution. So once we evaluate this, we will obtain the variance of this distribution, asymptotic distribution of sigma tilde square. So in the similar fashion, we can also prove the estimates for, means the strong consistency result for sigma prime, which is our second estimate, as well as the asymptotic distribution, asymptotic normality for the second estimator of the second distribution. And in order to let us now jump to the construction of the test statistics. In order to obtain the asymptotic distribution of the test statistics, we may later use the recurrence relations between the moments of the log normal distribution. So these are the 3 recurrence relations which we are going to use in the later deriving the asymptotic distribution of log normal, asymptotic distribution of our proposed test. So the first test is based on the idea that let us take the ratio of these two estimator of sigma n, and the first estimator which we derive, sigma n square tilde, divided by the maximum likelihood estimator of sigma. So if I substitute these two values, the test statistics which we define is 2 times of log xn bar minus yn bar divided by s square y. I should write sny because it is empirical, obtained from the sample. So this is in the line of the Shapiro-Wilks test, and which is being used for testing the normality. So this is in that line, and under the null hypothesis means when my observations xi follows log normal distribution, then this Rn is expected to take values which are close to 1. So so now once we have a test statistics, means once we have a function Rn, we are interested to know what is the asymptotic distribution of this Rn. So to derive the asymptotic distribution of Rn, let us consider an independent sequence of multivariate vector Tn, which is of xn bar, yn bar, and sn square transpose. So by multivariate central limit theorem, we will get Tn minus I is converges multivariate normal to 0 mean vector and sigma square, sigma as variance covariance matrix between P1, P2, and P3. So this is the result which we obtain, the asymptotic distribution of the Rn. So under root n Rn minus 2 times of log of mu x minus mu y divided by sigma square y converges asymptotically normal to 0 mean vector and xi square, and where xi is obtained by this formula, and where in this formula this q hat xi is in fact the takes the value 2 over mu x over sigma square y minus 2 by sigma square y and 2 times of mu y minus log of mu x by sigma power 4. So one can again follow the Arvindan Das book in 2008. They have discussed the derivation of the multivariate delta principle. So in order to derive, we need a lemma which is as follows, and this, with the help of this lemma as well as the previous theorem, under null hypothesis, this Rn converges to 1 as I mentioned. So under root Rn minus 1 converges to normal with 0 comma sigma square, and this sigma square is now given as 2 over sigma power 4, 2 times of e to the power sigma square minus 1 minus 2 sigma square minus sigma 4. So so in order to construct the test, what we will do, we will simply to make it as a parameter free distribution, so we divide it by sigma in both the side. So we'll get Rn tilde. Rn tilde is under root n xi Rn minus 1, which is asymptotically normal as normal 0, 1. So once we define the test statistics as in 12, we are interested in obtaining, because for the large sample size it approaches to normal, but what happens if the sample size is small? So for such we need to first obtain the critical values, so that these values will help us to either accept or reject the null hypothesis. So for sample size less than 200, we reject the null hypothesis at alpha level of significance if the Rn is less than critical value obtained at alpha by 2 level, and if Rn is greater than Cn 1 minus alpha by 2, and Cn 1 minus alpha by 2 and Cn alpha by 2 is obtained by equation number 30. So for large sample, we can obtain these critical points from the standard normal density, which is in fact the Z1 minus alpha by 2. So with the same line, I am not going to take much time. With the same line, we can obtain another test where we take the ratio of the second estimator of sigma n square, which is obtained by the sum of the first two Thiel's index. So the test statistics here is Sxy divided by Xn bar Sn square y, which is again in the line of Shapiro-Wills. So now again this will also be the close to 1 under the null hypothesis, and these are some results for this test statistic. So so this work is still ongoing work, and we have obtained the critical values for this test. However, the comparison study of this test with other available log normal test has not been done, which is still in progressing. And so we can obtain the critical values by following this procedure. To begin with the investigation, we will follow this stepwise procedure to obtain the critical values, in which we just fix the value of the sample size and the parameter sigma square, and generate a sample of size n, where n varies later on. So we will get yi's, and with these yi's as well as xi's, we will obtain the two statistics Rn tilde and Rn tilde hat star. Now we will repeat this procedure b times, where b is the bootstrap iteration. So, and each time we will obtain these test statistic value, and then based on these b values of the test statistics, we will choose the critical point by using the equation number 15 as well as equation number 13. So these equations will help us to find out the critical values, and then to have a power study, we will generate the sample from the alternative family, and then see how many proportion of test statistics falls in the rejection region. That will give us the power of the test. So that work is still going on. So we are doing that work, and these are the references with which we are working on. And just to mention that there are very few tests available for the log normal distribution. Particularly researchers, they simply transform the observation by taking the e to the power x, or by taking log of x. If I take log of x, it goes to normal, and there are ample amount of tests available for testing of normality. So rather than searching for a test statistics which is exclusive for log normal distribution, researchers, they take the logarithmic of the observations and apply the normality tests which are available. But this test, in a sense, do not make this transformation. We simply have a different test statistics. So Batadish in 2016, they recently proposed a new test which we are going to compare our test with this Batadish, as well as Thiel's. You get information about the Thiel's index in the Sarabia, Jorda, Remoza, as well as the Thiel's index by H. Thiel's. So these are the some references, and I sincerely thank all of you for your patience hearing.
Thank you, Dr. Bhati. And it was really an interesting presentation on log normal regarding two new proposed ratio test of fits. And it was really heartening to see that they are exclusively designed for working for log normal distributions directly. So now the floor is open for the questions and the queries or feedback, if there is any. You may please ask your questions or suggestions or any comments. Anyone there?
Deepesh, may I ask a question, ma'am?
Yes, sir.
Yeah. Deepesh, you said the first and second Thiel's indices
Yes,
are
sir.
equal to sigma square.
Sigma square by 2, sir.
Are these characterizing properties of normal?
Sir, yes, sir. These are the characterizing for the log normal distribution.
Oh.
So first one is sigma square by 2. The other one is also sigma square by 2.
Okay.
So that is why we make use of this in the test, in construction of the test.
And also, do you have any discrete analog of this characterization?
Sir, not yet. I think that can be think as a possible work, because discrete analog of Thiel's index has not been explored yet.
Oh, okay. Thank you.
Thanks,
ma'am. Thanks.
So,
Thank you.
hello.
Yes, Dharmen, please continue.
Yeah, so can you hear me?
Continue. Yes, very well.
Due to some technical glitch, I was not able to listen to you because there was some problem in my device. So, good morning, everyone, and thanks to our organizer of this conference, Dr. S. Satish sir, for giving me this opportunity. So, Dr. Deepesh, thank you for your wonderful presentation. I just have one query that which particular software have you used during the simulation in your study?
We are using the R language, so to have the simulation study, R software.
Okay, R software. So okay, so you have just created the population which is following the log normal distribution with some different parameters.
Correct.
Okay. Okay. Thank you.
Okay. Thank you. So thanks to all of you.
Thank you, Dr. Bhatti. So if there are any no more questions, so let us thank the speaker. And it was a wonderful presentation, and we are looking forward for your actual applications and whatever proposed work you are left with. So thank you very much. So now we can move ahead with our next speaker, Dr. K. Jayakumar. So Dr. Dharmen, would you like to?
Yeah. So actually, I'm not getting much detail, but I have shared it from the website. That Dr. K. Jayakumar is presently working as professor at University of Calicut, India, and he will present on sub-exponential distribution. So we welcome to Dr. K. Jayakumar for your presentation.
Yes, and sir, you may take 25 minutes for your presentation, and 5 minutes we can have for discussion. Thank you. You may start, sir.
Okay, thank you. Let me thank Professor Satish Kumar and Professor Sheila Mishra. Thank you all. And let me share my screen first. Is it okay?
Yes, sir. It's visible.
It's fine.
So today's discussion is on sub-exponential distributions. So in this talk, I may concentrate on the class of sub-exponential distributions and give quickly a review on this class of distributions, its connection with the various well-known type of distributions such as heavy tail distributions, class of distributions with the long tails, and the class of regularly varying distributions. So let me review all the literature on this one, and then we will look for some sub-exponential classes of distributions which are introduced by us, and we will look for its properties. So we said that a distribution is in the sub-exponential class if it has the property that the tail of the distribution, tail of that is 1 minus f convolution f, it is asymptotically equivalent to twice 1 minus f(x) as x tends to infinity. So if you are any distribution that has this property, such a distribution, we may call it as the in the sub-exponential class, and you can see that the Pareto, Weber, log normal, etc. will belongs to this class of distributions. So now for give a meaningful interpretation of it, let me consider two random variables x1 and x2. I let x1 and x2 are two random variables which are IADS F. Then the assumption that we have given above, that will in fact indicates that the probability of x1 plus x2 greater than x is in fact asymptotically equivalent to twice in the probability that x is greater than x. So if you have that is such a property, we will say that it is in the sub-exponential class, or in other words, you can have limit x tends to infinity f bar twice convolution of x by f bar x is 2, or you have the limit x tends to infinity integral 0 to x f bar x by own simplification, it will turn out to be this property. Or in general, you can have f bar n convolution x is in fact asymptotically equivalent to n into f bar x. So how you may be able to interpret this? So if you look for the sum of n IAD random variables, and if the sum can be approximated by the maximum, then we may be able to say that the corresponding class of distributions is in fact sub-exponential. So, or in other words, the distribution of the sum we may be able to approximate by the probability of exceedance, which may have a lot of applications in various fields such as insurance modeling and so on. And we can see that all sub-exponential distributions are long-tailed, but the converse need not be true. That is, there are long-tailed distributions which are not in sub-exponential class, and you all know a distribution is long-tailed if you may be able to approximate the survival function of x evaluated at x minus by y is in fact asymptotically equal to probability that x greater than x as x tends to infinity. Here is such a random variable we may call, that is, we have a tail equivalence of this sort. If the random variable x has this type of tail equivalence, then we will say that it is long tail. And for that class of random variables, if you find the hazard rate, as x becomes large, the hazard rate will tends to be 0. And as another class of distributions which is more interesting is the class of dominator variation distributions, and you have the class of dominator variation distributions, the class of long-tailed distributions, and sub-exponential distributions are related through the property, that is, you have the intersectional is a proper subclass of the class of sub-exponential distributions, which is in fact, which in turn is a proper subclass of the class of long-tailed distributions. So that is the what about the class of sub-exponential distributions. And you can see that all sub-exponential distributions are heavy-tailed, but the converse may not be true. That is, there exists heavy-tailed distributions which may not be sub-exponential in nature. And we know that a distribution is heavy-tailed in the sense that the tail of the distribution is heavier than that of the exponential tail. And you can see that the Pareto distribution, the Weibel, etc., may belongs to that class. That is the sum of examples of the one-tailed distributions that belongs to the class of heavy-tailed distributions are the log normal, the Levis distribution, that is, you have the positive stable with exponent 1/2, you have the Burr distribution, you have the log logistic, that is the Pareto, log gamma, Weibel, log Cauchy, etc. are in fact belongs to this class. And in the two-tailed case, you have the Cauchy distribution, and you can have the class which contains the Cauchy. You can have the class itself. That is, you have the stable class itself. It is an example of that, and you have the T distribution that again is in that class. And you have the heavy tail distributions have more and more properties, and you have the Pareto principle. The Pareto distribution will, again belongs to that one. And if you have the Pareto distribution shares the scale invariant property, that is the asymptotic scale invariance property, that is you have a distribution F is scale invariant if there exists an x naught and a g such that f bar lambda x is, you may be able to write it as g lambda into f bar x for all lambda x as such that lambda x greater than or equal to x naught. And you can see that a distribution is scale invariant if and only if it is of Pareto type. And if you look for the Pareto distribution, if you calculate the f bar lambda x in that situation, you can see that you may be able to write it as f bar x into 1 by lambda raised to alpha, or in other words, it in fact shares this property. That is f bar lambda x, you may be able to write it as g lambda into f bar x. So why I am talking of this scale invariant family, all these things is connected with the sub-exponential distributions. And you can see that a distribution scale invariant if and only if it is Pareto, we have already shown that. And you see that a distribution is asymptotically scale invariant if you may be able to write your f bar lambda x by f bar x is some g lambda in the Sx large. And the class of sub-exponential distributions is in fact connected with the class of regularly varying distributions. And regularly varying distribution is this one whose tails you may be able to approximate by power laws. So you have the tails you may be able to tail of the distribution you may be able to represent by approximate by the power laws, or in other words you may have your f bar x is in fact approximately equivalent to x raised to minus rho, where rho is greater than 0. And if you can see that your Pareto distribution belongs to this class, and you can see that the Beeble distribution, etc., belongs to this class, and the regular variation is in fact extremely useful, and you may be able to study the behavior of the distributions belonging to the regular variation class based on the Karamat's theorems and Tauberin's theorems, and based on the methods of asymptotic methods in analysis. And I have already told the sub-exponential distributions have the property that you may be able to, you have the catastrophic principle, that is you may be able to replace the maximum by maximum of x to xn by the sum. That is, or in other words, the probability of maximum of xn to xn greater than t given xn plus x2 plus etc plus xn greater than t, that probability tends to 1. And that is a result that is in fact applied in the theory of random walks, queues, instrumental fields, etc. I'm not going into the details of it. And you have the conspiracy principles also. And for sub-exponential distributions, you have the probability of maximum xn x2 etc xn greater than t. You may be able to approximate it by n into probability that x greater than t, where x is our IEDF. And that has some interesting relations with the various type of various families of distributions that come across in the survival analysis and reliability modeling. That is, heavy tail distributions tends to have decreasing hazard rate and increasing MR levels, and also the long tail distributions have the negation, that is, they tend to have increasing hazard rate and decreasing MR levels. And you can see that not all heavy tail distributions are DHR, and there are some long tail distributions which can be DHR. And now we will look for a class of sub-exponential distributions that is introduced by us, and that is in fact that is we have introduced a generalization of Pareto distribution. That is which was in fact appeared in the Journal of Communication Statistics Theory and Methods, Simulation and Computation in the year 2019 or 19. So how we have introduced it? We have introduced it by looking at a generalization of looking at a relationship between the uniform and Pareto. The uniform and Pareto. You have seen that the uniform random variable and the well-known Pareto random variable is connected through your relation equation number 5. And naturally, you may be able to see that whenever I may be able to replace the y in equation 5 by a generalization of the uniform random variable, it should naturally give a generalization of the classical Pareto distribution. Right. So that is the way that we have proceeded. So we have considered the relationship between the uniform and the Pareto random variable. And the uniform and the well-known Pareto type 1 random variable are connected through the equation number 5. And whenever, if I may replace y in which is uniform 0, 1, by a generalization of the uniform random variable, it may give rise to a generalization of the classical Pareto distribution. And you can see that the distribution that we have come across by that generalization has a number of interesting properties, in the sense that they are heavy tail, they belong to the class of sub-exponential distributions, and in that case also you have the probability of maximum you may be able to replace by the probability of x1 plus x2 plus etc plus x1 greater than t, and we have compared the performance of our distribution with a number of distributions that have recently appeared in the literature as generalizations of the well-known Pareto distribution, and we can see that it may performs well for modeling some data sets. Now the question arises, what is the type of the generalization of the uniform distribution that we have considered? So this we have considered through a work of us which appeared very earlier, that is in a paper that is Ms. Nadaraja, myself and Ristik, where we have introduced a technique for introducing new classes of distributions using what is known as the concept of random maxima or random minima. So that it means that is we have this mechanism, that is you have let us consider the equation number 1, where equation number 1 in fact represents the random variable un, where un is the minimum of a random number of random variables, where n is a discrete random variable, and x1, x2, etc. xi, which we are assuming that they are IID random variables, and at the same time they are independent of n. So then we have considered n as the negative binomial distribution. There is the truncated negative binomial distribution which is truncated with 0, and considered the family of random variables arising out of my un, arising as the distribution of un. And we can see that that family of random variables is in fact a generalization of the class of well-known Marshall-Orkin family of distributions. So, or in other words, that class of random variables you may be able to study through the survival function of this, where f is nothing but it is the common distribution of these xi's, and n I am taking as a truncated negative binomial random variable with the probability mass function, that is gamma raised to theta, that is the probability mass function like this, that is being a truncated random variable. This is the PMF. I have given it earlier. That is, this is the probability mass function of the truncated random variable, negative binomial random variable. That is gamma raised to theta by 1 minus gamma raised to theta, theta plus n minus 1, c theta minus 1 minus gamma raised to n. You can see that. You see that whenever xi's are IIDF and n is truncated negative binomial, then the distribution, the survival function of the un is nothing but it is given by your equation number 2, and you can see that it is in fact a generalization of the class of distributions, and whenever your gamma is equal to 1, gamma tends to 1, the g bar x will in fact turn out to be f bar x. And here what we have considered here is we have taken that is how it is already an appeared work in the journal Statistics in the year 2016. It is in fact a generalization of the uniform random variable, and you can see that as gamma tends to 1, it will in fact becomes the classical uniform random variable. So in our technique, what we have proceeded is that this family has a number of properties. You can see, one can refer to the paper in the Statistica for the applications of the generalized uniform random variable. And here what we are doing here is we are replacing this y in equation number 5, which is earlier uniform, by our generalized uniform. Right. So we are now okay, and that as you naturally expect, that is the equation number 5. Whenever your y is simply uniform 0, 1, it is nothing but it is a classical Pareto. And if you replace your y by our generalized uniform, you may naturally expect that it may give rise to generalization of the classical Pareto distribution, and that we may called in the literature as we have told, we have named as the generalized Pareto distribution, which has with parameters alpha, beta, gamma, and theta. And this class of distributions has so many properties. That is, this in fact belongs to the class of long-tailed distributions. That is, the long-tailed distributions are those class of distributions for which the survival function evaluated at x minus y and x, that is, whenever x is large, you may be able to approximate this. And whenever alpha is finite, it belongs to the class of dominator variation distributions. And also, and automatically you can have your NGP, that is the new generalized Pareto distributions, belongs to both D and both L, and so you can have it belongs to the class of sub-exponential distributions because your D intersection L is a subclass of the class of sub-exponential distributions, and so your new generalized Pareto distribution is a class of sub-exponential distributions. So, or in other words, the NGP is in fact you have. It is heavy-tailed, and it is it has so many other properties that we may look into it. And so you can have you may be able to study the behavior of it, that distribution, that you may be able to characterize that distribution based on the property of the hazard rate function. That is, if your HFX is the hazard rate of a random variable, and if HFX is the hazard rate of any random variable, and if it satisfies the equation that we have written here, the differential equation here, then the corresponding random variable is NGP, and automatically the NGP will in fact satisfy this one, and you have the boundary condition also holds here. And also you may be able to characterize it the distribution based on the reverse hazard rate also, and also you may be able to characterize the distribution based on the truncated moments also. So if x is a function from omega to beta infinity, be a continuous random variable, and let me take the functions q1x and q2x like this one, q1x and q2x is here, q1x is this function, and based on that, if your q1x and q2 are this like this one, then your random variable x has the NGP distribution if and only if this function has the form e raised to minus 1 by 2 minus 1 by 2 e raised to minus x raised to alpha theta. So this has the property that the NGP random variable has the property that you may be able to approximate the probability that you can find the distribution of xn plus x2 plus etc plus xn and find the probability that xn plus x2 plus etc plus xn greater than x. And you can see that that is in fact asymptotically equivalent to probability that maximum of x1, x2, etc. xn greater than x in the NGP case, where your x's are in fact IAD NGP random variables. So that's right. And now we may discuss some applications of it, and for that we may have how to take the data set. That is a data set studied by a number of authors earlier. That is in fact a breaking stress of carbon fibers data, and that is already available in the literature. And to model this one, we have used first we may have to identify whether this data is appropriate for modeling the Pareto distribution, and this the data has been previously studied by Nichols and Badgett in 2006, Wiedemann in 2015, to compare a generalizations of Pareto distributions. So there are also so to compare the performance of the NGP random variable, we have also considered the this data set, and for that, for the comparison, we have considered the TTT plot, and that you also know it is a method to identify the shape of the hazard rate function of the data, and the empirical TTT plot is given by your GRN of which is equal to sigma over I going from 1 to r xi x1 and plus n minus r xrn given by this one, where xin is the ith order statistics of the sample, and you have the shape of the hazard rate function would be the hazard rate function should be increasing, decreasing, or buttock shape, and upside buttock if the TTT transform it is convex, is concave, convex, and convex, first convex and then concave, or concave and then convex respectively. For details you can see in the paper by Arset, and we have the TT data here, and you can see the hazard rate function of the TTT plot here, the TTT plot, and you can see the NGP case, NGP, exponential Pareto, truncated Pareto, Pareto archetype distribution, and so many other comparisons here, and you have your data set itself.
So 2 minutes more to wrap up, sir.
Okay. So from the comparison, based on the usual procedures such as the Agaiga information criteria and this one, you can see that the NGP distribution. So based on all the summary statistics, we can say that as compared to the PPS, Pareto, Pareto Arctan, transmitted Pareto, exponential Pareto, the NGP distribution may becomes better for modeling this type of data and this data. And so with this, let me conclude. And here are some of the, I'm going into the details of it. Here are some of these are the applications of the heavy-tailed distributions in multiplicative processes. You can see that the multiplicative processes we have almost always leads to heavy tails. That is, and our power distribution being heavy tail, it has immense use in modeling multiplicative processes with lower barrier, with noise and so on, and also modeling external processes. And here are some of the references. That is, this is on a generalization of uniform distribution properties, statistic, and which we have generalized. That is, in fact, the nutshell for generalizing the NGP distribution, obtaining the distribution. And this is the work that we are mentioning. That is on a generalization of distribution, which appeared in this one. And these are some of the generalizations of the uniform distribution. And this is another work that is, this is one of the basic work who are interested to learn about the sub-exponential distributions can go to the paper by Kruppelberg, and there is a book on heavy-tail distributions by Kruppelberg that is, and its applications in various fields such as insurance, risk theory, and so on. And another work which is connected with our work is this is the paper that is the Nadaraja himself and Rusty, which appeared in Journal of Statistical Computations. With this, let me conclude and thank you all.
Thank you very much, Professor Jayakumar, for such an extensive, very elaborate and very exhaustive presentation on sub-exponential families. You have given a huge, the dimension of all applications as well, with so many interesting properties of all these distributions. So now the floor is open for the audience to ask the queries, questions, or any comments on the presentation.
Professor Jayakumar.
Yeah. You may unmute yourself, please. Go ahead.
Professor Jayakumar.
Yeah.
This is Satish. I just want clarification. You obtained this distribution as a solution to a differential equation under certain boundary conditions. Okay?
Yeah.
Does this boundary condition have any probabilistic implication or just a mathematical requirement?
It is just for a mathematical requirement and not a probability. Another thing.
Okay. Thank you.
Thank you, Dr. Sridharan, for your question. Dr. Dharmendra?
Yes, ma'am. Actually, before going to our next presenter, I just want to introduce our resource person, Dr. K. Jayakumar, because now I get his CV. So Dr. Jayakumar is presently working as Professor and Head, Department of Statistics, University of Calicut, Kerala, and he has done his PhD on contributions to modeling autoregressive moving average process from the Department of Statistics, University of Kerala, under the guidance of Professor R. N. Pillai. He was former head and professor, Department of Kerala. And Dr. Jayakumar has also done his postdoctorate from Cochin University of Science and Technology, Dalhousie University, Canada, and Memorial University of Newfoundland. He has got many honors and awards like CSIR Research Senior Research Fellowship, NBHM Postdoctoral Research Fellowship, John Ginberg Award of International Statistical Institute, Netherlands, Best Research Paper Award of papers published in ISI cited journals by King's University, Saudi Arabia in 2012. He has teaching experience of 25 years and research experience of 31 years. And his areas of research are distribution theory, time series analysis and forecasting, probability theory. And he has guided successfully almost 10 PhD students and 6 MPhil students. He has been the General Secretary and President of Kerala Statistical Association. So it was just a brief introduction, not only this one, but there are so much, achievements of Dr. Jayakumar. So thank you, sir, being with us.
Thank you very much. Thank you very much. Thank you, Professor Dharmendra, Professor Sheila Mishra. Thank you all. Thank you.
So, can we invite our next presenter? So, can we invite our next presenter, ma'am?
Yeah.
Okay. So now I would like to invite our next presenter, the resource person, Dr. K.K. Jose. And Dr. K.K. Jose is presently Honorable Director, Science, School of Mathematics, Statistics and Data Analytics, BA at Mahatma Gandhi University, Kottayam. He was the Honorable Director of the Department of Biostatistics at St. Thomas College, Palai during 2015 to 20, and was Honorary President of Kerala Statistical Institute, Trivandrum, during 2015 to 18. He was formerly Professor and Head of the Department of Statistics at Central University of Rajasthan. After retirement from regular service as the Principal of St. Thomas College, Palai, Dr. Jose is an elected member of the International Statistical Institute, Netherlands, and a Fellow of the Royal Statistical Society, UK. Dr. Jose was the General Secretary and President of Kerala Statistical Association during 1994 to 2000 and 2000 to 2006, respectively. He was Chairman of PG Boards of Studies of Statistics, Biostatistics, and Actuarial Sciences at University, Kottayam, during 2006 to 2012. He was member and chairman of examination boards of MSc, MPhil, PhD of various universities in South India. So, Dr. Jose is an eminent more than 40 years of meritorious service as a reputed principal, professor, and head of the department, teacher, researcher, and organizer. So, we welcome you, sir.
Thank you.
Thank you. Session.
Hello, thank you. Thank you very much for your nice introduction. Now I am going to share it.
Thank you, sir.
I think Professor Jayakumar has to stop sharing his screen.
Yeah, please stop sharing.
So
that Dr. Josh can share.
Okay, I think Josh now.
How it is saying?
Yes, sir, it is coming.
Can you see? Okay. Can see it?
Yes, sir, we can able to see your presentation.
It's coming.
Yes, sir, it is coming, it is coming. Let me see.
Okay. So my talk is on random self-decomposability and its applications in autoregressive time series modeling. So I am very much grateful to Dr. Satish Kumar for providing this opportunity. And I have been a past student of an alumni of the Department of Statistics, University of Kerala. And my topic on random self-decomposability that actually generalizes the concepts of self-decomposability and geometric infinitability and their applications in time series modeling. And this is actually a tribute to Professor R.N. Pillai. He taught us in details about self-decomposability, geometric infinitability, and time series modeling, which were his favorite topics also. And myself and Jayakumar worked on these areas actually. So, as far as my talk is concerned, so the objectives are actually to review the works in self-decomposability, geometric infinitability, random self-decomposability, etc., which are significant theoretical developments in time series modeling as well as probability theory. And here we illustrate the application with respect to a specified marginal distribution. And finally, some empirical illustration is also provided. So coming to time series modeling, all of you may be familiar with this. Time series is a realization of a stochastic process. It's a sequence of chronologically arranged observed values of the process like atmospheric temperature, price of a commodity, sales, exchange rate of currencies, etc. So it was actually Yule who made a systematic study on time series data, like the world sunspots data, as early as 1927. And Fox and Jenkins made it more systematic. Fox and Jenkins 1970 made systematic study on unit time series models.
Lots of echo is coming. Can you please stop one of the devices? Maybe like you are logging with two devices or so.
Yeah. Echo is coming.
Yeah.
It's not clear?
Echo sounding.
Yes.
No problem.
Echo was coming, sir. Now please try.
Echo is coming even now?
Yes, sir.
The other device mute here.
Okay. So It was Box and Jenkins who made a systematic study on linear time series models called ARIMA models or Box-Jenkins models. And certainly some extensions were made by Subbarao in 1980s on non-linear time series models like bilinear models. So which were actually some generalization of the autoregressive integrated. So that is the ARIMA models with an additional, that is the last term, that is actually a product term. So some sigma I equal to 1 to R, sigma k equal to 1 to S, Cik into x t minus I into epsilon t minus k. So that actually brings non-linearity actually. So this model is denoted by bilinear BL, PQRS. When we are having R and S equal to 0, certainly it will reduce to the usual ARMA PQ model. So I am not going to discuss too much about that. So now we will be coming to the non-Gaussian time series modeling. So far up to 1980s, it was actually an era of Gaussian time series models. But actually researchers are finding it very difficult to model using Gaussian models. So for exact modeling, they wanted actually these non-Gaussian models, even non-stationary models, non-linear models, etc. And it was actually, the first work was actually by Gower and Lewis in 1980 on non-Gaussian models, and it was on exponential and gamma marginals. And they considered simply starting with the first order autoregressive model given by xn equal to rho xn minus 1 plus epsilon n, where rho lies between minus 1 and plus 1, where sequence epsilon is a sequence of EED random variables called innovations. So they consider the form of the innovation sequence.
Please check the voice. Lots of echo is coming, sir. Are there 2 or more devices?
Whether it is from here or...
There is some disturbance.
Or reduce the sound of the audio of the lab.
Let me see.
Speaker, yeah. Reduce the volume of the speaker. That also will.
Okay. Now we can hear.
Now also that echo is here.
No, it is again creating problems. Here.
What you have to do is switch
if there is any electronic device nearby.
If there is a mobile laptop,
mobile and laptop.
Yeah, that you mute the other device or sound, minimize the sound. The other device, mute the other device only. Your device you have to. Okay, sir. Try to share it once again. The presentation disappears.
Sir, now you may present your paper.
Yes, sir. Hello, Joseph.
Hello. Please come.
Hello, Joseph. അവിടെ സാറേ കൂട്ടത്തിലെ ഈ മൊബൈലിൽ ഏതെങ്കിലും ഓൺ ചെയ്ത് വെച്ചിട്ടുണ്ടോ ഈ പ്രസന്റേഷൻ അല്ലെ മറ്റേതെങ്കിലും 2 ലാപ്ടോപ്പ് വെച്ചിട്ടുണ്ടോ? ഇപ്പൊ കേൾക്കാം. ഒന്നുകൂടെ now we can check.
Yes sir, we can see. Thank you.
Okay, please continue.
Now it is.
Yes sir, it is clear now.
We can see the slide.
It is all right, sir. Please continue.
Okay. So we were concerned with the first order autoregressive model. Now it is clear? You can hear?
Yes, sir.
Now it is clear.
Okay. Now coming to self-decomposability, actually, as far as the structure of the model or as far as the innovation structure of the model is concerned, so actually we want some particular distributions only. So that was actually the main concern for considering the self-decomposability. As far as this first order model xn equal to rho xn minus 1 plus epsilon is concerned, so we were concerned with the model, so the probability structure behind that. So for that, actually, we considered the concept of self-decomposability. It was actually introduced by Stutel in Stutel and very early days, 1960s. And so this definition of self-decomposability is this one. So if you are having a characteristic function phi, then it is said to be self-decomposable if for every rho in 0, 1, there exists a characteristic function phi p such that phi t is equal to phi x of rho t into phi rho t. So that is actually a product of two characteristic functions, or actually the random variable becomes the sum. Then coming to this one, so this was actually the first consideration. And later on, Sandesh and Sandhya in 2005 noted that an IR1 model can be defined in a wider class. That is actually they have extended this to something called semi-self-decomposability. In semi-self-decomposability, we are having a characteristic function phi is said to be semi-self-decomposable if for some 0 less than rho less than 1, there exists a characteristic function phi p such that phi t is equal to phi x of rho t into phi rho t. That is actually semi-self-decomposability. Now we will be coming to semi-self-decomposability. So when, as far as the self-decomposability is concerned, it is possible, it should be valid for every value of rho lying between 0 and 1. When it comes to semi-self-decomposability, it is only for at least for some values only that much. So when you come to the exponential case, we have phi xt equal to lambda by lambda minus it as the characteristic function. We can write phi epsilon t as lambda minus I rho t divided by lambda minus it, and rho will be, and that will be reducing to rho plus 1 minus rho into lambda by lambda minus it. This actually shows that this innovation epsilon is a mixture of two random variables, and that will be having this structure. This gives the inversion structure as epsilon n equal to 0 with the probability rho, and some exponential random variable like en with the probability 1 minus rho. So that our stochastic process xn or time series xn can be written as, so rho xn minus 1 plus 0, that is actually with the probability rho, then rho xn minus 1 plus epsilon and en with the probability 1 minus rho. So that is actually the advantage. So this here itself, some non-linearity comes in. So we are having two components. One component equal to rho into xn minus 1 with the probability rho, and the other component is actually rho xn minus 1 plus en with the probability 1 minus rho. So this was actually the first non-Gaussian Waterloo model considered in time series analysis, and this was due to Gower and Lewis, and they refer to it as EAR1, that is exponential Waterloo model of order 1. Then comes actually the theoretical justification, etc., were noted or established by Bonderson in 1981, and they noted that the first order IR1 model can be defined only for self-decomposable random variables, and this was a fundamental theoretical solution to non-Gaussian innovations or non-Gaussian IR1 modeling. And later in 1981, so just immediately after next year, Lawrence and Lewis modified the structure. So certainly there were some inherent problems with the structure we have developed. Then for them the model was actually xn equal to epsilon n with the probability alpha, and rho xn minus 1 plus epsilon n with the probability 1 minus alpha. And they refer to this as new exponentially autoregressive or new exponential IR1 model or any IR1 model. And here you can see, so that there is a component epsilon n with the probability alpha, and the other component is actually the autoregressive structure rho xn minus 1 plus epsilon n with the probability 1 minus alpha. And this is actually having some realistic meaning. So this occurs when in certain situations this epsilon n itself is having the major role. So in the case of, say, in India, many of the rivers are dry during actually the most of the time. So in such a case, another situation is actually some economic, so some financial situations, some financial data, so where the situation is handled by innovations alone. That is actually some major problems in the economy. So such situations, so you can think of this type of situations. So another is actually rainfall. So when you are having heavy rains, just something which we have observed in Mumbai, then in Kerala during last 2 years, and then in Chennai, etc. So occasionally on one day or 1 week, there is huge rain. So that is actually epsilon is having the major role in that case. Otherwise, it is for following an auto-reduced structure. So this one is actually the model proposed by Lawrence and Lewis, and they considered. So when you come to this one, so if you consider the characteristic function, that is the model is rewritten in terms of characteristic function, then you will be getting phi xmt equal to phi epsilon t into alpha plus 1 minus alpha phi xn minus 1 rho t. And if you assume stationarity, that is something which is free of n, then you will be getting phi xt equal to phi epsilon t into alpha plus 1 minus alpha into phi x rho t. So this was actually a generalization of the usual auto-reduced structure. This actually lead to a generalization of the self-decomposability structure also. And Kosubowski and Podgorski actually referred to these distributions as randomly self-decomposable distributions. So they have extended the concept of self-decomposability, and when alpha equal to 0, this actually reduces to self-decomposability. And myself, Yosan Pillai, in 1993, we considered the role of geometrically infinitely divisible distributions in auto-reduced model. And there we considered xn equal to a structure epsilon n with probability alpha, and xn minus 1 plus epsilon n with probability 1 minus alpha. This is a generalization of our usual random walk model. So in the usual random walk model, we are having xn equal to xn minus 1 plus epsilon n. So here there is an additional component, that is epsilon n, that is innovation. So having some major role with probability alpha. And in that case also, if you proceed in terms of rewrite in terms of characteristic function and assume stationarity, then you will be getting phi xt equal to phi epsilon t into alpha plus 1 minus alpha phi xt. This is actually the condition for geometrically infinitely divisible random variables. And you can see that this also is a special case of random self-decomposability. Now we will be coming to the concept of geometric infinite divisibility. Some people may not know. So here actually we are having a random variable x is said to be geometrically infinitely divisible if for every row, every p in 0, 1, there is a sequence independent and identically distributed sequence of random variables x1 is to etc. such that x is a random sum. So that is sigma I equal to 1 to nu p xi. So that is actually a random sum. Here nu p that follows a geometric distribution. So probability nu p equal to k, that is p into 1 minus p raised to k minus 1. That is a truncated geometric, that is from k equal to 1, 2, 3, etc. it is taking. And here x and this nu are independent random variables also. So now a criterion for identifying geometric infinite divisibility was introduced by Klebanov. Actually, this concept was introduced by Klebanov, and my professor Aaron Pillai and his associates also had detailed work on geometric infinite divisibility, and this was actually a theorem that is actually a random variable x with a characteristic function phi t is geometrically infinitely divisible if and only if it can be written as psi t equal to exponential 1 minus 1 by phi t. So if that is infinitely divisible, then you can say it is the original characteristic function is geometrically infinitely divisible. So these are actually the result. Pillai and Sandhya in 1990 in a paper which appeared in Advances of Probability and Advances in Probability. So they proved that the class of distributions with monotone, complete monotone derivative is a proper subclass of geometrically infinitely divisible distributions also. So then comes random self-decomposability. So now coming to random self-decomposability, so we are having this structure actually. So psi t is equal to psi of psi pt into p plus 1 minus p into psi ct. And this actually corresponds to the auto-reduced structure of the form xn equal to epsilon n with probability p, then epsilon n plus c xn minus 1 with the probability 1 minus p. So which is the NEIR1 model which was introduced by Lawrence and Lewis. And now coming to this one, this you can rewrite in terms of random variables as x is equal to some c into an indicator function ix plus xcp. So where x and xcp are random variables with the character functions psi and psi cp. So where I is a Bernoulli random variable. So having this I is equal to 1 with the probability 1 minus p, and I is equal to 0 with the probability p. And these x and xp are mutually independent random variables also. So when you consider c equal to 0 or p equal to 1, we are getting the different situations. When p equal to 0, it actually reduces to psi t equal to psi ct into psi t c. So which is actually self-decomposability. So that means x you can write as x is identically distributed as some cx plus some component xc. And when c equal to 1, we are getting psi t equal to psi pt into p plus 1 minus p psi t. So which actually reduces to, in terms of random variables, you can rewrite as x is identically distributed as x plus some xp. So which is actually geometric infinite divisibility. So in terms of character functions, we can write it as psi t equal to p psi pt my 1 minus p into psi pt. So showing that for each p in 0, 1, the random variable, the random variable x with character function psi can be decomposed into a random sum of the form x equal to xp1 plus xp2 plus xp np. And this is actually, so what you can see is this random self-decomposability is a generalization of, or this actually unifies self-decomposability and geometric infinite divisibility to the same platform, you can say. So when you are having c equal to 1, you are getting actually geometric infinite divisibility, and when p equal to 1, p equal to 1, we are getting self-decomposability. And then coming to a stationary stochastic process is well defined if and only if the distribution of x is randomly self-decomposable. So you can define a stochastic process of this form if and only if your random variable x belongs to the random self-decomposable class. When p equal to 0, it actually reduces to the standard order structure. When c equal to 1, it reduces to xn equal to epsilon n with the probability p, epsilon with xn minus 1 with the probability 1 minus p, and then certainly some modifications you can think of. So instead of addition, if you write minification, so minimum of rho xn minus 1 epsilon n and xn equal to epsilon n. So this actually reduces. So this was actually a generalization of the model introduced by Lewis and Mackenzie in 1991 in a paper which appeared in the Journal of Applied Probability. So this also gives you a generalization of our usual minification model. So here also we are having the random component epsilon n, that is the innovation component epsilon n alone with the probability p. Then another is actually the maximum or max random self-decomposability, where xn is equal to epsilon n with the probability p, and maximum of rho xn minus 1 epsilon n with the probability 1 minus p. So this minification process and maxification process, these are actually used in extreme value theory for modeling hydrological situations and so on. Then coming to the min geometric infinite divisibility. So there also you can think of xn equal to epsilon n with the probability p and min xn minus 1 epsilon n with the probability 1 minus p. So this actually lead to min geometric infinite divisibility. Similarly, you are having max geometric infinite divisibility when minimum is replaced by maximum. Now I am coming to some applications. So here we are considering multivariate linear distribution. So starting with that is a generalization of the multivariate Laplace distribution, multivariate alpha Laplace distribution. Actually, linear distribution is also referred to as alpha Laplace distribution, and alpha Laplace distribution was studied in detail by our Professor R.N. Pillai, and many of us collaborated with that. The characteristic function of a multivariate linear distribution is having this general structure psi t equal to 1 by 1 plus t transpose sigma t the whole raised to alpha by 2, where t is a vector and sigma, that is the dispersion matrix, a positive definite dispersion matrix of order p, and alpha belongs to the range 0 to 2. And when we are having the univariate case, it is actually Laplace. The situations are 1 by 1 plus sigma square p square the whole raised to alpha by 2, or that is actually 1 by 1 plus sigma into modulus of t raised to alpha, which is the alpha Laplace distribution. Then when alpha equal to 2, it actually reduces to the Laplace distribution having characteristic function 1 by 1 plus sigma 1 by 1 plus sigma into t square, or sigma square into t square. So then, as far as the multivariate probability distribution is concerned, this I have taken from the literature on. So this you can rewrite in terms of some Bessel function and so on. So now coming to multivariate unique distribution. So there you can think of this one as a random sum also. So y equal to 1 by n raised to alpha x1 plus x2 plus x2. That also is a multivariate symmetric stable distribution. So that is having the loss of attraction, etc. So let S be a multivariate stable random variable vector with the characteristic function exponential minus t dash sigma t the whole raised to alpha by 2, where sigma is a positive definite matrix of rank n. And let E be a univariate gamma random variable with parameters nu and s, and G are independently distributed. Then the random vector you can write x is equal to g raised to 1 by alpha into s. And this can be used for generating this type of random variables, these linear random variables, multivariate random variables, and so on. So multivariate linear random variables you can generate using gamma and multivariate stable random variables. So univariate linear you can generate using gamma and univariate stable random variable. Now, the parameter estimation is a difficult task. So usually we have to make use of characteristic functions. So standard parameter estimation techniques are not applicable to linear distribution. And say Anderson and Arnold in 1993 considered the estimation method for linear parameter, and they consider a minimization technique. Here they are considering IL and alpha equal to supremum over T modulus of FNT minus FT, absolute value of FNT minus FT, where FNT denotes the sample characteristic function. So the difference between the sample characteristic function and the original characteristic function is minimized actually. So that is how, so that estimation actually needs computation, etc. So to estimate the parameters of the multivariate linear distribution, so we will be considering the empirical characteristic function psi cap equal to 1 by n, psi hat t equal to 1 by n, sigma j equal to 1 to n, exponential I into t transpose into yj, and Anderson 1992 gives some technique for that, and Press also modified some or proved that the estimates obtained are consistent. Now we will be coming to the multivariate linear process, where you can write, so I am considering the linear structure, a special case. So here xn equal to a into xn minus 1 plus epsilon n. Here xn and xn minus 1 and epsilon are multivariate in structure. So we will be coming to the special case later. And there also you can obtain the characteristic function of a multivariate random variable suspected value of e raised to minus t transpose into x. And making use of that, you can proceed, and you will be getting the innovation structure for epsilon. So psi epsilon t is rewritten as a raised to alpha plus 1 minus a raised to alpha divided into 1 by 1 plus. And that will give you the innovation structure as epsilon n equal to 0 with the probability, 0 vector with the probability a raised to alpha, and a linear random variable with the probability 1 minus a raised to alpha. And an AR1 process with structure 22 is stationary if and only if you are having this innovation structure actually. And you can consider sums, distribution of sums of random variables are something like waiting times, etc. So that you can obtain, and you will be getting join distribution. So join distribution is important. We want to know whether it is time reversible. Time reversible means whether the forward movement as well as the backward movement are identical function. So phi xn plus 1 t, t1, t2, that is not, that is phi xn plus 1 t1, t2, that is not equal to phi xn plus 1 t2, t1. So if you interchange, so it is not identical. That is actually time irreversibility. So the process is not time reversible. So if the process is time reversible, it is very easy. It is a very good property actually. So in particular, we are coming to the geometric infinite divisible structure, that is xn equal to epsilon n with probability p, xn minus 1 plus epsilon n with probability 1 minus p. Then we will be getting psi xn minus 1 or psi xt equal to p into psi epsilon t plus 1 minus p into psi xt into psi epsilon t. And that will give you psi epsilon t equal to 1 by 1 plus p into t transpose sigma t, the whole raised to alpha by 2. That is for the multivariate linear situation. Now, here we introduce the multivariate geometric generalized linear distribution. And so the geometric geometric generalized linear, that is actually coming from some
So your voice is not coming.
Jose sir, it seems your microphone is switched off. Please.
No voice, yes. Joe, sir, can you hear us? You are not audible, sir.
Jose sir, you are not audible. Dr. Jose.
Please switch on your mic, sir. Joe, sir, please see that your mic is not mute.
Okay. No problem. So here we are considering a data consisting of 2086 observations on the daily exchange rate of US dollar to Indian rupees. And the log returns values are considered. And from the data, the summary statistics obtained are as follows. So we have considered the data, we have made the log transform data. And certainly the histogram shows it is something like normal or linear or Laplace. So we have considered the case and we have obtained the mean values. Then the estimates of the parameters were obtained using the methodology, and we have obtained the estimates. And we have made use of the generalized moment method actually. So that actually leads to the estimates actually. So here in this case we have observed that the linear distribution, that is the univariate linear distribution, is more suitable. And for that actually we developed an auto-regressive model and we obtained these estimates actually. And
Sir, 1 more minute to wrap up, sir.
Okay, I will finish it. Applications, the models you can consider for modeling multivariate time series as well as univariate time series on currency rate exchanges and so on. So in biological and biostatistical modeling, in some other works, we have considered the applications in gene sequence microarray gene sequence modeling. In the case of stock market analysis and option pricing, also the stable distribution was primarily used, but this Laplacian distribution is widely used nowadays actually. And this linear distribution is another alternative, and we can make use of this. Kosubowski and others have made use of stable distribution for use for modeling portfolio data, this financial data, exchange data, and so on. And conclusion, so we have just considered self-decomposability, geometric indivisibility. Actually, random self-decomposability was introduced by Professor Thomas Kosubowski in 2010. And these are my references. Thank you. Thank you.
Thank you so much, sir. And it has really been a very elaborate and very informative presentation on random self-decomposability and its application in autoregressive time series modeling. And now the floor is open for the questions, comments, suggestions from the audience.
Hello. Hello. I would like to make a couple of comments. You had referred to my paper with Sandhya in 2005 that showed that all the AR1 models can be generated not necessarily by class distributions. Okay.
Okay, sir.
In fact, there is a correction to our paper that we had published in 2007. Okay. It says that even finite range distributions can be used to generate AR1 models. Okay. And finally,
that also I have seen.
Finally, Yeah, that was in 2007. Finally, myself and Bowser have characterized the class of distributions because it is known as alpha decomposable distributions by Professor Lowe. Lowe's book we are all familiar with.
Okay.
It is alpha decomposable distributions that characterizes the marginals of stationary AR1 models. Okay.
Sandhya and Satish have contributed immensely. So here is actually.
I was just mentioning some corrections. That's all. And one more thing. The idea of random self-decomposability by Kozubovsky, that also we have generalized to some other structures.
Okay.
Other than geometric structure. Okay.
Okay, sir.
Thank you, sir. Thank you for the nice presentation.
Thank you very much for Satish. So for your contributions, etc. So I am aware of it. So all of us are students of Professor R.N. Pillai. So the Sandhya, Satish, then Jaykumar, myself, and many others made use of these works, and we generalized these concepts of geometric incompressibility, self-decomposability, random self-decomposability, then geometric infinitesimality, and so on. So so many. So we are grateful to. So any more questions? Any more questions? So thank you, Madam Sheila.
Thank you, sir. And if there are any more questions, I think we can take them up from the audiences.
So thank you very much, Dr. Sheila and Dr. Yadav, for chairing this session and helping. And
thank you, sir. Thank you, sir.
I'm grateful to Dr. Satish for giving this occasion to remember my professor, to pay tribute to my professor, Professor Kalyanaraman sir also, I have seen. So he had also contributed, he had also kept us in our research works. I remember with gratitude. Thank you, sir.
Thank you, sir.
So let us thank the speaker. And if there are no more questions from the audience, so we are really honored to have the enlightened speakers in this specially invited session of Wsta 2021. And all the speakers, including Dr. Deepesh Bhati from Central University of Rajasthan, Professor Jay Kumar, and Professor Josh, they all have been wonderfully very informative and very application-oriented presentations, and it was very exhaustive as well. So we could see it was the whole book of yours on the topics. So thank you so much, and let us give a big applause for all the speakers. Thank you. And Dr. Yadav, you want to add something?
Thank you so much, because I am not the right person to say anything, because I think I am the most junior person here. So I just want to say thanks and mentoring us and for showing the path of research, which will definitely continue for our young generation. It's really a great motivation. And thanks to Satish sir for giving us opportunity to come on this platform and to hear the learned speakers. So thank you, sir. Thank you.
So yes, indeed, it is a time to congratulate Professor Satish Kumar and his team for conducting this webinar in such a successful manner, despite of all odds. And this is, I think, the great quality of Professor Kumar and all his students, team, and colleagues, that they are always rising up to the occasion despite of all the challenges, and they are bringing us on the same platform to discuss so many latest updates in statistics and its application. So thank you so much, Dr. Satish Kumar, for giving us an opportunity to chair the session and to listen the enlightened speakers and be a part of this great grand mega event. So thank you each and everyone, and thank you.
Just to say something. In 2015, I remember when we have conducted the ISPS conference, I was just a research scholar of madam, and Dr. Satish were the guest in our. So really for remembering us. And I just want to mention one thing, that all the achievements today I'm just because of my teacher, Professor Sheila ma'am, and I'm really want to be her student. And now I'm in front of you just because of her motivation, because it's a journey from student to your faculty. So thank you, ma'am, for your blessings.
Thank you, Dharmendra, and we are really proud of all our students. Thank you so much, Dr. 2021.
Thank you, sir.
So over to the organizers.
Thank you.
Satish, sir, you are muted. Please unmute yourself.
Sorry, extremely sorry. Sorry. Thank you, Dr. Divishwati, Professor Jayakumar, and Professor K.K. Josh for your wonderful talks, and Professor Sheila Mishra and Dr. Dharmendra Kumar Yadav for nicely chairing this session in a very beautiful way. In fact, Professor Jayakumar and Professor Josh we are always proud of them. They are our alumni, as well as Kerala University is always proud of these statisticians in our area. In fact, I utilize this occasion to extend our gratitude on behalf of Department of Statistics, University of Kerala, as well as ISPS and Kerala Statistical Association, KSA, for extending our heartfelt gratitude to each one of these speakers. Once again, Dr. Divishwati, Professor Jayakumar, Professor Josh, and Professor Sheila Mishra, and Dr. Yadav. Thank you all. Thank you so much for your support to our.
Thank you. And stay safe. Thank you.
Yeah, thank you. In fact, our next session will start at in the same platform at 1:50 p.m. So we have a lunch break time, and at 1:50, so everyone should please try to assemble here at 1:45 itself. And at 2 p.m. there is the parallel session is there. That link also already there in our website and already sent to all. In fact, let us have a break for our lunch and meet sharp. I request everyone to assemble for this session, TS 33, at 1:45 itself, and TS 33A at 1:40 or 1:55 at that platform. Okay, thank you all. Thank you so much, and I'm waiting for your. Now this is a time. Let us start. Others will join in the meantime.
Okay,
that's better. Okay, let us start at the right time itself. Yeah.
Okay, thank you, Satish.
Oh, yeah. Shall just I invite you? Now in this session we have 4 speakers, and to chair this session we have Professor Jayakumar sir. Jayakumar is here, and also Dr. Divishwati is here to support the chair as the co-chair of this session. Dr. Divishwati is a very active researcher. Is presently working in the Department of Statistics of Rajasthan Central University.
Yes.
And he is in fact very active in areas of extreme value theory and its applications, actuarial science, statistical inference, distribution theory, etc. I think so.
Yes.
He has several credits. I'm not extending because in the previous session we have detailed about him. Or otherwise, his details are there in the webinar website. I invite Divishwati to introduce Professor Jayakumar and thereby support Jayakumar to run this session in a smooth way. Whatever you have to give, please.
Okay.
Thank you.
Good afternoon to all of you. I personally would like to thank Professor Satish for giving me an opportunity to co-chair and support Professor K. Jayakumar for this session. Already Dr. Dharmesh in the previous session, Dharmesh Yadav, he have introduced him, but I have personally want to say a few words for Professor Jayakumar, because I myself very frequently and continuously follow his research and his publications. So Professor Jayakumar is a professor and head of the department of University of Calicut, and he has completed his master's and PhD degree from University of Kerala, and postdoctoral from Cusat, Dalhousie University, Canada, Memorial University, Newfoundland. He works in the area of distribution theory, time series forecasting, statistical inference, stochastic modeling, probability theory. Very recently, I just wanted to say this word to Professor Jayakumar. His work on Mittag-Leffler distribution, discrete Mittag-Leffler distribution with R.N. Pillai is very much useful, appreciated by the actuarial community. And in last 2 years, recently in 2020 and 2021, a good number of publications are available in the field of actuarial science, and they have published in very renowned journal like Scandinavian Actuarial Journal, Insurance Mathematics Economics. So whatever work he has pursued during his research activity and during his PhD, that work is now getting so much attention of the actuaries in modeling the claim frequency and modeling various insurance related phenomena. So I congratulate sir, and then I on my own behalf, I request you to chair this session, and over to you, sir. Thank you.
Thank you, Divesh Bhatti. Thank you, Satish. So now our first speaker in the session is, there are 4 speakers in this session. The speakers are Priyaranjan Dash, Kavya Rashu, Vittal, and Ashokan Varier. Professor Priyaranjan Dash is presenting on the topic, a class of predictive estimators of finite population mean for a 2-stage sampling procedure using 2 auxiliary variables. Dr. Das, please.
Thank you, sir. Thank you, sir, Professor Jayakumar, sir, Honorable Chair. Thank you, Dipesh Bhatti, sir. I am thankful to all of you. I am thankful to Professor Satish Kumar, sir, for giving me a scope to present my work in this platform. Now, sir, is the screen visible?
Yes, sir, it is visible.
Okay, it's coming.
Today, I want to present on a class of predictive estimators of finite population mean for a 2-stage sampling procedure using 2 auxiliary variables. Here we consider the case of 2-stage sampling. We consider a population with n first-stage units, and we denote it by capital U, 1, 2, 3, 4 up to n. And the ith unit of the population UI contains mi second-stage units, so that the total number of units in the whole population we denote it as m, capital M. And our survey variable is y, and auxiliary variable x and z. And yij, it is the value of the study variable for the jth unit, second stage unit of ui, ith first stage unit. Similarly, we can define for the auxiliary variable x and z. Now, for the ith first stage unit, we define the population mean as yi bar, and overall population mean, that is y bar, capital Y bar. And we assume that in both these stages, we select the sample following simple random sampling without replacement scheme. So first we select n first stage units from the population. Then from the selected first stage units, we select each of the selected first stage unit, we select mi second stage units. So for the sample, we denote the sample mean x yi bar 1 by this is small mi j equal to small mi yij, and overall sample mean ui yi bar, and we define x bar dash and z bar dash accordingly for the sample. Now here we are defining a function of small y bar and small x bar. This is according to the Srivastav 1980, the class of estimators of y bar. He defined the class of estimator as a function of sample means y bar and x bar, satisfying some conditions, that is function of capital Y bar capital X bar is capital Y bar, that is the population mean of the study variable, and the function gamma is such that it satisfies the two regularity conditions. The first one, the sample point y bar x bar, it assumes it is a values in a bounded and closed convex subset R square, which contains the point y bar x bar, that is the population mean, and it is continuous, having first and second order partial derivatives, and again these first order and second order partial derivatives are continuous in two-dimensional space R square. Now our classical ratio estimator is, we denote YR bar as small y bar into capital X bar by small x bar. Similarly, we define classical product estimator and the classical regression estimator YRG, and all these estimators have their own limitation for their use. Just like classical ratio estimator can only be used when there is a high degree of positive correlation between the study variable and the auxiliary variable. Similarly, the classical product estimator, it can be used when there is a very high degree of negative correlation between the study variable and the auxiliary variable. But in these cases, our regression line of y on x passes through origin, then these two estimators becomes optimum. But when the regression line of y on x does not pass through origin, we use our regression estimator, that is given by y bar minus beta byx into small x bar minus capital X bar, where beta byx is the regression coefficient of y on x, which is defined by this. Now, in a two-stage sampling plan, it is usually felt that the efficiency of an estimator depends upon how well the auxiliary information that we utilize at different stages. That means the auxiliary information can be used in either in the first stage or in second stage or in both. And the objective of using this auxiliary information is to improve the precision of the estimator. Now with this spirit, Sahu and Pandit in 97, they considered a class of estimator. They considered the weighted mean for each of the selected second stage units. And it is the functional form is like this: mu 1 by n, I belongs to S, that is the sample, ui, these are the weights depending upon the size of the proportionate size of the first stage unit. Then it is a function of yi bar and xi bar, and they used this x bar dash. So that means they take the weighted functional form. Here we have defined two functions, mu and mu I, and this mu I is defined for each of the selected second stage units, and mu is for overall. So here both these functions, mu and mu I, they satisfy all the regularity conditions in R square. And particularly here, this type of estimators in which they have chained the estimators for different selected fastest units. So these type of estimators are called as the class of chain type estimators. So we can define some particular cases of these estimators as Smith ratio estimator. This is also a particular case of this class chain type estimator. Murthy, Sahu and Swain, they have defined this a particular class of this estimator. Sahu and Swain, it is chain product estimator, and Sahu, he has defined also a class of this. So now Sahu and Sahu in 2003 they have developed a class of estimator in which they take this functional form. Again, this is chain type, and here the regularity conditions are satisfied in the same way. Now different estimators of this class can be proposed like this. We denote this YRSS P. This is in the product form because it is Y and Z, Yi bar and Zi bar. This is the product of the mean of the study variable with auxiliary variable Z, and the ratio of x bar dash by x bar, another auxiliary variable, is taken outside. And this is the regression. All these estimators are chain type estimators. Now, in all these cases, classical estimators, we have their limitations in the use. Here we have proposed the predictive approach designed by Basu in 1971 and subsequently by Smith in 76. So because what happens when you select a sample and try to infer on the basis of the sample, our population is divided into two distinct categories. One is the some selected units, other is the non-selected units. So in predictive approach, what we do, on the basis of this sample, we want to predict what is the value of the characteristic for the non-selected units. So that is the approach. So here we take the first auxiliary variable x, we have the information on x bar, that is the overall population mean of the variable x, as well as the information on xi bar, the mean of the population for each of the fastest units. Now the second auxiliary variable z, we assume that z bar, it is overall population mean, it is also known, and zi bar, this is also known for selected units. Now as a particular case of this, as an example we can consider in a crop survey. Crop survey we conduct, that is to estimate the yield of a certain crop in a district. We consider different blocks as the fastest units. These are the clusters of villages, and villages as the second stage units. So our study variable is y is yield of the crop, x we can take cultivated area, z in the area under the crop. So the information on x and z can be easily available from the district records. Also we can get the information the values of xi bar, capital Xy bar and Zi bar for the selected units. So the assumptions, these assumptions are readily satisfied. So now what is the objective of this predictive estimation? Here we have the population. It is divided into different, it has different fastest units. So here the figures though appear dark, they are the selected fastest units, and from the selected fastest units we select the second stage units. So S bar, capital S bar, we write the fastest units, those who are not selected, and small si bar, the second stage units which are not selected within the selected fastest unit. So we design the estimator like this: 1 by m. M is the total number of units in the entire population. We take the summation over I belongs to S for the sample units. Here we divide it into two parts. So I belongs to S and I belongs to S bar. So our overall population mean 1 by the population size, it is now divided into two parts. One is I belongs to S, I belongs to S bar. So this capital A with S bar. This is for the selected units of the fastest units, and this is for the non-selected fastest units. Then again within the selected fastest units, we divide into again two parts. The first part is the selected second stage units, J belongs to small si. And the second part, J belongs to small si bar. So non-selected second stage units. So in this way, we divide the overall population mean into these first two parts. Again, it is two parts. So basing upon this idea, we design our estimator. So here, the population mean y bar, that is equal to 1 by capital M. This I belongs to S. This is I belongs to S means selected units of the sum fastest units, and this is non-selected fastest units. So mi yi bar. Again here the selected second stage units, and this part non-selected second stage units. So our population mean takes in this form, and our objective is to predict this second part and this second part, these two parts. So that is why it is the predictive estimator. So here we can, on simplification, we can write this in the form 1 by m. I belongs to S. Mi, this is yi bar. This can be obtained information from the sample, and mi minus mi yi r bar, we cannot get information on this and this. So here n minus n, this is the non-selected, the number of non-selected fastest units, n minus n yr bar equal to this much. So in order to estimate this population mean y bar, our problem is to predict the quantities, this yr bar and here yir bar, these two parts, the non-selected parts we want to predict from the sample data. Now the two-stage sampling, the prediction theory is described first by Scott and Smith in 1969, then subsequently it was described by Chaudhary and Stenger, Bolfarin and Jacks in 1992, and these predictions are based on either on the distributional forms or the assumed models. However, the classical inference on these predictions approach is limited, that we are discussing here. We denote capital Ti and T with the implied predictors of yir bar and yr bar respectively. Then a predictor of overall population mean can be represented in this form. This is the selected sample. This can be known from once we select the sample. This Ti and Ti bar, these are two implied predictors. We are just using it in place of yr bar and y bar. Now if the Si equal to Ui, that means all the fastest units are selected and all the second stage units are selected from the fastest units, that mi, small mi equal to capital Mi and small n equal to capital N, then this tends to capital Y bar. That is our target population. So this is the idea behind the predicting sample. So there is no addition, in case no additional information or auxiliary information is available, we can consider this simply Ti equal to yi bar and capital T equal to y bar. The simple means of the study variable for the ith selected fastest unit and ith selected second stage unit and y bar overall sample mean. So in this case, in no information case, suppose X and Z information are not available, we can consider an estimate of the overall population mean as capital Y bar. So we try to estimate Ti and T by exploring the values of X and Z. So we define a class of estimators using X and Z under the Srivastava regularity conditions that we have already defined. So class of estimator, it is for SI, the class of estimator or yi bar that we define, it is a function of small yi bar, that is mean of the units of the selected second stage units from the ith selected first stage unit. Similarly, a small xi bar, zi bar, this is the mean of the population mean of the z variable for the ith first stage unit. Capital XIR bar and capital ZIR bar, I belongs to S. That is the sample. So these are the population means of the units, those who are selected, for those selected first stage units. So if we replace these sample values by the corresponding population values, now this functional form of this becomes equal to yi bar. So here yi bar satisfies Srivastava regularity condition, and they are treated as the estimators of Ti and TIR bar, estimators of YIR bar and YI bar. Now, for a given sample, this capital N minus N, this is the proper number of non-selected first stage units. So N minus N, XR bar, XR belongs to these non-selected units. So N minus N XR bar, that is equal to summation I belongs to S bar. S bar means these units which are not selected, that is UI XI bar. And lambda Y bar X bar dash XR bar, these are the known functions of small y bar X bar dash and XR bar, such that lambda of these population values X bar, Y bar, X bar and X bar, this is equal to capital Y bar. It also admitted all the regularity condition in three-dimensional Euclidean space R3. Now, availing the auxiliary information on X at the level of first stage units, we can define a class of estimator of Y bar, the overall population mean, as this function of small y bar, X bar dash and XR bar. And for the ith first stage unit, we can define Ti, that is a function of yi bar, xi bar, zi bar, xir bar and zir bar. And T equal to function of y bar, x bar dash and xr bar. Here we define the class of predictive estimators as 1 by m summation I belongs to S mi y bar. This is for the part which we study. That means this is for the part we select the second stage sample. So this part can be known from after selecting the sample, second stage sample. And this is mi and mi. This is non-selected part. Non-selected part within the ith selected units. So we use an estimator here. It is a function of yi bar, xi bar, that is function lambda. And this is non-selected first stage units. This is n minus n by n. Why we take n minus n by n? So small capital N minus small n. This is the number of non-selected units, first stage units. So n by n minus n by n, it is a proportion of non-selected units, first stage units. So now to derive the asymptotic variance, we expand the functions lambda I and lambda about their points, mean points. So yi bar, xi bar, zi bar, xi bar, zi, and y bar, x bar and x bar dash. We take the Taylor series approximation and obtain these equations 5 and 6 for lambda I and lambda. And here lambda I k equal to 1, 2, 3, 4, lambda I1, lambda I2, lambda I3, lambda I4, and lambda 1 are the first order derivatives of lambda I, with respect to small yi bar, small xi bar, small zi bar, xir bar and zir bar. And lambda t equal to 0, 1, 2 are the partial derivatives of lambda with respect to y bar, x bar dash and xr bar. Now we note, if we obtain the partial derivatives, we can see lambda I 0 equal to 1, lambda I equal 1 equal to minus lambda I3, lambda I2 equal to minus lambda I4, and lambda 0 equal to 1, lambda 1 equal to minus lambda 2. And these are the values xi r bar dash equal to mi xi bar minus small mi small xi bar divided by mi minus mi. This is the not. Similarly, zi bar and xr bar we define non-selected fastest units like this. Now on simplification with these equations, we can get an estimate of the population mean y bar as this: y bar plus f by n summation I belongs to S sample ui lambda I1 into this, lambda I2 into this, lambda 1. Now we have, this is a function, this function only unknowns lambda I1, lambda I2 and lambda 1. These are constants, 3 constants. These are generally functions of the sample values and the population values, known population values for the auxiliary variables. So that we can define the variance as this. The variance, this is variance of y bar, variance of the simple mean estimator in no information case, that is simple random sampling without replacement scheme. And these are the covariance terms. So here each of these terms are evaluated like this. So variance of small y bar is this. This is for the variance of the simple mean estimator using two-stage sampling scheme, SBY square and SI square as the defined here. Now this is the variance term, and the covariance term between y and x is this 1 by n and I equal to 1 to n. Now using all these values, we can get the variance of the estimator is takes this form. Now, since our objective is to find an estimator with the maximum precision, we minimize the variance with respect to lambda I, lambda 1, lambda 2, lambda I1, lambda I2, and this variance is minimized when lambda I1 equal to minus 1 by f, beta Iyx minus beta Iyz, beta Izx by 1 minus beta Izx, beta Ixz. These are the regression coefficients. F is the sampling fraction, and lambda I2 is like this. We denote these optimum values as lambda I1 O, lambda I2. These are the optimum values, and lambda 1 equal to minus beta Byx. This is the regression coefficient of y and x for the overall population, where these are the regression coefficients beta Izx and beta Ixz.
Professor Dash, only 5 minutes more.
Okay, sir. Thank you. I am trying to. Now, using these optimum values, we get the minimum variance as this. And this minimum variance takes the value of this multiple correlation coefficient, and the optimum estimator, that is MBB estimator of this class is this yi over g bar lambda. This is the MBB estimator in this class. So now we consider some particular cases depending upon the particular values of the constants, where lambda I1, lambda I2 and lambda 1. So these are in no information case. This is simple mean, this is ratio type estimator, regression type estimator, product type estimator. So all these are belongs to the particular members of the proposed class. Now here the regression type estimator, this is in the chain form. This is also another class. This is a particular class of estimator proposed by us. Now, all these are some particular cases. Now, these are the variances of these estimators. Now, in order to compare these variances both theoretically, we have considered that our proposed class is conditionally better, performs better than other, and these are the conditions, and how well these conditions are satisfied, we consider some real life examples. We consider two different populations. So in this paper, since ratio method of estimation is used in case of positive correlation, and product estimator is used in case of the negative correlation case, and we take two populations where the study variable and auxiliary variable are positively correlated. So we compare here only ratio type estimators. So this is the comparison. And here one thing we can specify here, the performance of our estimator is better than all other estimators, and this condition is to be satisfied. Here one important factor is this 1 minus f. This ratio should be greater than or equal to 1 minus f, where f is the sampling fraction. So while using these estimators, we have to take care of the sampling fraction in order to increase the precision of the estimator. So in all these cases, we find a suitable limit for the sampling fraction is this. And to verify this, we consider two populations, population 1 and population 2 is defined here. And in both the cases, we compare all these 9 estimators, a ratio type estimator and a regression type estimator. And this is our conclusion. Performance of different estimators for both populations are similar, and the estimator, the proposed class of estimator y over the lambda, this attains maximum precision that is proposed here. The efficiency of the comparative other estimators, they considerably more variance, and they are less precise. And we consider the MVP estimator of comparative classes YSP and YSS. These estimators utilize the auxiliary information in different way in order to be optimum in those respective classes. So the predictive estimator, it performs better than the counter classical estimators. So it is desirable to use predictive estimators rather than their classical counterparts, and the auxiliary information is to be used in a very careful manner, keeping in view the value of the sampling fraction, so that we can improve upon our estimator so far as its efficiency is concerned. The MVP estimator of our class, which is suggested here, it is more precise than the competitive estimators so far as the MVP criterion is considered. And the sufficient conditions under which an estimator belonging to the suggested class is more efficient than other predictive as well as the non-predictive estimators. Thank you, sir. These are my references.
Thank you, Professor Dash. Any questions or comments from the audience? Any questions or comments? Otherwise, let us thank the speaker, Professor Das, once more. Thank you very much. And let me.
Thank you, sir, Professor Joy Kumar, sir. Thank you, Bhatia, sir, and I am thankful to Professor Satish Kumar, sir, for giving me a scope to interact with you, sir. Thank you. Namaskar, sir.
Our next speaker is Dr. Kavi Arasu. He is talking on the topic certain studies relating to conditional repetitive group sampling plan under zero inflated Poisson distribution. This
So good afternoon. Yes, I'm myself, sir. Very good afternoon to another person here. I'm really very happy to be in part of this program. First of all, I'd like to thank the organizer, especially Satish Kumar sir, for giving an opportunity to organize this program and able to give it, share my research in this platform. And also, I thank Jai Kumar sir for sharing the session. So now I'm going to give my research talk. So did my screen is visible?
Yes, visible.
Okay, thank you. So my talk is based upon certain studies relating to conditional RGS plan under the zero-inflated Poisson distribution. So this is the work which was done by me with my research scholar, this research work, carried out in Bardya University. So here I just give an outline about my topic, what I'm going to share here. Introduction, part, review of literature, designing the method, discussion and references. So statistical quality control is the term used to describe the set of statistical tools used by quality professionals. It refers to the use of statistical methods in monitoring and maintaining the quality of products and their services. So the main objective of quality control is to reduce the company's cost by reducing the loss due to the defects occurred in the manufacturing industry. So the aim of quality control is to achieve the interchangeability of manufactured goods in large-scale production. It also helps to produce an optimum quality at minimum price. It ensures the satisfaction of customers with the products or services at high quality level to build customers' goodwill, confidence, and reputation of manufacturer. It ensures quality control at a proper stages by proper inspection to make sure that the non-defective products are only produced, and if who judges that conformity to the process to be established the standards and to take suitable action when there is some deviation occurs in their manufacturing place. So quality control not only protects, but also it improves the quality and productivity, because it is not an one-time achievement, it is a continuous process. More or less, the process control and product control are two broad areas of quality control. These two broad areas are like two sides of a coin, one without another cannot be exist. So all these things can be done with the experimentation and based upon the customer's feedback. So here, these techniques are developed based on the theory of probability and sampling, which was extensively used in almost all small-scale industries, such as manufacturing, textile industry, electrical equipment industry, plastic industry, rubber, electronics, chemical, petroleum, transportation, medicine, and few more. The word quality does not mean the quality of manufactured product only. It may refer to the quality of the process, that is with the men, machine, material, and also with the management. So the quality of the manufactured product is defined as the quality of product that fulfills the requirement of the customer. It's not absolute, but it is judged or realized by comparing it with some standards. It is usually determined by some characteristics, namely design, size, material, chemical composition, mechanical functioning, workmanship, finished, and other properties. Finally, the quality standards for the products are established by the customer. So my research area is mainly focused on acceptance sampling plan. So acceptance sampling plan is one of the major components in the field of SQC. When inspection is for the purpose of acceptance or rejection of a product based on certain adherence to a standard, the type of procedure we employed is usually called as an acceptance sampling. So there are many acceptance sampling plans that are available in the literature. Many people may be aware. Here, the item, at what situation we should go for acceptance sampling plan. When the item of interest can be incoming shipments of raw materials or purchased parts as well as finished goods from final assembly. Typical application of some sampling plan is for lot dispersion, sometimes referred to slot sentencing, for receiving inspection activities. The lot is disposed of in shorter time so that the scheduling and delivery are improved with less product damage. Accepted lots are put in production, rejected lots are returned to the supplier or subjected to other lot dispersion action. Sampling methods may also be used during various stages of production, that is single sampling, double sampling, multiple sampling, RGS plan, like that. N number of sampling plans are available in the literature. So acceptance sampling plan is the middle path in between the 100% inspection and no inspection at all. So according to the Professor Dodge in 1969, the major areas of acceptance sampling may be classified under 4 broad headings, called by lot acceptance sampling by method of attributes, lot by lot sampling by method of variables, continuous sampling of flow of units by method of attributes, special purpose plan called by chain sampling, schizo sampling, repetitive group sampling, etc. So whenever you want to implement a sampling plan, here the methodology the type of sampling plan proposed by Dodge, the methodology what I am doing is continuous sampling flow of units by method of attributes, since the plan conditional repetitive group sampling plan comes under continuous flow of units. So according to the Case and Keats in 1981, they proposed there are 4 different methodologies to be categorized for designing a sampling plan. They classified as risk-based approach, economical based approach, non-Bayesian approach, and Bayesian approach. So my sampling plan comes under risk-based Bayesian approach, comes into effect for under category 3 based on the past performance of the production unit. So Dodge 1967 has proposed a new sampling inspection system in 1967 called by switching system, that is 2-plan switching system. This 2-plan switching system has 2 states. One is normal state, another is tightened state, which has some stringent rule to be followed for the OC curve when it compared with the normal single sampling plan. So it was largely incorporated and studied in Milton 105E in 1989 for designing a sampling system. So this becomes a system whenever we talk about a 2-plan system. The system together with the switching rules from normal to Titan and Titan to normal form an integrated sampling inspection system which guarantees the consumer with specified acceptable quality level, and the risk of rejection will be small for products of the quality levels what they fix. So there are normal to Titan and Titan to normal. There are 2 situations may occur in any 2-plan system. So this was extensively studied by Rumbowski. So Rumbowski in 1969 has presented an extensively a system of immediate switching to Titan inspection when there is a rejection comes under normal inspection. So due to switching between normal and Titan, this system is called as an quick switching system. This quick switching system has been elaborately studied by many authors that we're going to see in the review of literature in the coming slides. So here, this Rumbowski studied cases by taking a single sampling plan as a reference plan under a constant process model. So this system considered as a finite Markov chain with 2 states, and hence the composite OC function has been derived by Rumbowski. Later in Southarajan et al. 1988 studied the properties of these modified systems and observed the following advantage of QSS-R. So there was initially Rumbowski proposed QSS-1. Later they proposed QSS-2 and QSS-3 by Southarajan and many authors. So thus QSS-2 and QSS-3 comes into the picture. So the modified system result is a composite OC curve, which is more discriminating more than the original QSS-1. So the QSS-2 and QSS-3 has been derived. And the QSS-2 and QSS-3 are more efficient than QSS-1 as said by these authors. So according to these authors, this QSS can be classified into 2 types. One is QSS NCNCT with normal and Titan 2 cases with sample size, that is 1 sample size with 2 acceptance number, which called by CN and CT. Another system, what we call by NK and CNAT, that is normal and Titan. Here they talk about two sample size, one N, another is KN, with one acceptance number, CNAT. So here, the first one introduced the QSS of NCNT-CT, which a normal level and Titan level of acceptance number. And the second one with sample size with normal and Titan with acceptance number only 1. So this system, when K is equal to 1, this system may reduce it to single sampling plan. So whenever the quick switching systems plans are studied, widely used in literature, cases 1, 2, and 3, with various sampling plan as a reference plan, single sampling, double sampling plan, mini plan. But here I used cases 1 with Bayesian conditional repeated group sampling plan as a reference plan. So here, a distribution that is called by zero input Poisson distribution is taken into the picture, and it was executed under the circumstance of zero inflated Poisson model. So in the competitive world, every manufacturing company strictly follows certain procedures at every stage of production to maintain their quality. So generally, in count data, when excess number of zeros are present, it can hold to a Poisson variable. So the good example I can point out here is the number of insurance claims received by two-wheeler insurance, the number of cigarette smokes by a student in a college, the number of defective items occurred in continuous production of items. These are the situation where the defects may occur. That is, the number of excess number of zeros are possible to occur. In such situation, the occurrence of defective items are rare phenomena. That is, the non-conforming in lots would be more in number with excess number of zeros are occurred. However, due to random fluctuations and some unavoidable reasons in manufacturing process, there may lead in a situation to occur few defective products within a batch or perfectly functioning production system. So there need a sampling plan that is based upon Poisson distribution has been oftenly used to monitor the number of defects in sampling unit. However, one of the major problems is evaluating the excessive number of zeros of non-conforming events in production process of a long run from a statistical viewpoint. So here we proposed the zip distribution can be an alternative for in such scenario, which helps the management to take a precise decision, or it can be certainly reduce the error rate than the regular Poisson model. When the manufacturing equipments are properly aligned in an order, the number of defects are impossible, say it been aligned the probability P, and the occurrence of defects follows the lambda, then we may propose to a distribution what called by zero inflated Poisson distribution. So here we consider the Bayesian sampling plan because the conditional RGS sampling plan is based upon, I already told, is a continuous process, and it is based upon the condition, previous condition I. So we assume, we consider the Bayesian perspective. The basic assumption underlying the theory of conventional sampling plan by attribute is that the lot or process fraction unconforming is constant or stable. However, in reality, the lots are formed from a process will have quality variation that occur to random fluctuations. Generally, there are two types of variations that occur. One is within lot variation, another is between lot variation. In such situation, many authors have come across the importance of designing a sampling plan under the Bayesian perspective. So here, this methodology can be used when the quality engineer has some prior information on the production process to make a decision about the distribution of the lot. So here, I'm just highlighted some of the few authors have given some studied already about the zero inflated Poisson distribution. That is comes under the review of literature. So Lambert 1992 has discussed the application of defects in manufacturing process with zero inflated Poisson model. Readout et al. 1998 derived some models for count data with occurrence of excess number of zeros. And Boeing et al. 1999 has discussed ZIP is a better model than the Poisson in dental epidemiology research to measure the dental health. And Rodriguez 2003 has made some discussion about the zero inflated distribution out of the Bayesian perspective. Nayan et al. 2008 established the comparison between Poisson and zero-infinite Poisson model with an application to a number of black spots in the Codar shape. Muzita et al. In 2013 reported the zip distribution is a well performed to model with the excess number of count data, and he draw the OC curve. And Loganathan and Shalini in 2013 developed the tables and procedures for the single sampling by attributes under the condition of zip. Later, Srinivasa Rao, Kaviyarasu and Asif and myself and Sivakumar also developed some model for the zero-infinite Poisson model. Then coming to quick switching system, so Rombosky initially introduced the concept of cases 1, 2, 3. I already told you in a single sampling plan as a reference plan. Later, Soundarajan has developed with the two different types, NCNTD and KNC0, with the various sampling plan with the reference plan. And Soundarajan studied the RGS plan as a reference plan. Later, Jayalakshmi in 2009 studied some sampling plan as a reference plan, like STDS plan, RDS plan, that is repeated deferred sampling plan, multiple deferred sampling plan as a reference plan. And they have developed a lot of procedures, how they can be implemented in their own scenario. And myself in 2012 studied the QS1, 2, 3 with RGS, CRGS, and MRGS plan as a reference plan. And Pratibha Veerakumari in 2015 developed the economic order quantity policies of QS1 and under the condition of intermittent Poisson distribution. And Uma et al. 2016 has constructed and developed cases 1 with the zero-infinite Poisson distribution was carried out for the traditional plan. Later, myself and my candidate studied the single sampling plan and RGS plan for under Bayesian perspective. So in Bayesian sampling plan as concerned, Brush 1986 showed the producer risk under non-Bayesian and Bayesian perspective. Both are not same, he has evaluated. Calvin 1990 has pointed out that in many practical situations, the lot proportion on conforming will vary over lots. Suresh and Lata has developed the Bayesian single sampling plan under the condition of gamma Poisson distribution. Loganathan has said about certain single sampling plan under polio distribution. Vijay Raghavan and et al. Has studied the single sampling plan under the condition of gamma Poisson distribution. Muzida et al. Has derived a zero-infinite Poisson distribution under the inflated model. Here, the model, the plan what we proposed is conditional repeating group sampling plan. So the concept of conditional repeating group sampling plan has been derived from the RGS plan, which was introduced by Sherman, and later Gauri Shankar and Mogapatra has introduced the conditional repeating group sampling plan, which was an extension of the RGS plan, and they named the conditional repeating group sampling plan based upon the previous ILOTs. They observed that the CRGS plan is better in sample size and it's more efficient than the RGS plan, and they have framed the model and the dynamics more than the repeating group sampling plan. The conditional RGS plan has been derived through the JERT approach, which has been used by several authors for studying some quality control plans. Later, myself also studied the traditional plan of the conditional RGS plan, and in this we focused on Bayesian conditional RGS plan as a reference plan. So according to the Shankar and Mogapatra and Sherman, the procedure, the operating procedure, what they follow is draw a random sample of size and determine the number of defects D found therein. Accept the lot if D is less than C1 and reject the lot if D is greater than C2. And if D lies between C1 and C2, repeat step 1, 2, provided the previous I lots are accepted, otherwise rejected. So this plan can be reduced to the normal plan. When C1 is equal to C2, it reduces to single sampling plan. When I is equal to 0, this plan becomes an RGS plan according to the Sherman 1965. The OC function of the sampling plan, that is a conditional RGS plan, is related by, which are given here. A PA of P equal to the probability of acceptance and rejections are given with the probability of acceptance 1 minus PA minus PR has been given. So here, the model, the zero-fit Poisson model, has been considered for count data and exhibits over dispersion to excess number of zeros. So here this model is assumed to mixture distribution that includes proportion of excess number of zeros proposed from the Poisson model, so which was proposed by Lambert. So here we consider x as a non-negative integer value as a random variable with the probability mass function of the model as given as probability of x is equal to omega and lambda, the two parameters which are involved in zero-fit Poisson model. The model can be derived by using the following steps. And here the omega is the weight parameter and lambda is the Poisson parameter. When omega is equal to 0, this model is reduced to Poisson model. When omega increases, then the model will be more, the zero-fit Poisson model will be more appropriate than the Poisson model. So it is termed as the mixing proportional of degenerate 0 with Poisson model, and omega and lambda are the parameters of the zip distribution. So according to the Loganathan et al., the OC function of single sampling plan under the zip distribution is given as such, and omega indicates the inflation of 0 defects, and the lambda is the NP value. So here, when the number of non-conformity items in the sample P follow the zip distribution with parameter P and omega, which can change from lot by lot. So we need some prior information. The prior information distribution, what we call by gamma distribution, so we call this gamma zip distribution, can be assumed to be the conjugate prior of P considered a random variable. So here P follows gamma with S and T, where T is a scale parameter and S is the shape parameter, where S denotes the prior knowledge which may be estimated from the past history of the production process. So the derivation of the acceptance sampling plan for the number of non-conformity X with prior distribution under zero-inflated Poisson distribution has been given. Yes, and this is the final equation. From this, we are designing some methodologies for the sampling procedures. When selecting a sampling plan, the parameters are selected through a set of specifications for various quality level. The two income quality levels, namely AQL and LQL, are considered along with their corresponding relative slopes of the OC curve for the selection of various sampling plan. Incoming quality levels and AQL, IQL are studied here. So the operating procedure for the proposed plan is given here. Draw a random sample of size n, test each unit for conformance specified requirements. Under normal inspection, inspect the plan under the Bayesian CRGS plan with parameter n, u1, u2. If lot is accepted, continue step 2. Otherwise, go to step 3. In step 3, under title inspection, inspect the plan under
5 minutes more.
Yes, sir.
Oh.
These parameters have u1, u2, v1, and v2. It may be noted that, so I'm skipping this point. Determining the optimal parameters. The operating ratio value is calculated corresponding to alpha is equal to 0.05, beta is 0.10 is considered. This gives the strength of the model, that is considering P1, P2, alpha, and beta for the plan parameter, and we can compute the operating ratio values, that is P2 by P1 by R equal to P2 by P1, determining the acceptance number C from table corresponding to alpha, beta. The OR can be found, and we can go for the nearest value, and one can determine the unity values of NP1 and NP2 from the corresponding table. And thus the quick switching system provides the flexible sampling under normal and Titan situations. So these are the behaviors of the OC function when compared to gamma zip with the zip and the gamma Poisson. So this is an example where we can apply this gamma Poisson model in our, this is the proposed model where we can apply. For example, a small scale industry manufacturer in food industry have the responsibility to produce the quality products to the consumer with high good quality products, because quality is not a one-time achievement. It is necessary part of the planning, preparation, and execution of the production process in foods. So any lack in the consideration of quality can result a serious threat to public health. Suppose the quality engineer wants to conduct an experiment, wants to inspect the food products for possible acceptance or rejection of their item. Assuming that the quality of food products follows the gamma Poisson, the inflation of 0 will be more. And we know the prior history of the production unit, which can be estimated through the prior production process. We may fix as S is equal to 5. Suppose the quality engineer wants to find the strength of the plan of this proposed plan, that is quick switching Bayesian CRGSS plan, under 2 levels, namely of the QSS model, that is normal and Titan, with AQL and LQL, that is P1 and P2, with and alpha is 5% and beta is 10% is fixed. So the food manufacturer has a lot of 3,000 packets in a day. In that, they have adhered to consider 50 sample of inspection based on the proposed model. What we consider the designing of given sample size, we put n is equal to 50, u1, u2, v1, and v2 with I equal to 2. So in such scenario, they take 50 sample for inspection, and they start with normal inspection, and they provide 2 defectives. If there are more than 2 defectives occur, they immediately switch to Titan inspection when there is a rejection comes under the normal inspection. So in Titan inspection, the quality engineer tighten the inspection, and with the same sample size n is equal to 50, they allow only 1 defectives. 1 packet is to be defective packet. Otherwise, if it occurs more than 1 defective, the lot will be rejected. Otherwise, the lot will be accepted and switched to normal inspection. So switching between the inspection of Titan and normal, this methodology is called by quick switching system. Thus, the proposed procedure may have more protection to the consumer. When production increases in the long run, the quality of the products, that the level of acceptance will be increased when compared to the gamma Poisson model. So come to the last point, conclusion. So from this model, when the omega value becomes large, the sampling plan under Bayesian zip distribution has performed better than the classical sampling plan under the zip distribution and the gamma Poisson distribution. It should be noted that when the production process has more inflation, that is 0 defect manufacturing environment, the proposed model plan has significantly reduced the producer's risk as well as consumer risk. It is observed that from the table, the optimum of gamma zip sampling plan may require more items to be sampled from lot submitted for inspection. However, it reduced the risk of producer regarding the rejection of good qualities and safeguard the consumer against poor quality when it was assigned. So here are the table values, what we have derived through the computer program. So it's open.
Thank you, Dr. Kaviraju. Any questions or comments from the audience? Any questions or comments? Otherwise, let me thank Professor Kaviraju once more.
Thank you very much, sir. Once again, I'd like to thank the organizer and the chairperson for giving an opportunity to share my research. Thank you very much, sir.
Our next speaker is P.R. Vittal, and he is talking on the topic stochastic finance in a business company associated with ruin, bankruptcy, restricted reserve, dividends, and dividend strategy. Professor Vittal, please.
Praveen. I'm Praveen. Just a minute. Are you able to hear Mr. Satish Kumar? Mr. Jay?
You start your presentation.
Yeah, I'll start my yes, I will start my presentation. Just a minute. I'm really thankful to Mr. Satish Kumar and his team for providing me an opportunity to participate in this mega conference with several speakers of well-known caliber and all that, and given me my last moment an opportunity to me when I requested him to participate in this and present my talk. I'm really thankful to Professor Satish Kumar, and I start my talk. Now, the talk is on stochastic finance in a business company associated with ruin, bankruptcy, restricted reserve, dividend, and dividend strategy. Now, the question is that more concerned with companies and insurance, especially with insurance company. Now, when we go into the abstract, the stochastic models are considered to analyze the risk involved in ruin and restricted reserve as barriers. Ruin is reaching the barrier x equal to 0, and restricted reserve, suppose, is k, and reaching the barrier k. The Kolmogorov forward and backward equation are derived for models with inputs and outputs as random, and risk involved in ruin and restricted level are derived using Kielson's compensation function. The philosophy of this technique is to convert a bounded process in terms of Green's function of an unbounded process. In other linear model, drift is also introduced in addition to random jump, and characteristic of this process are analyzed. By suitable limiting procedure of this process is also converted into a diffusion process of Wiener type with drift. With the same limiting procedure, the first passage time for ruin or the risk level reaching the constant barrier are analyzed. The model is also extended into a model with exponential dip and time-dependent barrier. The analysis of the above problem is also done using Richard Bellman's embedding technique. Both the Philip Lindbergh and the dual model are also analyzed. The expected discounted value of dividends are derived. We also considered a risk model wherein there are two components of income with restricted level. We also study the optimal dividend problem to determine dividend payment strategy that maximizes the expected discounted values of the dividend payment. Now, contributors to this type of problem, Abraham Watt, unfortunately, he died in India when he visited the Madras University and went for a tour to Nilgiri. J. Kielson, a professor, well-known professor in Rochester, who introduced the concept of compensation function to solve boundary value problem, to convert boundary values into unbounded process. Kemperman is also well-known in dealing with generalized world identities. Joel is also considered the later variables and studied bounded product. Segardal especially tried such problem through insurance. Kryakov, a Russian, considered a moving barrier problem with diffusion. Richard Bellman, a well-known applied mathematician, introduces the concept of the embedding approach to solve bounded problem. Gerber, a well-known recent mathematician, studied many such problems. Now, what are the techniques that we apply in studying this problem? First, we go the Markov process to analyze the risk process. The ruin and restricted result levels are considered. Kolmogorov's forward equations are derived. Kolmogorov's backward equation are also derived. Integral differential equations are considered. Barriers are two types of barrier. One is called the absorbing barrier. The other one is called the reflecting barrier. Compensation function technique is a well-known and equivalent to method of images is considered for studying bounded problem into unbounded problem. Green's function is the main concern of compensation function in conversion to boundary value problem into non-boundary value problem. Laspam and Fourier transform the technique used. Inversion, of course, is a technique to convert into the Green's function. Limiting procedure to the diffusion process and moving barriers are also considered. Now, we go into the stochastic model wherein the inputs and outputs to the reserve of an insurance company follows a Markov additive process with a linear drift in the negative direction. The simplest model is now given by x of t equal to x naught minus alpha t plus sigma zi. Zi are the claims or the claims in the insurance, and n of t is the number of Poissons, and alpha is the drift. Now, here are IID random variables with common density. The problem of interest in this model is to study the first passage time for ruining the company or the first passage time for risk level to cross the barrier x equal to k. Essentially, mathematically speaking, this is a two-barrier problem. The compensation function developed by Kielsen has been found extraordinarily useful. The philosophy of this method is to arrive at the first passage time in terms of the Green's function of the unbounded process. The method can be used to proceed further also to the limiting case. Now you see, we go into the forward differential equation. We consider the dynamics of the process in the interval of time t to t plus dt and write the forward differential equation, which appear in the form of integral differential equation, and x equal to 0 and x equal to k are the barriers of this bounded process. To give effect to the boundary x equal to k, we introduce the compensation function, thereby converted the bounded process into an unbounded process. The CXT that appears in the last integral differential equation is called the compensation function. As derived by Kielsen, the CXT is now by, in terms of the Heaviside function h of x minus k, that indicates that the process crosses the barrier x equal to k for the first time. Now we take the Laplace transform and the Fourier transform, Laplace transform with respect to time, and the Fourier transform with respect to scale, the various functions f, c, as, the jump density, all appearing in the above equation, converted into an algebraical equation in terms of the last equation that you see. Now you see L plus alpha s plus nu into 1 minus as equal to 0 satisfy the root s is equal to sigma L. When s is equal to sigma L, the compensation function in the transform space, it takes the value of minus e to the power of sigma x naught. Now, the moment generating function, or in other words, the first passage time m of t, is defined by the integral cxt from k to infinity. The negative sign appears because cxt is jumping to the negative side and the first passage time compensating that. Though all through algebraical inversion, the first passage time is given by m bar L in the transform space. It is possible to convert in terms of the Green's function, and we have to find out the Fourier inversion transform of e to the power of sigma into x naught minus k, and hence you see finally the moment the first time passage time is given by m of t. If it is shifted with alpha drift, then we can convert also a pure jump process, checking x to x plus alpha t. Now you see we go into the diffusion limit. What we have considered is Kolmogor's forward equation with compensation function, jumping both ways and positive and negative direction. The insurance company's claims comes in a positive way jump, and the losses comes in the negative jump, the dual process. And therefore, we change the jump density gamma to gamma square mu, take the mean density of jump as 0, and the second moment as a constant, and proceed to eliminate as gamma tends to infinity. Now it is automatically converted into the diffusion equation. Inversion is possible. When you convert into there, we get the well-known diffusion equation whose density function is known. Now, it is possible to go to the same limiting procedure as we adopted, as gamma tending to infinity, size of the jumps tend to 0, and the second moment is converse. We get the first passage time to cross the barrier x is equal to k. Now, if the barrier is moving in time, that what we consider is a constant barrier. If we allow the barrier moving in time, that is, first we consider a linear barrier of the form a plus bt, then also we can proceed to the same diffusion process, same equation. The forward equation we have considered cxt. Now you see that the Heaviside function is given by x minus of a plus bt. We can write down cxt and proceed exactly the same way as we have done, and therefore the first passage time m of t and its transform are derived. Now, when you go into the inversion process, you see that the inversion takes place and the first passage time was also derived. Now, x equal to, suppose x equal to reach we consider a barrier wherein the jump is negative, especially in companies. If so had the claims goes downward, jump is negative, Poisson jump, the drift is always positive, and therefore the barrier can be reached. In the case of reaching barrier, the compensation function is split into CFT into delta of x minus a plus bt. The exponential drift could be used, and Pareto distribution of jumps are considered. Parasite distribution that when the risk reserve is very high, the reward is also very high. Now the forward equation in terms of this process is given by this equation. Now when you proceed, we find some difficulty in solving the integral differential equation. Therefore, we consider the transformation x is equal to e to the power of y and consider the transformation into a linear drift problem. The exponential drift problem is converted into a linear drift problem. The moment you convert this into a linear drift problem, the same procedure as we have seen already could be utilized to solve this problem with exponential decay. Now we go into the embedding approach. In the embedding approach is an alternative approach to study the first passage time problem, but here we consider the Kolmogor's backward equation, whereas Kielsen technical compensation function, we consider Kolmogor's forward equation. Now Lindbergh started the model, definitely introduced the concept of dividend. The dual process are there, especially in companies, your claim is now coming as a positive jump because of through royalty and investing as income, and the expenditure is going linearly, and hence we have a dual model compared to the insurance model, and we can also study the dual model in this situation. The first passage time for both the model and the dual model, in addition to we have considered the drift in the negative direction. Now you see ST is the jump, it goes downward, alpha t is the usual premium that comes, and they're all Poisson jump, summation SFT is equal to SFT, and then similar types of problems are studied in storage models also using Kielsen, Prabhu, Puri, Senduria, etc. There the barriers x equal to 0, x equal to k are considered, so the probability of ruin as well as the expected amount of overflow. The most important thing is that the expected amount of overflow above the upper barrier is given time. The expected amount means the amount that flows over the barrier is cut off for declaring dividend or bonus to the shareholder. In general, these problems form a class of first passage time problem to study either the emptiness or the overflow with reference to the storage model. Now, in neurobiology also, we find neurons firing takes place as a spike trains arise from the so-called spontaneous activity of response of neuron to external stimuli. The membrane potential change is due to the random jump in both the direction, and in between the jump, there is a deterministic decay. A detailed account of these types of model is given by Feinberg and also Vasudevan and Vittal et al. In some of the papers published earlier. The model given by one and the dual model, the interest of data is the excess over the barrier and is initiated by Fennetti in analyzing the optimal dividend barrier. In similar context, Perry and et al. With reference to white noise problem, they considered similar model. Perry and et al. Studied a queuing system also to determine such type of problem. Avanti considered the optimal dividend barrier in studying this type of problem. It is assumed that a Levy process, which is script-free downward, and in this paper we use the embedding method of Bellman and Bing to determine the expected discount of different models proposed. Now you see, I skip all this thing. Now I go into the optimal dividend case. Xt is equal to x minus alpha t plus zt. That means the spending is minus alpha t and the royalty comes in terms of SPT. It is actually the dual to the insurance problem. Now x at 0 is x is the initial risk reserve of the process, and the average size of the income is always considered to be positive, and therefore mu is considered to be positive. This model is more appropriate to companies that have occasional gain and constant expenses proportional to the time. The process is a Levy process, skip t in the negative direction. The process can be modeled to reach the companies where the gain due to selling of their patient is a random event with claims amount as a probability distribution and expense have a deterministic size. This type of problem can also to have two barriers. The one at the point of ruin, the other one is crossing the restricted reserve level K. The jump amount can be interpreted as the net present value of the future income. The excess over the barrier may not be distributed at once, but recorded as a debt to the shareholders, decreasing the net reserve by its present value. In such a situation, it is determined to determine the expected value of the discounted dividend. So we define VXKT as the expected value of the discount dividend in time t. We use the backward equation of approach to arrive at the result. The initial interval of time tt, either there is no jump, or there is a jump of small magnitude, or is a jump of such a high magnitude which crosses the barrier itself. Now, the stochastic dynamics of this process in the initial interval of time dt for the discounted value is expressed in terms of the initial interval of time. There is no jump in the initial interval of time, the first term on the right hand side, or there is a jump, the discounted value is given by e to the power of minus delta t, or the last term is the jump is such a large magnitude, it has crossed even the restricted reserve level K, and which go as the shareholders' income or for bonus or for dividend. And finally, it reset the level K. The excess is cut off and the reset at the level K. Note the last term, VKKT, that means the process starts from K and re-proceeding to calculate the discounted value. Using the Taylor's expansion, you see that we arrive at the integral differential equation for this process. And now V bar is the Laplace transform of the discounted value. And taking the Laplace transform, this equation is now converted in the transform space. Now you take the specific case of the jump density as exponential, where z greater than 0, which is a Heaviside function, transforming the variable z by y equal to x plus z. This is converted into a different integral differential equation, and differentiating with respect to f, we reconvert into a differential equation which could easily be solved. Now, this turned out to be a second order differential equation with constant coefficient whose roots are determined, and hence we know the general solution for the expected discounted dividend space in terms of the transform variable. The question is A and B are to be determined. Now we go into the solution, the Richard-Bellman's equation of the solution, which is seen here, and substitute this general solution. You will surprisingly see that all the coefficients of A power m1x, B power m2x cancels out. That is independent of initial position in between the barrier. And thereby we left with one condition connecting A and B. Now, since we have considered that the company is not ruined, the probability of starting from 0 is 0. And hence you get B bar of 0 Ks is 0. This amounts to the condition A plus B equal to 0. Hence, using the initial condition and also the boundary condition through the Richard-Bellman's equation, we are able to determine both the constants A and B, and hence the complete solution in the analytical space is determined. When you proceed S equal to 0, that means t into infinity, ultimately the discounted value for everlasting time is also calculated. This is the result which has been calculated by Avanti also, but there's an error which has been rectified by our work. This paper has appeared in Stochastic Journal and as application. Now the condition of the optimal dividend area, you see, in order to find out what is the optimum dividend, we differentiate that with respect to the K and thereby find K star, the optimal level of the barrier, so that the company will be safe in declaring the dividend and also discounting the dividend factor. Now the same thing you now see in terms of various parameters. It is very easy to now write down the optimal dividend barrier in terms of the parameter mu and delta, where delta is the discount factor, mu is the average income, which is always positive. Now see, we consider the dual problem. For the dual problem also we can proceed at the same level and arrive at the differential equation and integral differential equation converted into the simplest form, and the solution is arrived. Now we see that in order to calculate when the barrier is moving linearly up, it is going to touch and there is no jump. Therefore, we are interested in evaluating the expected discounted dividend before ruin. For determining this, we first need to know when it is going to reach the barrier. Therefore, we need the first passage time for reaching the barrier K, and it has been determined as F1 bar xk here using the Richard-Bellman technique. We can also find the first passage time for reaching the barrier K. Once you reach the barrier K, we can get the complete solution for this form, and then two situations arise. After reaching the barrier, it can continue without any jump. Therefore, there is a linearly increment in the income to the company, that is contribution by 13, or there might be a jump in between. After the jump, again it starts going linearly up. After the jump, it is going linearly up, is determined by this integral, and hence these two components are mutually exclusive, and hence the total discounted corresponding to both these factors are given in terms of V1xk. Now the Rxk at the equation 17 is now considered to how much amount is now discounted in the interval 0 to k. Rk is a function and which can be evaluated in finding out all the discounted cash flows in the company in terms of the dividend. Now total results has been arrived at, and hence we now see that Vxk ultimately completely analytically determined. If delta equal to 0, this function is analogous to that of the water that is wasted out in a storage problem, and delta equal to 0 correspond to all the events that occur in a storage when the water overflows, and hence it can be considered x equal to k as a reflecting barrier. Now you see we institute consider a model similar to the model 1, but we take the expenses are proportional to the surplus level. That means we are taking the exponential decay. Now the exponential decay is built in the second term, 0 to t x of t dt. Now when you go into x of t dt, we write down the model here, and then we construct the embedding equation. When you go into the embedding equation, because the x involved in the exponential decay, the solution comes in terms of 1f1 function, that is hypergeometric function. Now, the discounted cash flow is also written in terms of V2 bar. The 1f1 AC as the usual notation in terms of an infinite series. We can also find out what is the optimum barrier level in order that the discounted price is safer to the policy holder. That means K star in the sense of Gerber has been arrived at. Now the value of K from this results gives the optimal value of K. Now in this section, we introduced two components of discount. One is that you claim comes, you see, as discount. Another one is the amount invested in the bank will also come a constant increase. Therefore, we introduce alpha plus BT as the two components of income, one coming in terms of the interest, other coming account of the premium. So interest and premiums are the two components of income. One is increasing linearly, other is at a constant rate. Now, for such a model, assuming the Poisson jump level, we can calculate the expected discounted value. Now you see that when it is again when the upward linearly moving up, the barrier is going to be crossed. After the barrier cross, what is the first passage time to cross the barrier is important. Is chi ukt in the notation of the insurance is represent the probability of first time reaching the upper bound k, and then we find the solution for this in terms of the two components of discount, and hence we found out chi bar as a complicated function in terms of various transform variables. Now you see, after finding chi, we can find ultimate probability of the reserve reaching is also determined. Now you see all these when beta equal to 0 correspond to the original solution, and as long as they apply, the surplus increases with time deterministically, and all such increase will be per dividend. The discounted value of this dividend function is given, as we have seen in already section, by first one term. There is no jump at all. When there is a jump, it comes down and then again start moving up. Therefore, these two components pushed together is as similar as RK as we have introduced, and hence RK is determined. That means we have completely determined the entire set of solution. Now the dual problem we create. The dual problem in the sense that the royalty comes, the expenses come in terms of minus beta t plus alpha xk, and then the jumps are in the positive direction, is exactly dual to what we have seen earlier section. Therefore, the solution to this problem can easily be arrived at. And ultimately, we now to see what we have arrived socially. These started with the well-known Lindbergh model for insurance business to find the expected discount dividend for this model and also for the dual model, using the compensation function as well as the embedding approach. We also obtained the optimal barrier strategy for this model. Then we considered a dual model where the expenses are proportional to the surplus level to find the discounted dividend amount before ruin and also determine the optimal barrier. Finally, we considered the insurance business with two components of income, which are deterministic together with random claim. For this model, we calculated the expected discounted dividend, taking into consideration the possibilities of, once the reserve process reaches the constant barrier K. Finally, we pointed out the dual model to this situation can also be studied in a similar way. Now, Abramovich and Stegan is a handbook wherein you can find all these 1f1 functions to the solution of the equation that we have derived. Avanci and Gerber has write a survey paper on optimal dividend in the dual model to the insurance. In the insurance, you go that the claims go negatively and premiums comes positively. Whereas in business in company, we say royalties goes up, which is claim, and the expenses go linearly because of the drift. Bellman and Harris has written a very exhaustive book on branching process, wherein they considered the embedding approach of study. D. Finity is the person who introduced first, even though Lindbergh started insurance model in 1903, D. Finity introduces a technique of that the risk level should be introduced, otherwise the company go amassing well. Once they introduce a level K for the risk level, the excess over the level can be considered for declaring bonus or dividend to the stakeholder. Feinberg, in a similar model in neurobiology, studied the detailed expression of the neuron firing problem. Keels and Issy introduced the first passage time problem for a homogeneous skip-free process on the continuum. Lindbergh again is gone the work with reference to the neurofiring problem. Already we said why short noise problem was studied by Perry et al. Now, Prabhu has written a book on stochastic process, wherein he considered the Wiener decomposition to study the bounded process. Puri and Sandhya has considered a single barrier problem. Vasudevan and Vittal Vijayakumar, neuronal spike trains with exponential decay, we consider a similar type of problem. Myself, Tangaraj and Muralidhar studied stochastic model for amount of overflow in a finite dam. When delta equal to 0, this insurance problem corresponds to stochastic dam problem, wherein discount is not considered there. First passage time problem with restricted reserve with two components also considered. This appeared in the Scandinavian Actuarial Journal. Now, any question?
Thank you, Professor Vittal, for the interesting talk. Any questions or comments from the audience? Please. Otherwise, let me thank the speaker, Professor Mittal, once more. Thank you very much.
Thank you very much for providing me an opportunity to present in this conference. The chairperson and also especially for Satish Kumar.
Our next speaker is Professor Ashokan Variath. He is talking on the topic on applications of principal component analysis. Professor Ashokan, please.
Okay, thank you. Okay, can you see the slides?
Yeah, it's okay, sir.
Okay, so okay, good morning. Sorry. Good evening. So for me, it is a very good morning. So very early today. It is around 7:30 in the morning here. So that's why. Thanks for the invitation to this conference to talk on scientific research. And I'm thankful to the organizers for giving me an opportunity to present some of the interesting research I do. So this topic I just tried to give today is the application of principal component analysis. So the principal component analysis is a very old topic, we can say, because we are studied long time back also, but due to the present scenario, like the data science and big data analysis, this application of principal component is very important, and many researchers started using this principal component analysis. So I tried to give you some area where we can really use this and where I have some experience of using it. So I just going to not go in detail how it is done, but I can say these are the area where we can use this. So in the machine learning or statistical learning, so we have a lot of techniques. What they call is classified into two groups, like a supervised learning or unsupervised learning. So in the supervised learning, what normally we have a set of features, just like a covariates, like x1, x2, etc., xp for each subject or object or the unit, as well as a response or an outcome variable y. So that is, we have in supervised learning, we have a y and some set of covariates. And the goal is to predict the y using the covariate or the model the y using the covariates. So when you go to the unsupervised learning, we normally observe only the x value, x covariate, that is x1, x2, xp, and generally there is no y component in that. So the purpose is that in the unsupervised learning is just get an idea about the features and how we can utilize that. Like this technique is generally called as the principal component is coming in that part. There's only a set of variables there. Also factor analysis, also clustering, So these are known as the supervised, unsupervised learning techniques, whereas the supervised learnings are like regression, classifications, and all, where we have a so principal component analysis often considers a unsupervised learning method, but we can always use this, also link this PCA with the supervised learning scenario also. Okay. So I just go a little bit, a few slides on the principal component, then we'll go to the few applications of that. So the PCA produces a low-dimensional representation of the data set. So we have a large data set with many variables and many observed in different individuals or the objects. So it's a big data set, and we can go for a reduction in the dimension. That is the main idea about the PCA. It defines a sequence of linear combination of the variables that have the maximal variance and are mutually uncorrelated. So these X values are correlated generally, not necessarily fully correlated, okay, high correlation or not. For example, in the regression modeling, is correlation is there, we cannot do, the multicollinearity is there, but there's some dependencies there still. So the idea is you convert this variable, it's a linear combination, and we have the response, but these are all going to be mutually uncorrelated. So apart from producing a derived variable for use the unsupervised learning problem in the PCA, also serve as a tool for a data visualization. So we can look at how this these components is representing it as a visualization tool. And our main focus here today is to consider the PCA as a dimensional reduction tool. So if we have this covariance x1, x2, etc. variable, it's a normalized linear combination of these features, what I call, then we can find out a linear combination of all these variables as Z1, phi11, x1, x521, x2, like that, phi1, xp. So it's a linear combination of the variables, and we normalize means summation of this phi I square is equal to 1. So that is the normalization principle is coming there. And in the principal component, what we call these phi's are the loadings of the first principal component here. So we normally constrain the loading as so that their sum of squares is equal to the 1. So that is, otherwise we have many variables and it will go in different directions. So we have the normalization procedure is there. So the computation is, so we can, like that, we can do many components there. But the idea is to choose this component in such a way that we can, in a shorter number of linear combination, we can explain maximum variation of the X matrix. So suppose we have n into p data set X. Since we are only interested in the variance part of that, we assume that each of the variable in X has been centered to have the mean 0, that is the column means of X are 0. So we then look at the linear combination of the sample feature values, the same notation here, and with the subject to the constraints, this. So since each of these xj's are mean 0, so we can also see that the Zi also have the same way, because so we can construct the second principal component in a similar fashion, the constraint to the first component goes subject to that, because we want to go orthogonal to the first component. So independence is required. So this problem can be solved in a simpler way to that the constraint, because we can put as a constraint maximization there. But you can easily do that. It's a single value decomposition of this X matrix, a standard technique in the linear algebra. So we can construct the eigenvectors and eigenvalues of the covariance, this X matrix. And we can order these eigenvalues, because that is that you can say that is the variability explained. So we can take the first component, how much is the variable. So if the lambda 1 is the first one component eigenvalue, the lambda 1 divided by summation of the lambdas, we can see that much variation is explained by the first component. then second component, like that. You can see that. Then we can choose a set of principal component, maybe the first 10 or 15. So because we can put a constraint on that, because how much variability we need to explain by that, maybe 90% or 95%, then you can utilize those principal component for further analysis. So we refer Z1 as the first principal component with the realized values of Z11. So we can get the principal component score also, but that is multiplying by the X values by the first principal component. You can get the Z score easily there. So the loading vector 5-1 elements are defined as the direction of the feature space. So we are having a new space now with the principal component scores, along which data removes. Okay, so if we project the n data points onto the direction of the projected values of the principal component scores, Z1, Z2, etc. Okay, so we can have this, and the second principal component, the linear combination of this is uncorrelated with the Z1. So we get this second component with the first independent of the first component. So, and this is the loading vector. So these are the eigenvalues. So it turns out the constraining Z1 to the uncorrelated Z1 equivalent to the constraining the direction of the phi 2 to be orthogonal, and the principal component direction are ordered sequence of the right singular vectors of the matrix X, the eigenvectors, and the variance of each components are the eigenvalues. The first PC has the maximum variance, followed by the second, etc. So we only use the we can use it by leading to dimensional reduction. So we can see the first, second, third like that, and try to. So how do you select the PCs? Now we have, because if you have the X matrix with the n into P, we can have P principal component. So can use the eigenvalues for the selecting the number of the PCs, and the loading of each PC give an indication of the importance of each variable in that component. So the eigenvectors, or the first component, we can look at the values of this eigenvector, and if the larger in absolute value, we can see that how much is contributed to the principal component. If some of them are very negligible or close to zero, we can see that particular variable is not contributing much to the first principal component. Like factor analysis, it is easy to find a new latent variable too. Some people do, like we have a 5 principal component, and we can try to understand what are any latent variable type we can define for each component or not, because it is a score based on all values of the initial variable, but it can indicate some sort of factors. And another way of doing is for each variable, we can compute the sum of the absolute values of the eigenvector values of the each case and keep that as an indicator how important that particular variable in the entire data set. So we can also, just like a variable selection, so we can also, out of the P variable, which are the variables are very important in explaining the variability. So we can add the absolute values of each variable is component in the principal loading or the component loadings, then that can give indication. So you take the absolute value, not adding up all of them. Okay. So now I'm just turning to how we can utilize this principal component in the recent scenario. So one application this is generally available in, you can see that is the image processing. So when you are image analysis, like the photos and everything, so it is very, very difficult to send or store these images, which is very, very high. That is, the storage capacity is very high. So here I'm trying to see a case like sending or storage the photos or images are cumbersome if the file size is going to be very, very large. For example, consider the fingerprint. So nowadays, if you go to an airport, they take your fingerprints, and they will try to match with other fingerprints to find out, who you are and any other activities are going on, the terrorist activity, those things are there. So fingerprint is very, very important for each purpose, identify the correct person. And if they can match with the other person, because the photo only is given, so it can be fake photo can be given there. So the fingerprint can match. So if you take that type of fingerprints, you can see that how many people are traveling every day, many of the international airports. So it is very, very difficult to store and pass this information, checking with other things, a classification, for example, the matching and everything. If the file size is too large, it is not easy for the storage of this, and since we have storage of large number of images. So where we can use the PCA to reduce the size of the image without compromising the quality of the image. So how is it a possibility to reduce? So I just try to give a simple example here. So this is an image of the original image. So this dog, I just took a photo from the internet. So I took this image as my original image. Now I try to convert this image as a numerical data, the pixels. So then I can consider that as a covariance, there's an X matrix. Then I can do a principal component analysis on that and take few components of the principal components and try to reconstruct back the original data based on those principal components. Then I'll try to do it. So if I do with the 9 principal component, you can see the picture is just coming like this. It is not really good, but some similarity is there. So if I take the 22 pieces, so you can see that almost entire picture you can see is very tally, and if we match these two, you can see very easily this image is same. So now if you go to the 50 components, now at least you can see very clearly this is very close to that. So I'm just trying to use only 50 principal components of this original data. So how I did it, I'll just give you as a snapshot of what I did, but it is not sufficient, but I know, but we can convert any image in the numerical data using any software. So you may use a JPEG library in R. So in R software, you can use it and use the read JPEG to read the image file. So you have an image, you can use this command, reading this JPEG image, this command, you can call this image. So this conversion take the image data as a numeric in three matrices like R, red, G, green, and blue. So this is the color codes they're giving. So we can convert this in the 3 matrices. For example, the image I used in the earlier is converted to a 3 matrices of size 1333 and 20,000. So this is the size of the file. So this is a matrix, you see the 1333 and 22,000. So this is the size of the matrix, numerical matrix I'm getting for this image. And this is 3 because R is 1, G is 1, B is 1. Okay, so into 3. So this is the size of the image. Now we can use the principal component analysis on each matrix separately and select the number of components based on the cumulative proportion of the variance explained. So that is why I took 9, 22, or any number you can take it. Okay, so we can use this and arrive the PC score. So based on that, we can get the principal component score. Now, the main thing is that based on that PC score, for example, if I use this, so 2000 into 1333, so I reduced that, then I converting the 2002, this data to maybe 50 components. Now, I'm using that PC score, I'm going to reconstruct back the original data. I can do that. Okay, so set scores are there, then you multiply by the again. So X matrix, you multiply by the principal vectors, you get the scores. Now the score again, you multiply by the X matrix, sorry, the eigenvectors, you can reconstruct back that. So you reconstruct all of them, you stack it again, the 3, 1, the same as, then use the write JPEG command to get back the image. So have the data first, do the principal component, select the principal component, and reconstruct back the X. So that X and this X may be different. That is why you are getting different images. So the idea can be used also to video also. So this one, you can see that this method, what is the benefit is coming here. So if the full image I have taken, that one is 297 KB. Now, if I use the one principal component, only 71 KB is required. But if you take 22 or 16 images, so 16 pieces is 125. Or if I take the 50 principal component, it is only 169. So there is a reduction of 43% in the file size. But if you want the more clarity, so you can go from 50 to 100, then you get almost similar picture, but maybe you make a reduction only maybe 30%. So this way, the file size can be reduced using the principal component. Okay, so similar thing, we can also use it. So this is another, so I don't give you more detail here, but it is a turbulence modeling. So this is a currently work is going on with my student and another supervisor, another colleague. So it is the modeling of the turbulence. So you know the turbulence is very important, but very difficult to get the turbulence data. So there are softwares are available where we can utilize those software to generate some turbulence data similar to that. So for example, flow, okay, fluid flow in a tube, we can see it is how it is varying. So it is a 3-dimensional one, but we try to use a 2-dimensional one for this purpose. And it is a time components also there. So the flow is going on. So what here we use is the low eddy simulations. So we have generated a data, then we see how these fluctuations are going on. Then it is only around 100 seconds, or because the turbulence also, because we can look at that. Then this data is very, very huge data. And the principal component analysis can be done on that. Then we did the principal component, and the time, each time point, you can consider a variable. And this data can be converted into numeric. Then we use this first, you can see the first picture is showing a particular time shot image of a particular time point. I think it's 100 seconds. So now we use the principal component analysis, and we took only the 10 principal component of that, and we reconstruct back the image, and the picture at 110 is plotted here, the second one. So third one is a different approach using this principal. So we can see that with the 10 principal component, the first picture and second picture is almost similar. So the data reduction is very, very high here, because it is not easy that much data to analyze it. So, but if you convert it to a principal component and reconstruct it back, so we are very able to do this analysis, and even file transfer is possible. For example, if I use this in my home and I cannot send even the data through email or anything, it's so big data. Okay, so this is another work is going on, reducing the data, but without compromising the quality of the data using the principal component. And another application we just trying to do it here is the linear regression. So this is already, you can see some papers on this, where we can use the principal component analysis in the linear regression. So if you look at the linear regression model y, x, beta, epsilon, this is the standard regression model. So assuming that the X is the beta parameter we are estimating, X is the covariance covariate values, and Y is the independent variable. So if you want to reduce the variable selection, methods are available like AIC, BIC, or penalized approaches like SCAD and lasso. But here we are trying to use a PCA to reduce the dimension of the linear regression, that is the X matrix. So we can do the principal component of the analysis on the X matrix and take the lower reduction of the X matrix by a principal component score, and we can use it. So assume that covariates are continuous. That's the issue with that. We need to use the principal component. We need a continuous random variable there. So we can use the principal component on the matrix X and select important PC. For example, we can say X is a 90% variability is explained, then you can take Q principal component. Then we can select the K principal component, so where K is less than P. So P is the original number of variable. Now we can reduce that by K without sacrificing much, okay? And compute the PC score, set 1, set 2, set K. Then we can write the PC scores, the matrix as N into K said. Then you can fit a linear regression model, set delta plus E. Okay, so we can use another regression model now. Instead of the original variable, we can use the principal component score, and we can do that. So because you can see the utility here is the sets values are really orthogonal now, the principal component scores, so the regression have no issues at all. So the main advantage here is if the original covariates are highly correlated, so the multicollinearity problem can be easily solved by going to the principal PC regression, then it will going to be better. So then another option, another thing we are trying to do is the robust principal component regression. So where we know that in a regression modeling, the outliers is very, very problematic one, especially in the covariate value. So when you suspect that there is outliers exist in the covariate, then the regression parameter will be drastically affected. So one way is to remove the outliers and perform the standard regression. But how do you remove the outlier? So that's not an easy. So another approach we can do is we can use the robust estimate of the covariance of matrix X and construct the PC regression using the robust PC score. So you take the X matrix and use a robust estimate of the covariance, then we can use the PC regression on the PC. And we can use the reweighted MCD and reweighted MBE methods to arrive the robust estimate of the covariance matrix. So the idea is the mixing of this reweighted MCD, MBE type robust estimates and get the covariance matrix, then the multiply with the X and get the scores and use the principal component analysis, which are what you call robust principal component. So this is on robustness. So normally we know that the robustness is very important, and the mean is not a robust, and it is explained in terms of the breakdown point. That is the mean. If you take one value, then one value high or low, then you can see the mean is affected, but the median is not much. So the robustness can be easily explained by the breakdown point. So these are the two approaches on this MCD, MBE. So MBE is the estimate of the mean and the covariance based on the smallest ellipsoid containing a subset, at least half, of the observations. So you take at least a half subset, then finding out the estimate of the mean and the covariance. That is, the breakdown point is coming n minus p plus 1 by 2n. And the minimum covariance determinant is the estimate of mean and covariance based on the subset of observation having a covariance matrix with the lowest determinant. So you can choose just like a resampling of this, then you can get this one. So there are advantages are there, and there are reweighted versions of the MCD and MVEs are available. So this is developed by the Rosev and Somaran in 1990, and efficient and affine invariant and fast algorithms are available and also implemented in R. So we can use those, and this is the definition of the how do you calculate the X mean and covariance metrics of the original MEX, which are robust, using the, you can see the distance calculation is there. So we can use this, and how do you approach this now? So one approach is, again, I told you, is to use the robust estimates and use robust hot-linked T-square charts. So there are constructing the charts, hot-linked T-square charts are available. So using those charts, we can find out if any of these X values, the covariance values are outlier or not. So then we can remove it and perform the normal linear regression or a PC regression. So you can, if you want to look at more information about the hot-linked T-square chart and how we can utilize to find out the outliers, you can look at these papers. Chenouri and myself and Chiner is in 2009 JQT paper, and Chenouri and Warrior is in the Journal of Quality and Reliability, and again Warrior and Vatatur at 2014. Again, that's a paper in the Journal of Quality and Reliability International. So there's a package also available, raw PCA or robust base or RRCO library in R. We can use those, directly use the finding out the covariance matrix. Once you get the covariance matrix robust, then very easy to convert to eigenvalue, eigenvector, then we can reconstruct back the X matrix. Again, then you can use whatever the approach you want. And the second approach is to use the robust covariance matrix X, then construct the PC score and model PC regression. So we did some simulations, and we find that this method works very well. I'm not showing those things here, but we can use that. And the other application of the principal components are, they are usually mainly used for dimensionality reduction as a tool for supervisory learning. So it is a pre-processing, like, for the supervisory learning we can use. And there are applications of the PCA in fraud and anomaly detection in the financial sector. So there are, if you search the net, you can see a lot of applications of this PCA in the fraud and anomaly detection. So I summarize my talk. I think I trying to give you some idea where there is a good scope for using the principal component analysis. So most of the principal component analysis, what we learned earlier or standard books, normally reduction is there, but how to reconstruct back, then we can utilize. So that will give you real application where you can reduce the size and everything. So especially when you are looking at reducing the size of the images and the videos. And the PC regression also can be used to reduce the dimension reduction, but we are not using here as a tool for a variable selection here, because assume that all variables are important in the original regression. Now, then the PC regression is going to be much informative, and variable reduction is possible there, thereby improving automatically when you have lower number of variable parameters to be estimated, your error degrees of freedom is going to be reduced and the MSC is going to improve. Then together with the robust method, we can also robustify the principal component regression. I think I'll stop here, and if you have any questions, please. Over to
Thank you, Professor Ashokan. Any questions or comments from the audience? Please. Any questions or comments? Otherwise, let me thank. So this is in fact the end of this session. There were 4 speakers: Professor Niranjan Das, Dr. Kavirashu, and Professor Vittal and Dr. Ashokan. Thank you all for your presentations, and I thank the Dr. Dipesh Bhatti for the co-chair of this session, and also Professor Satish Kumar. Satish Kumar, please.
Thank you so much for your all the speakers. In fact, on behalf of the department and our associated societies, I hereby extend our gratitude to each one of the speakers of this session. Professor Niranjan Das, Professor Kavirashu, Professor Vittal, and Professor Ashokan. Very nice section, and it concluded in time. So the special credit to our Professor Jayagumar and for chairing this session in a nice way and concluded in time. Also, Dr. Dipesh Bhatti supported him in a very nice way, and both of them are to be congratulated. I utilize this occasion to extend our gratitude as well as congratulations to both the chairs and also the speakers. Thank you all. Thank you. Thank you so much. Now let us move to the next session in time. In fact, we have Professor Jijo is here with us from ISI. He is the man behind this session, a session on statistical applications in business and industry. Professor Jijo is the session organizer, and I would like to invite Joby Kejos also here, and Professor Jijo to chair, and Dr. Joby will support him as a co-chair. I invite Dr. Joby. Dr. Joby is here, isn't it? Hello? Dr. Joby? Joby, yeah. Earlier he was here in this group. Hello, Joby? Okay.
Earlier he was here, but then after some time he has left, I think.
Okay. Then I just mentioned some words, and later Joby will join and do the needful. We will support our Jijo. Professor Jijo is presently working in Indian Statistical Institute, Bangalore, and he is always well-wisher to our activities, our department and our activities. He's a very active researcher and active organizer in the research activities, research sessions. We all from I think 2015 onwards. He always support us in many of the events. Yeah, Dr. Joby joined.
Okay.
Yeah, Dr. Joby is presently working in the Kannur University in our Department of Statistical Sciences in Kannur University. He is also very active, young active researcher, and I would like to invite Joby to give a brief introduction to our Professor Jijo, and thereby you please do the needful to support him to the remaining proceedings of this session. Okay, Joby, you are.
Okay, sir. Am I audible?
Yeah.
Okay. Thank you for giving such an opportunity. Also, I congratulate the Department of Statistics, Kerala University, for organizing such a wonderful seminar. And my duty is to introduce Dr. Jijo, who is chairing this section. And he is actually working as the professor in the SQC and OR unit of ISI Bangalore. And he is very active in research, and his areas are reliability theory, quality management, and business analytics, etc. So with this small introduction, I invite Jijo to chair this section.
Thank you, Professor Jovi, and thanks to Professor Satish sir for giving us an opportunity every year in every conference for organizing sessions and things like that. It is very nice to see that in this pandemic time also, you are organizing such a big event with participation across the globe. Now, in our session, this session is on statistical applications in business and industry. So there are 4 speakers in this session. One is Professor P.K. Perimalu, then Professor Sriranka Bhatt, then Professor Vinayambika Bhatt, and Mr. KVSS Iyer. And all these speakers will talk about different applications in industry based on their experiences and research. First, I'll invite Professor Perimalu. Professor Perimalu, he was working with Statistical Quality Control and Operations Research Division of Indian Statistical Institute in Bangalore for a long time, and now he is retired from ISI. So he was very active in consulting in industry in various statistical tools and techniques, and he was guiding a lot of students, a lot of projects in industry, and he has rich experience in conducting a lot of live projects in industry. So now I request Professor Perimalu for this talk.
Yeah, thank you, Professor Jijo, and thank you, Satish Kumar. And it is an opportunity to again participate in your conference. As Jijo said, we are really thrilled that Kerala University and your department would organize such big events, and whether corona or no corona, it doesn't matter at all. So you have shown that. Very good. Yeah, I have chosen a topic which is related to the industrial application of these statistical methods. So I would like to share that on my system. I don't know whether it's coming or not. I think so.
Professor, you want?
Yeah. If I try to share, but window.
There is a small arrow button there. Yeah.
Yes. Now you can see my window. Everybody can see.
It is fine.
Okay.
Possible to make it full screen.
Yeah. Okay. So this is regarding one application of reducing the variation in some molding process. This is using Taguchi methods. Taguchi is a very prominent researcher, and he was very close to our institute in the past. He was a postdoctoral work he did in our institute in 1950s. Then he took some interest in orthogonal array experimentation, took it to Japan, and then made it very popular. So this is one application of his methodologies, and he added to what he has taken. Like Japanese always add some value what they take. He added value to the orthogonal array techniques in using his concept like quality engineering. He says that there are certain signal to noise ratio measures you have to use rather than general way of applying the statistical analytical methods like analysis of variance, and he has a different views about that. As we go along, I try to explain some of his thoughts in that and how it is applied in a physical world to get some improvement in a process. Okay, so there is a organization which is manufacturing switch assemblies.
I think you can put in the slideshow mode.
Huh?
You can put in the slideshow mode.
Slideshow mode. Slideshow mode is, this is what is slideshow mode only. This is okay, or should I go back?
Okay, fine. Go ahead.
Okay. So this is having this component called as roller W, which is one of the critical component in that. And in that component, the thickness of the component is very critical. And this part is produced by injection molding process, is a plastic type of part, injection molding process. The thickness, there is a lot of variation that result in when it is component is assembled in the switch assemblies, then switches don't function properly for a longer period. Okay, so there is a reliability issues as well as the quality issues for if the thickness is not properly maintained. So customer demand is about a rework level of 0.1%, but at present they are having very high rejections and a lot of rework as well. So 100% inspection they were doing, and they are doing the sorting so that only good parts are sent to the customers. So customer requirement is satisfied, but company gets a lot of rejections and reworks. So at present, the process is, if you take some data, and around 100 observations data is taken, and then we see that data shows that the process is a normal process, producing normal kind of observations. And you look at this, it has some specifications on this, lower specification limit and upper specification limit, the dotted vertical lines. And you see the distribution is very much away from the band of specification limits. So it means that there are a lot of rejections are happening. And you have some measures called as CP and CPK, which are the measures used in the industry, especially to compare the specifications and process capabilities. So these are called as capability indices, CP and CPK. CP is called as potential capability, and CPK is, I interpret it as achieved capability. You may have very high potential, but you may not achieve 100% of the potential. So it speaks about this, the graph speaks about this, how is the variation, a normal distribution. Fits quite well because it is tested for normality, and yes, it is.
Sir, that slide is not changing.
Yeah, it will change. Oh, it is not changing?
No, only first slide is coming now also.
Oh, wait a minute. Okay, this is the presentation mode. No? Is it okay now?
Yeah, it's okay. Yeah, now it's okay.
Okay. Good. Okay, so I am in this slide. I was explaining to you that this is a normal distribution tested, and it was found to be normal, not p-value is very high, more than 0.05. And within the specifications, it has very few observations, but outside specification, quite a number of. So you see at the bottom, you see that there is a ppm level, parts per million defect level, is quite high, around 25%. So the process is not capable. That's why they have to do 100% sorting and have a lot of rework because of that. Now the issue is how we reduce the process variation so that the process is capable, or CP, what you say CP here, you see in the right hand side, CP is very low as 0.56. So how we improve the CP means it is the ratio of tolerance, that is LSL, USL minus LSL range, divided by 6 times standard deviation. That is, we calculate the process capability. So that ratio is coming as low as 0.56. We expect it to be more than 1.67. The variation in the process should not occupy more than 60% of the tolerance. But it is occupying, as you see, it is more than 100% of the tolerance. So our objective is to reduce this variation, and also as you look at as a practitioners in the industry with respect to the process observations or the statistics related to the process data, they look at where the average is. You see, normal distribution, the average is very close to the lower specification limit. That is the reason why CPK is all very, very low. CP is a potential capability, but you have achieved only 0.22 out of 0.56. 0.56 itself is less, but you get much less than that. That is 0.22 only. So how do you set the target in the middle of the specification, and how do you reduce the variation? These are the two objectives of this improvement activity. So what is done is they discussed with the concerned experts, and then did some lot of research on the process. What are the variables which impact this? And then came out with 4 factors, named as these are the process factors: that injection time and injection pressure, because the material has to be pushed into a cavity so that it takes that form. And then after taking it is given at a hot condition, then you have to allow it to cool down, and then under some pressure it should be applied. So those are the 4 variables: injection time, injection pressure, cooling time, and clamping pressure. So these are the 4 variables considered. And for each of these variables, you have to do some experiments or trials to find out which are the best conditions. So they have taken 2 levels. So one is at a lower level, another is at a higher level, 4 and 7. Injection pressure 45 and 60 kg per centimeter square. Injection time is in seconds. Cooling time also in seconds, 13 seconds and 18 seconds. Clamping pressure 30 and 40 tons. Okay? That is the pressure at which it is material is flowed into the mold. So with these conditions, they wanted to try out one experiment. So the experiment they have chosen orthogonal arrays, and mind you, these orthogonal arrays are now mostly known as Taguchi designs. Okay. Though the orthogonal arrays are actually, the methodology was developed by Dr. C.R. Rao. So Dr. Rao has developed that in our institute in the 1940s, very early 50s, and late 40s, when India was going through the green revolution. A lot of experiments on the agriculture, how to improve the yield. So he was developing that methodology of orthogonal arrays, and Taguchi has taken that and then improved on that further. So here we have got 4 factors, and each of these factors are having 2 levels. So if you have to do in a classical way, that is full factorial experiment, you require to do 2 power 4, 16 experiments. In these 16 experiments, instead of that, he took only 8 experiments. It is a partial, or it is a in a full factorial design is a fractional factorial design, half fraction. So this fractional factorial design can be as also termed as orthogonal array design. He used that, and he has given something like some linear graphs, etc. So he converted the mathematical principles of Rao, Dr. Rao, to graphical principles, so that people can understand very easily. Engineers can understand very easily and apply these methods. So he developed that, and using that you can design the experiment very easily. So these are the, it has a L8 design, they call it L8, he calls it. That L8 design has 7 columns. Each column specifies 1 factor to change as given in that column. 1 and 2. Either 1 means first level, 2 means second level. So there are 7 columns. Out of 7 columns, these are the 4 columns chosen, so that there is no effect of interactions of the factors. So they were chosen here, and then the experiments were planned. So experiments were planned like this. You see, these are the 8 experiments. So these are the 4 factors: injection time, injection pressure, cooling time, clamping pressure. So these are conducted in a array. That's why it is called orthogonal array. You take any 2 columns, any combination appears only exactly equal number of times. 4 and 45 happens 2 times. 460, 745, 760. You take first and third column, also it happens. Any combination you take, it appears exactly 2 times. So it has certain properties, and it has a benefit because of that properties. So this experiment is conducted, 8 experiments with some repetition to see, replicate 1 and replicate 2. 2 results are taken, and then Here where the Taguchi's innovation has come, he created one measure of performance. He called that as signal to noise ratio, SN ratio. This SN ratio is, if you see in the next slide, we'll come back to this later. You see the SN ratio, this is the formula of the SN ratio. Eta is 10 times logarithmic value of average square by standard deviation square. Okay, S is the standard deviation, Y bar is the average of the performance. Average performance square divided by variance, this is the variance. This ratio multiplied by 10 times log, because in decibels you always express the in tens, okay? 10, 20, 30, 40 like that. So he's taken logarithmic, so he converted this variable into a kind of decibel method. And he called that as a signal to noise ratio. He considers here conceptually Y bar is the signal and variance is the noise, because it is not expected, not wanted, so it is a noise. And this is what is wanted, so it is a signal. So signal to noise ratio. This ratio should be as high as possible. When this value is high, it means the variance with respect to the average is very small. So related to average, the variance is very small. So that combination, that is what he wants to find. So if you go back to this, you look at this, for all these experiments, each experiment you have got multiple observations. These multiple observations, he found out that average by variance square 10 times logarithm of that. That is this way. So all these values are computed, and this is the standard deviation among these two observations, and the mean of these two observations. So those are the things which are taken, and each of these are analyzed using Taguchi's approach. Okay, here maybe I have to do some explanation, because Taguchi doesn't really go are very keen on doing analysis of variance. Normally these data are analyzed by analysis of variance, but he doesn't go by that. And he uses the other method called as delta factor. So data analysis for Taguchi signal to noise ratio, mean and standard deviation. For all the responses corresponding to each level of the experimental factors, the performance measures are computed, the signal to noise ratio and all that. The delta factor, that is nothing but difference for the two levels of each factor. That is, you see here, the delta factor is level 1. What was the value? Level 2, what is the value? What is the difference in these two values? Because when you change the factor to a new condition, new level, what is the difference that you have got? Whichever factor gives the large difference, that is the most important or more contributing factor. So actually we test it in ANOVA whether that difference is significant. But he says that, okay, whether it is significant or not, if one is giving a different value than the other, you go for the one which gives you best. If it is not significant, anyway, it doesn't matter. It says that, yes, both are same, coming from the same population. So you don't lose anything. If you gain, you gain, but if you don't lose, that's okay. So that is his concept. So he uses that delta factor, the difference. So results are shown for each of these three measures. So this is the formula, signal noise ratio. You see here with respect to signal to noise ratio, so this is the factor A, factor B, factor C, factor D. Now here, this level 1 of the factor A, we have done 8 experiments, and 8 experiments are repeated again. So you have got total 16 observations. Out of these 16 observations, 8 observations are from level 1 and 8 observations are at level 2. So he took all these 8 observations and calculated as per the formula here, as per the formula what is the signal to noise ratio. And for the second level, he again did the same. And he found what is the difference. That difference is 2.21. That is the delta. So for A, B, C, D factors, he found out what are the delta values. And he gives the rank as first rank is for the factor which has the highest delta. 8.9 is the highest delta. So that is the level, that is the factor he has chosen as rank 1. Next is factor C, that is the rank 2. Next is factor A level, rank 3, and rank 4 for factor B. So that is how he considers this ranking. So what does this really mean here? You see, this rank 1 factor B, when you change the level 1 to level 2, what happens? The ratio of average to variance is very high in case of level 1 compared to level 2. That means in level 2, you got either more variance for the same average or a higher average but the same variance. Variance has not changed but average has changed, or average remains same but variance has reduced. So he considers that ratio. So together, this is one very important and very useful measure in the sense, normally in analysis of variance, we consider only average, but we don't look at variance side. Variance, though we call it as analysis of variance, we see from different levels what is the difference in the average, and these averages we calculate the variance. But here we are taking the variance among the observations itself. That's what normally, if you continue the process to follow certain condition, you get a variation in that. That variation is what is reflected in this variance estimate. Okay. So keeping that variance, this factor gives very high value at level 1 than at level 2. The difference is 8.9. So he considered that as a rank 1 parameter. So in the same way he does for means as well for standard deviations. As you see here, with respect to means, the factor A is contributing to the highest difference. See, delta is highest, 0.201, and B is 0.019, C is 0.021, D is 0.026. So the rank is coming as 1, and factor D is 2, and factor C is 3, and factor B is 4. The rank is now different for these factors, same factors, the rank is now 1432 rather than, if you look at here, 3124. Okay. With respect to standard deviation, it is again 4, 1. This C and D has the same delta, so it is that 2 and 3 is distributed among these as rank as 2.5 and 2.5. Okay. Now we got the experiments, we've done the experiments, and then we got the results from the experiments, and then we analyze the experiments. Now we find what is the best combination, optimum combination for these factors. Here is what Taguchi's concept comes. I need to explain to you a little bit about this. What he considers is, in our problem, as I explained, we have two objectives. One is we have to set the target value to the matching to our average of our normal distribution. Our normal distribution process average should match to the target value, that is specifications in the middle of the specification. As well as we have to reduce the variation. So we have two objectives. Now, how he is trying to achieve these two objectives in one go? What he is trying is, if you use the signal to noise ratio, you are looking at the combination or the factor which gives you the lowest variance. Because for the same Y bar, if your variance is small, then your signal to noise ratio is high. So this is the factor which gives highest difference in the signal to noise ratio. So if you select level 1 for factor B, you get the minimum value for the variance. You are reducing the variance in the experimental results or the process variation. Then same way we follow for next is factor C, that is next one. You choose the best value for that, and factor A for because it's rank 3, factor D is the rank. Now, if you choose the best combinations with respect to that, what you get is the lowest variance, and whatever may be the average. Average you are not looking at. Considering the same average or different averages, but variance is small for that combination. Now, if variance may be reduced, but we have other objective also, that is, we have to set the process average close to some specific value. Okay, so how to achieve that? So he says you reduce variation by looking at the signal noise ratio measure and adjust the average by looking at the means. See, the rank for A is 1 in this case, means the average value changes significantly or very big delta for factor A. Factor B, it has high contribution with respect to SN ratio, but not the least contribution with respect to average. So what he says is, you reduce variation considering the factor B, take the best level with respect to SN ratio, and select the average in such a way that use the factor A. So you get the average adjusted by using factor A, and you get variation reduced by considering variation that factor B, or C and D also according to that. Okay. So he suggested that approach. So as you see here, we are not doing any analysis of variance in this case. We are looking at using the data, computing certain measures like signal noise ratio, or what is the mean for all the 8 observations in a group. So standard deviation of that 8 observations in a group, and then seeing what is the delta, level 1 and level 2, what is the difference it gives. So we see that, yes, the signal noise ratio, and here in this case it happened. In this case, signal noise ratio, B is first rank, and if you see the variance, standard deviation also, you see the B is the rank 1. So you reduce the variation by selecting the best level for factor B. And you adjust the average by selecting the level of factor B. So you achieve both the targets. Okay. Now this is what the average response curves. Okay. As you see here, B has the highest slope for level 1 to level 2. When you change, it has changed very drastically. That's why it has got highest contribution for me. Okay. Signal noise ratios also, first level to second level, big difference. That's why delta is high. So it is rank 1. So next is factor C, rank 2. Then rank 3 is A, rank 4 is B. With respect to average, means, so rank 1 is for A. So rank 2 is maybe for C and D, more or less same. And rank 4 is for B. For standard deviations, it follows more or less like SN ratio. So rank 1 for B and rank 2 for 2.5 for C and D, and then rank 4 for A. So using this, we select the optimum combination as for factor A level 2, factor B level 1, factor C level 2, and factor D level 1. Because factor A is affecting the average but not standard deviation. And if you look at the SN ratio wise, that SN ratio table, you look at that, which value gives the highest? Level 1 gives the highest. Here level 1 gives the highest. Here level 2 gives the highest. Here level 1 gives the highest. So 1, 1, 2, 1. 1, 1, 2, 1 should have been the best combination as per SN ratio. Okay. But 2 was taken because we want to adjust the average also. So that is why level 2 was taken to reduce the average. As you see here, this combination we can predict. In the orthogonal array, the advantage is, though we don't do 2 power 4 experiments, we can predict the expected value for all the 16, as if we conducted 16 experiments. So it is predicted for this combination, though it is not one of the experimental combination. It is seen what is the expected SN ratio, mean, standard deviation for this combination. So it can be predicted, and these predicted values are like this. So the SN ratio is so much, mean is so much, standard deviation is so much. And CP value calculated, that is the tolerance, which is the values are 9.8 to 9.6, is around 0.2 is the tolerance, divided by 6 times standard deviation, 6 and standard deviation. So that comes as 4.19. So earlier it was very, very low. So it can increase the CP value very high. What about CPK? CPK can be low because 9.6 to 9.8 is the tolerance, and the mean is coming very close to the upper limit, 9.76. So CPK will not be good. So we have to do something for the mean. Okay. So this is for another combination, 1, 2, 1, 2. This is what actually at present they were following, their process. In that process, the CP value is coming as 0.58. Okay. That is because average is 9.63 and the tolerance is 0.2 and standard deviation is so much. So because standard deviation is high, the CP value is very low. Now, specifications for thickness are 9.6 to 9.8. So if you want to set the mean at the middle of the specification, that is 9.7. So for optimum combination, as we've taken, it is coming as 9.76. So we have to select the combination or the value for factor A, because factor A is having highest influence on the average. So this value is not the middle of the specification, so we have to do something on that. So the average value is to be adjusted by adjusting the factor which has least influence on the signal to noise ratio, but has high contribution to mean. This is factor A, injection time. So for the injection time, the average values, we have fitted a function, a linear function, and then we found out which value of x, that is the injection time, will give you the average of 9.7 on the performance. So y should be 9.7, the thickness should be 9.7. So we found that x equal to 6 will give you this. The regression equation for standard deviation also is done, and then we see that for x equal to 6, the standard deviation coming as 0.0061. That x is fixed based on the target value we have to achieve. And for that x, that injection time, what is the value of standard deviation expected? That is this. So CP value for this combination is coming as 5.46, because now the value is coming in the middle of the specification. So tolerance is 9.8 to 9.6. Now it is coming. Okay. Now if you take the data, the trial is done, confirmatory trial. Some 100 observations have been taken and then plotted. Now you see it is a normal distribution and it is quite in the middle of the specification. I mean, close to the middle of the specification. Average coming as 9.70121, close to 9.70. And standard deviation is quite small, 0.01. So with that, CPK is coming as 3.23. So 3.27 was the CP and CPK is 3.23, because the average is close to the middle of the specification. CP and CPK are very, very close to each other. And your expected defective level or not non-conforming parts, it is dropping down to 0, because now the process is very much within the specification. So one is the capability of the process has improved, the rejections or rework are eliminated almost, and then we got the best process. And with what? We didn't go for any new innovation or new design of the process or new equipment. Same equipment, change the process conditions. Which conditions influence what? Then based on that, you can set the process levels in such a way that you get both average is adjusted to the middle of the specification as well as variation is reduced. So 2 birds at 1 shot. So that is what the Taguchi's approach is. Okay, so that is what I just want to present. And thank you very much for giving this opportunity. And now any questions, please. Yeah?
Any questions to speaker? Yeah, yes, you can ask.
Yes, very nice, interesting presentation. Very nice. What I want to know is, compared to the earlier rejections, percentage rejection, you said something, how much improvement has taken place on the acceptance level? How much rejection has come down?
25% was there earlier, now it is 0.
Okay. Suppose you convert into cost of quality.
Yeah.
Cost of not doing it right, something like that. It contributes to the profit of the company?
Yes.
Thank you very much. Very nice.
100%. Yeah.
Very nice presentation.
Yeah. Okay, thank you.
Yeah, any further questions to speaker? Then just thank Professor Perimalu for giving a nice talk.
Thank you.
The next speaker of the session is Dr. Sriranga Bhatt. He is a faculty at the Department of Mechanical Engineering at St. Joseph's Engineering College, Mangalore. He has a bachelor degree in mechanical engineering. He has a master's degree in engineering management, and he has a PhD in mechanical engineering. And he has published more than 15 articles in reputed international journals. His area of research is including Lean Six Sigma, robust engineering, reliability engineering, and design of experiments. And today the title of his talk is Lean Six Sigma Methodology for Sustainable Manufacturing in an MSME. So over to Dr. Sriranga Bhatt. No, you are not audible. I think mic is mute.
Yes, sir. Yes, sir. Sorry.
Yeah.
So we are grateful to Professor Jijo as well as the conference chair for providing an opportunity to delineate what we have learned from the hardcore statisticians. As I have mentioned or has been introduced from Professor Jijo, we are not hardcore statisticians, but we have learned something from the statisticians, and which has helped us to apply in some of the areas, especially in manufacturing side. So today I am going to discuss about, I hope my screen is visible, sir.
Yeah, it is coming.
Yeah.
Now it is okay.
Yeah. So today I'm going to speak about the Lean Six Sigma application in one of the small scale industry, which is situated in a tier 3 city. In fact, is situated in Bangalore. So as you know, Lean is all about lean thinking strategy, or basically it's known as Toyota production system. We evolved from Toyota company, and it has been termed right now lean thinking just because it can be applicable anywhere or even in the service industry. So that's why it is being termed as lean thinking. And you know that basically the lean thinking is going to concentrate on value proposition as well as circular economy, which is very relevant in today's era. Whereas Six Sigma is going to concentrate on the sustainable manufacturing, or a structured statistical methodology with which we are able to analyze the root causes. So when both Lean Six Sigma or lean thinking and Six Sigma will be combined together, it is going to give the result in a much faster manner, and it's going to leverage the potential of both lean thinking as well as Six Sigma. And ultimately, as we have mentioned earlier, it will create value proposition and circular economy through sustainable result. So here we are going to use both lean thinking strategy as well as Six Sigma, basically some of the statistical tool to improve the process. So this has been applied in one of the small scale industry, which was manufacturing polymetric membranes. And in fact, the industry was very small, I must say that it's a micro industry. That's why I have termed it as a MSME, micro, medium, and small scale industry. So we have started with the DMAC phase. So in the first phase, in the Lean Six Sigma strategy, we are going to define the project and we try to quantify it. And here we are going to specify what is the project charter, with which everybody will come to know what is their roles and responsibilities. Then we are going with SIPOC, which is going to give an idea how exactly the process is going to follow. Then we are going to come down to CTQ tree, so that is critical to quality tree. And finally, we are going to culminate the first phase with the CTQ specification table, with which everybody involved in the team will be getting an idea how to proceed further. The next phase, in fact, we are going to have a comprehensive data collection plan. Then we are also going for a measurement system analysis. If it is a continuous data, we are going for gauge RR, or if it's a discrete data, we are going for a kappa analysis. Then of course, as per the statistical requirement, we are going to test the data. If it is going to have normality, then we are going to carry some control chart, and we are going to see whether it is within the statistical limit or not. Then we'll be getting into the process capability analysis. Once we are able to establish the process capability, we will come to know at what stage the company process is standing. And in the business terminology, we are going to say the baseline status can be established through this particular stage. Then we will be getting into the cause and effect analysis or diagram, through which we are able to do the root cause analysis. So of course here we need to use both the tools of Lean as well as Six Sigma to make sure that we are going to arrive at the solution quickly. And in the improve phase, we are going to try to generate the solutions with the risk analysis as far as possible. And in fact, in this particular case, I have gone for mixture design of experiments. And of course, I have gone for ANOVA to get a validation of some of the root causes. Then at the end, we have generated the solution and we try to sustain it. Then we have measured to what extent it is been improved. So as a first phase, in the define phase, as I have mentioned, we are going to categorically define the entire project. And we are going to express in a quantifying factor. So title of the project was basically a study on the implementation of Lean Six Sigma methodology in a polymetric waterproofing membranes industry. So we thought basically the tensile strength of the material is crossing the required specification limit, and because of which rejection is been happening. So while doing some preliminary study, we came to know that in fact we were able to take this data from the next phase. The process was at 1.82 sigma level. I will explain how we have arrived at that point. And aim was to improve to higher level. Say for example, benchmark was 4 sigma level. And this project basically was carried out through my students. Of course, the company is too small that they are not able to do the project, but they have assisted us whenever we have given some of the design of experiment table, they were able to perform it. So then in the CTQ, that is critical to quality, is being defined as tensile strength, and specification limit was defined by the company 138 to 142 Newton. Then anything crossing that limit can be taken as a defect. Then we have defined when exactly we need to complete the project. So once that is done, we have gone through the process, how exactly is happening, one of the industry, Bitutech industry in Bangalore. So bitumen will be added and it's been heated to 50 degrees Celsius. And of course, the temperature was varying at certain point, which we have observed in the later part. And some additives also been added, tar and polymer. Then in the mixing chamber is getting mixed with the limestone powder as a filler. Then they are going to laminate using one of the machine. Then the polymetric waterproofing membranes is going to come out. So that is what the whole process that is happening in the industry. Of course, workers are, I must say, not even semi-skilled. There is a lack of skill. They are going to hire directly those who are going to clear 10th or 2nd PUC, since it is a very small industry. So then we have gone for SIPOC, supplier input process output chart. So here we try to understand for a particular process which we are studying, what is input and what is output, and going beyond, who is supplier for that, who is customer. So if there is any problem in the supplier side, we are able to fix it. As you know, quality is very important from the perspective of supplier. The incoming quality is good, we are able to deliver in a much better way. So that's why to that extent we are getting not only from input and output perspective, even from the supplier and customer perspective. So then we have generated a CTQ tree to understand whether that is really important or not. So need of the project is to reduce the rejection, and driver for that is nothing but treatment and lamination process. And CTQ was dimension, especially the tensile strength. And we have not concentrated much on the dimension as tensile strength was one of the major requirements there. So then we have specified our specification table, as you can see. So with which we have completed the first phase. In this first phase, the people as well as like managers or team who are involved, we are able to get some idea what is happening in the industry from the statistical perspective. Then we have gone for a measure phase. In the measure phase, we have gone, specified what should be the data collection plan. So once we have specified the data collection plan, basically we have gone ahead with the gauge RR study to make sure that the measuring equipment is proper. So we have taken 5 specimens and 2 operators were selected. Each operator measured each specimen 4 times and the tensile strength values were recorded. And since the total gauge RR value is within the specification limit as per the standard, that is 30% should be the standard maximum acceptable limit, whereas we have got the variation as 10.85. So that's why we have come to a conclusion that the measurement is measuring system is proper, so with which we can proceed further for the rest of the analysis. Once that is done, we have analyzed the data that we have collected and finally found that it is following normal distribution. So once we have culminated with this particular point, we thought we have to go for the capability analysis. From the capability analysis, we have found out that basically the parts per million rejection is nothing but 3,76,991. And from the Six Sigma table, we will be able to comprehend that it is there at 1.82 sigma level. So this has helped us to understand or to specify the baseline status of the current process. So once we have done this, then we have gone for a brainstorming session with all the people, even the layman or the end person who is working in the industry. His concern was taken into account. So they were randomly giving some of the causes for a particular problem. As you can see, in some way, some of the people are saying the people are not working properly. Even that we have considered, and we have termed in a business language the lack of positive attitude. So everything has been taken into account without, we have not rejected at the first point of time. We have gone for a cost validation plan. And we try to validate through quantifiable factor. So here we have segregated into two parts. One is that the potential causes on which we are able to collect the data. And we thought those things can be validated through some of the statistical methodology. And some of the potential causes which we are not able to collect the data, that reliable data, we thought we are going for Gemba methodology. That is one of the lean principle. Through the Gemba methodology, we are able to culminate whether it is a root cause or not. So in the Gemba analysis, a specific cause will be observed for a specified period of time. And if the frequency of happening is more, then we can culminate that it is a root cause. However, in the statistical methodology, there is a specific the benchmark or limit upon which if it's going to happen, we are going to accept the hypothesis or we are going to reject it. So you can see in my table, variation in temperature. So we thought that we will go for ANOVA because most of the time it's not happening in the proper sequence. Observation goes beyond the specification limit, and we have observed 25 times out of that it is going beyond. So that's why we thought we are able to get the reliable data and we will do a ANOVA for that. In the similar manner, the composition, there was a problem with the composition because there is no specific limit set. Even though there is a limit in the engineering manual, the people are not following properly. That's why we thought it is not giving the ultimate result that they are expecting. So for that, we thought we will go for design of experiment. Since it is a composition, we thought we will be going for mixture design of experiment over here. Then we also thought we need to measure the variation of the structure, which is Martin's state, as per the specification from the R&D, from the external R&D department. We have confirmed, so that it was not a root cause. In the room temperature also it's constant. It is also not a root cause. Then humidity was also not root cause. We have observed. Then repeatability and reproducibility, that is gauge error study that we have already performed. That was also not a root cause. But there was a problem with the maintenance because there is no standard procedure they were following, because of which they're having lots of problem with the machineries. Then skill was also not root cause, and positive attitude. We thought that based on our observation, we thought it is not a root cause at all. So whichever we thought we have to study further, especially ANOVA as well as DOE, we have gone ahead. So we have taken a data on 3 different temperature, and we have seen there is a huge variation when the temperature is going to vary. So we have come to a conclusion that the variation in the temperature is a root cause of the outcome. Then, in fact, we have gone for, in the improve phase, we have gone for mixture design of experiment. So here we have randomized the entire table. We have taken a range. In fact, for polymer, we have taken a range from 10% to 15%. And for the limestone, we have taken a range from 30% to 33%. Then for bitumen, we have taken a range from 55 to 60%. So when we have given this data into the Minitab software, it has generated the experimental layout. For each experimental run, we have taken 3 replication, and it was randomized. And based on the experimental analysis, we found that best composition for the polymer is 10.2%, and limestone is 31.17%, and bitumen should be 58.64%. So based on this, we have proposed that if the composition is set in this limit, the tensile strength will be as per the specification. In addition to that, because there is a lack of maintenance, we have given a simple table of 5S lean audit checklist, where sort, set in order, shine, then some simple standardize and sustain were there, which was helpful for them to do some sort of audit at least every month, just to sustain what they have achieved. In addition to that, we have given a lean audit checklist to make sure that the wastes are minimum in their process. With this, with all this solution implementation, in fact, we have also given waste analysis sheet for the industry, and basically we are going to term it as downtime. D stands for defects, overproduction, waiting, non-utilization of talent, transportation, inventory, and motion. So if they are able to audit this one from time to time, probably even if they are able to address some of the other issues, for which no need of going for Lean Six Sigma as a hardcore philosophy to identify the solution. Then finally, after implementation, we found that it has been improved at the tensile strength variation, and DPMO was around 62,395, and Six Sigma limit was improved from 1.82 to 3. So that was, even though it's a small improvement, we found that in a mediocre industry which is not following any rules and regulation, more or less is there only in the manual. For them, it was a substantial improvement because they were able to do the things in a much structured way. So we would like to conclude in this way. Though Lean Six Sigma methodology, the objective was met, being under the limitation, the results of implementation of 5S and the tools of LSS was that the rework were reduced largely. Thus, by resolving the root causes of the reworks, sigma level rose from 1.82 to sigma level of 3. The major outcomes of the study are the principle of 5S, which is a loon tool, was effective technique, helped us to improve the system. And also DMAC, we found that DMAC is one of the very prominent phase with which we are able to execute this project. And finally, we thought that even, of course, it is very difficult to train the people who is not aware of anything, but we were able to execute the project through our students. But we were able to correct the data. So this indicates that even Lean Six Sigma can be applicable in a small scale industry when there is an interaction between academia and industry, with which we are able to help them to improve their production. So that's it from my side, friends. If there is any question, I'm happy to answer.
Yeah, any questions to speaker?
Yes. Sir, can I ask you some small clarification?
Yes, sir.
Yeah, sure.
Sir, the presentation was excellent, very nice, very relevant and interesting. What I want a clarification is the tensile testing machine you are using, it is calibrated. Isn't it?
Yes, sir. Yes,
calibrated.
sir.
They also issue a calibration certificate.
Yes.
Now, what I want to know is, when they are issuing a calibration certificate, they also expand that uncertainty at 95.45%.
Okay.
Am I right or wrong?
Yes, yes, sir.
They are giving. How do you apply this information in the calibration certificate on the measured values so that the actual values exceed the component will be available?
Okay.
Why I'm asking this question is I was trying to find out, nobody gives an answer. I checked with some of the calibration experts and with some examples, they said when you minus the expand uncertainty from the measured values, that should be the value taken acceptable values. Because when you apply this one, it can be anything between the plus or minus of the measured values. That is the explanation they have given me.
Okay.
That's what they have given in the literature also.
Okay.
Now, what is your experience?
Sir, actually, that's what, sir. In most of, even when we are going to conduct some of the experiment in our laboratory for the materials, we actually won't conduct, to be frank, a gauge error study, because human interventions are very much minimum. And we know that the person who is taking the reading, he is expert in that because he is handling only that particular lab. But in the industry, because the persons are not proficient, to gauge their proficiency, it might be the gauge error will help.
I agree with you.
Yeah.
I also take measurements. I am not an expert. Expand uncertainty, what I do is I go to the laboratory.
Yes.
Laboratory, there is an expert who has been certified by NABL for his competence level for assessing the expand uncertainty and advising the users what is the use of these measurement information given in the calibration certificate.
Yes.
So when I ask the lab, he will tell me, look your friend, if your measured values are 170 and expand uncertainty of 2.75, you can accept it only up to 165. Now, can you reject? He said, no. You have to talk to the customer. What is the criticality of these characteristics for application? By chance, it is 175 or 160, then it goes in the rejection. It's a question of assumption or chance cases, or as you say, probable, and not a confirmed case. But in any case, you are not agree. You must not accept it. Thank you, sir. Very nice presentation. Very good.
Any further questions? For others, let us thank the speaker. Now, the next talk is by Dr. Vinayambiga Bhatt. Dr. Vinayambiga Bhatt is working as a professor and head of the department in Electronics and Communication Engineering at Mangalore Institute of Technology and Engineering. She has received her BE degree from Malnad Engineering College and MTech degree from NMAMIT, NITI, and PhD from Manipal Institute of Technology. Her research interest includes advanced control engineering and robust control engineering. And she is going to talk about optimization of PID control parameters using Taguchi's robust engineering approach. Yeah, over to the speaker.
Yes, thank you, sir. Good evening, one and all. Today, I am going to present you before my research on optimization of PID controller parameters using Taguchi robust engineering approach. So these are the content of today's presentation. So my objective of the work here is to control the speed of the motor. So we all of us know that the DC motor is one of the major equipment or the major device which is used in most of the industries. So the effective control of the motor is very much essential in order to achieve the better performance and also to reduce the cost. So in this regard, significantly we need to identify a good controller which can take care of all these parameters. Now, when we need to control, so we need to control in order to achieve a stable response or stable output. So there are different parameters which is getting added into the system whenever we want to achieve a better performance. Something like noise. So that may be an internal noise or external noise. So in general term, in the industry, if I speak about with respect to a process industry, the disturbances also getting added into the system other than the noise. So our aim is to take care of all these things. So during the simulation study, we consider the mathematical model of the system. So when we have the mathematical model, when we really implement it the real time, certain level of disturbance or certain level of deviation in the result also can be seen. So in the present study, I'm also going to consider the uncertainty. What do you mean by uncertainty? Uncertainty means we are having a system, but we are able to get a better output within that limit, wherein which the parameter variation is also not going to affect that controller performance. So here I'm going to consider two methods. One is based on IMC, that means internal model control algorithm, and Taguchi method. So here, as per my title indicates, it's a PID controller. Here P stands for proportional, I stands for integral, and D stands for differential. So as I told you, the uncertainty is also being taken care here. So objective are, these are the major objective here. So what are the challenges? Now, most of the process industry, to control, they use PID control algorithm, which is a conventional way of controlling any system in the industry. Now, even though there are many advanced control algorithms or optimization methodologies are available, still 90% of the industries go for PID control. That is, the reason is that it is simple and easy to understand compared to any advanced control algorithm. And also there is a lack of understanding in case of the advanced control algorithm is also. That is the reason why PID, it is a tuning methodology. So based on your expected output or what is your target, based on that you need to identify your controller value. And also our aim here is to attain the result, expected result, even in the presence of uncertainty. So here I am going to consider two methodologies. That is, it is taking PID itself as a base with the Taguchi and without Taguchi approach. So this is a general block diagram of a DC motor. That is direct current. That is a DC motor. So this is the input, that is acceleration voltage it is, and output is a angular speed, that is speed omega, which is always measured in radian per second. Now, this is a simple block diagram which represents the motor. Now, using the block diagram reduction technique, a transfer function is being determined. So this is GDCM indicates the model of a DC motor. So there is a separate methodology. By reducing that, by using that reduction technique, we can find what is the transfer function. Now, in real time, we are not going to work on the transfer function. We are going to implement the algorithm on the real time. But to proceed with the analysis, real-time analysis, we need to analyze the algorithm or simulate the algorithm with the help of the mathematical model. So this is the mathematical model which has been arrived using the reduction technique. Now, moving further, this is a simple closed loop system. You can see this is a simple closed loop system. So R of S is the input and Y of S is the output. This is my system, that is DC motor mathematical model. Now, I need to design a controller to achieve the better, significant, stable output. Now, I have also considered the disturbance here, okay, because disturbance is also a major parameter which need to be taken care in the process industry. Again, the disturbance can be a load disturbance or input disturbance. So in the present study, I have considered the load disturbance. Now, the feedback is given, which is a negative feedback. Now, what I am obtaining here, you can see here, what I am obtaining as output of this summation, that is my error. So my aim is to control the error. If the error is 0, whatever the target I am setting, that can be achieved. If the error is not 0, I need to control. I need a controller so that it will make the error 0 and I will get a desired output. Now, this error can be of 3 types. One is proportional. That means immediately we are getting what is the error. One is because of the future we are expecting some error because of when a mission is running for a long time. So if there is any small deviation in the process, that if it continues over a long period, the error goes on adding it, right? So that is what is that integration. That means it is getting added. And then we have a derivative controller also that will take care of the past error. So 3 times, what I am designing is a PID controller that will take care of the present error, past error and future error. So mathematically it goes like this: proportional, integral and derivative. So in this study, I am considering 2 methods. One is IMC PID and other one is Taguchi PID. So IMC PID is basically based on the mathematical model of the system. So I have directly taken here the mathematical model. So this is a mathematical model. This is how my PID controller look like. PID. So proportional, 1 by S, that is integral, S into KD, that is our derivative term. This is with respect to the mathematical concept. Now comparing with the standard equation here, these are the P, I and D values can be derived from the mathematical model. So you can see here, this is a one proportional controller, integral controller, derivative controller. These are function of the DC motor parameters. You can see here L is an inductor, J is the inertia, R is the resistor. So these PID values are depending upon the system parameters. So that is the reason why it is called as internal model controller. Based on the model itself, we are finding a controller. Now, in the study, we are going to have 3 methodologies. One is system design. So considering the spectrum of parameters and different levels, then parameter design, we need to design the parameter and ensure that there is a least variation in the source. Then the tolerance also need to be taken care to achieve the better performance, better stable closed loop performance. So methodology goes like this. So I have taken based on some of the specification of DC motor, this transfer function is being arrived. So once the transfer function is being arrived, for my convenience, what I have made it here is that this is a second order transfer function. We can see that it is a second order transfer function. So K divided by A into S square, BS plus C. Now, whichever the DC motor I am going to consider, it is always a second order, only based on the specification of the machine or the motor, my K, A, B and C value will vary. Rest all will remain the same. That means based on the system parameter, these values will be varying. So this is a standard approach I am considering to proceed with the algorithm. Now, using PID tuning methodology, we could identify the PID values. This, how did I get these PID values? What I have done is here, you know, we have the specifications. KP is determined using the system parameters. Here also, this lambda is a tuning value which need to be tuned in order to achieve the stable closed loop performance. So that is how we could get the nominal PID values from the system parameters. Later on, we have identified the level for the controller as well as the noise factor. So a range is being fixed. So based on this range, we have 3 levels. Now, this is the nominal parameter of the mathematical model. This is the nominal parameters. In most of the industry, the article presents, the literature says that we can permit up to plus or minus 10% uncertainty, because what I am analyzing is on the mathematical model. When I implement it in the real time, there may be some noise factor, disturbances getting added into the system. Because of that, the controller what I have designed for that particular model may not work. So in this case, I need to analyze the performance even with a variation of certain x plus or minus x variation. So normally a plus or minus 10% uncertainty is permitted. So with that condition, so this is the nominal parameters of the model, then considering plus 10% and minus 10% uncertainty. That is the generalized parameters of K, A, B and C of mathematical model. Once it is been designed, then we need to select the appropriate orthogonal array and assign the process parameters to it. Then we need to conduct the experiment. So here we have done the simulation study using MATLAB in the Simulink platform. We have every time we have run the algorithm and determined based on that we have analyzed the result. Now here in control engineering aspects, there are different, I'll go to this diagram, okay. So in the control engineering aspect, we analyze the stability of the system based on few of the specifications. The specifications goes like this: how fast your system is getting settled or getting stable. That is one of the parameter. Because the faster I get stable, my response is, my output is better. Second one, if a disturbance is getting added in between, you are working in a stable condition, I am adding some disturbance. How quickly you are going to settle? That is a second specification or the constraint which need to be taken care in designing a controller. And the third point is there is any oscillation? I am settling, but we having n number of oscillations. If I settle, that is also going to affect the system performance. So that also we need to identify. And in process industry, there are 4 errors which we need to minimize. So here in this study, I've considered one of the error, that is integral square error. Integral square error indicates a system or if a process is running for long period, the error in the 0 stage, if I count the error in the nth stage, it is getting added. So integral square error should be minimum as far as possible. And there are other criteria also: integral absolute square error, integral time square error. All these are the there are 4 performance index which they study to analyze the performance of the system in process industry. Then settling time. Settling time is also one of the major constraints which we need to understand, and also we need to obtain as minimum as possible. So that means how fast the system is getting settled in the presence of disturbance or without disturbance. Generally in control engineering aspect, we calling it as regulatory response and servo response. Regulatory response adding disturbance, servo response without adding any disturbance. So in the study, these are the 2 specification which is been taken into consideration. One with the IMC PID approach and other one is Taguchi PID approach. So by performing the simulation, this is the value what we could obtain for minus 10% uncertainty and original planned model, and with plus 10% uncertainty. Now here you can see we have studied using Taguchi whether there is any interaction, what is the level of interaction, that also been studied across the table. Now you can see here that this is a response what I have obtained in the MATLAB Simulink platform, that is the process output over a period of time. Now here the blue color wave that indicates Taguchi PID, you can see that response is settled fast. The settling time is fast. Settling time is, see, I have set a target of 1. How quickly I am reaching that target. So that is decided by the settling time. So in comparison to these two algorithms, the Taguchi gives a significantly improved settling time compared to IMC PID algorithm. And also, see, once it's settled, both the responses are settled, then a disturbance is added. You could have seen in the earlier slide, I had used a block diagram with a disturbance, low disturbance. So added a disturbance, whether the system is settling or not. Sometimes this will not happen. If your control algorithm Turing is not proper, then what will happen is the system will go on oscillating once the disturbance is added. So that also need to be taken care here. So the response is analyzed under both servo and regulatory response. So conclusion here, so optimal value of control factors has been identified. So settling time is also reduced with the Taguchi approach. Then also taking into consideration of the load disturbance, the performance is also been analyzed. The optimal value of the controller using Taguchi robust engineering approach resulted with faster settling time and also minimized error. That means I have analyzed with respect to integral square error. So we can compare here. So this is the table which present that. We can see that the settling time is reduced compared to the IMC PID approach, and also the error, the integral square error is also significantly reduced compared to the IMC methodology. So now further we can extend this work. This is, we have considered a single input, single output system. Further, if you go for multiple input, multiple output system, there are several challenges like the matrix, the MIMO system, the complexity, mathematically also it increases, and controlling parameter also increases. The levels also we need to take care. So that is a challenging task. And the second thing is, if it is a non-square matrix, if your model is a non-square in nature, that means you have 2 input, 3 output, or 3 input, 2 output. In such case also it is, controlling is a challenging task, wherein which we need to identify a better optimized technology, methodology in order to have a optimized value so that the result, better result or the better target can be achieved. So because we know mathematically we cannot directly apply the inverse, because wherein which in several algorithm which we come across in the control engineering aspect, we have the concept of inverse to find Laplace inverse. Because if you have, we don't analyze any system in time domain, we go to Laplace domain, wherein which we need to go for the inverse. So this non-square system will not have the concept of inverse terminology. So that also needs to be taken care. So further study, we are planning to go with the multiple input, multiple output system. So these are the references. Thank you. And I would like to extend my thanks to the organizers and also to the Professor Jijo for giving us an opportunity to present our small bit of work which we are carrying out. I thank you. Thank you one and all. Any query?
Any questions to the speaker? If there are no questions, let us thank the speaker. Now, the next speaker is Mr. KVSS Iyer. He is an engineer and was working with BHEL for 37 years in quality and project management and retired as a senior manager. And he has published many articles related to quality and now working as a freelance inspection engineer. He is talking about Ishikawa diagram, a diagram of logics for analysis of anything and everything. Yeah, Mr. Iyer, over to you.
Has it come? Yeah. Is it not coming, is it?
Yeah, it's coming. You can show your Excel. Yeah, you can open your presentation.
Okay. What happened? Nothing is coming, is it?
Yeah, it's coming. You can open your presentation. Screen
I
share.
have opened it. I have opened it.
The screen
But
is
it is
shared.
coming.
Yeah, no, but your slide you are not opened.
I opened, I have shared.
Your screen only shared.
You have to select the entire screen instead of
entire screen. Okay.
select your entire screen. That's better. Now it is coming.
Coming.
But yeah, but again, yeah, you have to move to slides. Open the slide or move to slide. Yeah. Now you can open the, yeah. Yeah, it's coming. It's
coming.
Yeah, that is fine. You can make it full screen or slideshow mode.
Okay.
Yeah, it's coming.
Can you see?
Yeah, it's coming.
Yeah,
You
it
can
is
start.
okay. It is okay.
It's all right. See, I am very weak on this business.
No problem. You can start.
Okay. Okay, sir. So thank you very much. Salutations to and namaskar to University of Kerala, Trivandrum, and all the participants. 5th International Seminar on Statistical Theory and Applications. Now, my special thanks for the Indian Statistical Institute for giving us company-wide training program for a period of 10 years. The topic for today is Ishikawa diagram. Yeah. Ishikawa diagram, a diagram of logics for analysis, the series of whys and responses for anything and everything so universal, a case-based diagram, visual-based exploration. Right questions are more effective than right answers, as right questions drive us to further inquiries and exploration till the truth, the reality is established, whereas seemingly right answers put us to dead ends. Ishikawa diagram, named after its author Kaoru Ishikawa, the Japanese scientist engineer, popularly known as the cause and effect diagram or causal diagrams, indicative of what they do. The fishbone diagram or Ishikawa diagram, indicative of its form and shape, or the herringbone diagram, indicative of its pattern, as shown here, are the diagrams of responses to voice. Is the diagram of logics consolidating all the factors coming into play, leading to the creation of effects or the consequences or events against our own will, or displeasure and miseries, or even very much in advantages to us, being the reasons for our growth and prosperity. A series of whys and responses get to the root of the problem, or thrills and excitements for corrections and corrective actions, or positive reinforcement actions as applicable. Statistics and statisticians have become so involved with very simple but very effective problem-solving tools in every business processes, not to speak of quality control, quality assurance, and inspection processes, that a basic understanding of application of statistics and statistical tools, more specifically the Ishikawa diagrams, become an indispensable part of any business process, so also training curriculum for business growth through customer satisfaction. It facilitates arriving at the exact root cause for failures, defects, defectives, leading to purposeful and meaningful corrections and corrective actions, so also positive reinforcement actions as applicable. While being so, it also helps figure out the exact risk involved in any strategies or actions, enabling elimination of such risks and realizing the purpose of actions in total. Consolidation of all the factors in a visual, logically organized influencing an event with and through a team of expert, experienced professionals, through a system of brainstorming, is the hallmark of these diagrams, making them very popular. The paper explores with examples from the lines the wide applicability of these diagrams for daily practice for performance, effectiveness, and growth of the business and institutions. The cases are real. It's a typical cause and effect diagram. Any process you're looking for efficiency or effectiveness, performance, there are four factors are influenced, popularly known as the 4 M's. First is the method we are using for do the process, which more or less is the process specifications, which can be a published standards by institutions like BSI, IS, or so and so, or the old specifications, a dedicated specifications for the purpose. The materials, even the method is perfect, materials are wrong, then we will land in the problems. So material specifications and the conformance to material specifications, a major factor. Third one is the people who are working on the job, qualifications. Every job, every process needs a qualification of the man for the process, whether he is qualified or not. Especially in case of special processes, which are defined in ISO 9001, like the painting, fabrication, welding, soldering, or the bracings. All the processes, there is no different method of evaluation. So process owner, the task man should be qualified purpose, and there is a system for qualifying them. Then the machines, what we are using, for is it able to hold the process or not, process capability, so that it can hold the tolerances specified for the purpose. Now, all these factors and control within the limits are conforming. Then what happens? There is a process, there is a customer satisfaction. What the customer ordered, he gets what he wanted. The result will be repeat orders and business growth. In case there is non-conformity, it leads to customer complaints, then there is a loss of customer, business decline. Now, next I have shown a diagram. There is a lot of discussions on the Taguchi's proposals. What I have taken is one part of that, a loss function. What he says is, any deviation from the basic values on the actual is the reason for loss for the customer. And this loss also identify is proportional to square root of the such deviations. That is assumption, that is the inference made by Taguchi. So as much as possible, the actual should be as close to the basic value. Now, what is this basic value? Is it the design value? No, it is not a design value because there is a design quality also involved. It is a basic value or ideal value as it required at the site of installation, commissioning, and erection. That decides how much it is. Now, when you look at it, now I have got an example for this one. Srinivasa, he has written a book, Chronicles of a Quality Detective. He says in these 8 cases he had nicely quoted, what he says is, a profound knowledge as proposed by Deming. Now he quotes an example. The Ford Motor Company, they had a steering systems, transmission system connecting the engine to the back axle or differential. These, whatever it is, 50% of them, the Ford Motor Company ordered a Japanese firm, and 50% they are an American firm. The author says there was a big rush for the automobiles fitted with the transmission system received from the Japanese factory. Now, what is the root cause? He says the Japanese firm, when he got the specification standards, all the tolerances and the dimensions and properties, they generally made it 50% halved it. After halving, they introduced a strict process control system so that the deviations will not take much over the period of time the processing. The result was actual dimensions or our properties in the components tend to fall very much closer to the basic values. Of course, he talks about the design values, not the actual values at site. Considering the design is perfect. Now, as a result of these deviations from the actual values, deviation with the basic values, there is an impact on the customer experiences. It's a Kano model. He described the experience of the customer, 5 different levels out of 3 I have shown. If the item is exactly matching to the specifications, as a tensile strength 150 is coming, if in these limits of acceptance, it is acceptable. But it is not satisfying the customer because his expectations are not basic. And again, when you are checking second time, the 150 can go in anywhere else, depending upon the instruments used, person using, etc. So it should be always be more than what he specified in the drawing. Now, there is a satisfaction level which the customer has an expectation, which is not exactly given in the drawing, but much more than that. If tolerance of 100% is given, 198 to 102 is okay, but as customer is concerned, he is expecting much closer to 100 or 101, 99 like that, even though that he cannot claim from the vendor. Now, as a result of the deviations or customer experiences, what follows is a corrective actions based on the plan do check. When you are planning, we do the process, then check. Check is coming from the feedback from the customer. We analyze why it has happened. It is here we use these cause and effect diagram extensively. All the factors influencing the process parameters are studied, analyzed, and pinpointed what exactly the cause for deviation to the dissatisfaction of the customer. Now, here, typically when you say quality of a product, it is defined in terms of quality of design and quality of conformance. A design which, to what extent it reflects the actual requirement at the site of installation, that decides quality of designs. It's based on study of the customer needs, specifications, and he draws up a specification based on what customer is looking for, validate the specifications by testing, prototype testings, or qualification of prototype testing, or type testings, which proves in a condition which is prevailing at a site of operation, the product will perform satisfactorily for the period which is guaranteed as a life for the customer. Reliability, which is there are systems of standards available how to test these products in various conditions like temperature or humidity or vibrations. All parameters which are affecting performance at a site of installation are simulated in a simulating chamber and tested. Feedback analysis for the customer for the first period, contractual period, or over a period of time, analyze and design reviews takes place. That is what quality of design. Now, when the designer makes these specifications, he also classifies the characteristics as critical, major, or minor. This is for the benefit of the process engineers or manufacturers, where to focus attention more. A critical parameter is that one, where a small deviation from the specification value can create havoc for performance. For example, a limits and dimensions, limits and fits. You are at a bearing. Bearing is a close fits on a housing. If the dimension is a small value, it will not fit there. Or if it fits, it will be loose. It will not work as a bearing. Then there is a safety parameters like terminals, clearances between terminals in a transformer or terminals in a way. These things are to be controlled, so it will be well within limits or better on that one. These are safety parameters are critical. Third one is aesthetics. You are having a car in the showroom, go to a showroom and see a scratch. The scratch is coming the bonnet or the door. You find it is critical, you will not accept the car. It is saleability is reduced. But the same scratch coming underneath on the chassis, you will not look at it. Yeah. So that's what regarding design is all about. Now, having the design is frozen through a system of testing or applications or feedback from various sides. This design has been matured. Then goes to the conformance level where manufacturing takes place. It is the person you study the specifications, measurements, and gap analysis, report generation. Here also there are severity of deviations, whether deviations are minor or very major, very severe, etc. Depending upon that, there will be an action. So when we say the product quality, it is based on customer feedbacks. We analyze why this feedback has come. So it goes the same series as earlier. You go to the how much deviation takes place from the basic values, and depending upon that, there is a customer experiences and go through the PDCA rules. But failures why failures are taking place? There are two various roots of failure reasons. One is a lack of knowledge, or the other one is lack of attention. A person is knowledgeable, process, strategies, purpose, then he'll be able to do a good job conforming to a specification or customer needs. But we have seen an experience where we are lacking is not the process knowledge or production knowledge. Where we are losing the game is lack of attention. There are three parameters, three considerations of attention we are losing. Doing the process, we lose attention. Doing measurement, we lose attention. Or we lose attention to vendors' premises. Halo effect, there is one thing. Friday slips, gold obsession. The three factors are influencing the attention of a very learned, very experienced, very expert person, task performer. Halo effect is that one. We go by the opinions of some people. I can tell you some examples. And a person who was working in the mechanical lab, an excellent metallurgist. No, he teaches metallurgy to others, but it was in his hands. A customer complaint has taken place. The complaint was the material specification for a component was SS316L. SS316L means it has got a carbon percentage of 0.03%. But what he has accepted was SS316, which has got percentage carbon of 0.8%. It has got a problem on the performance of the material because it loses its repair welding capability of the components. Now, what happened? Root cause analysis. We talked to the person. He is a very knowledgeable person. We cannot beat him. He will teach us. What happened is there was a revision of the specification 2 to 3 days before the inspection took place. Now, his PC was not working, so he went to the vendor's premises. There, the power supply was not there. He is a very senior man. The vendor told him, "Dear sir, we have done everything as per the latest revision only. Don't worry, these are the drawings, you can go ahead." Now, rule number 1 in any inspection process is you have to get the latest revision confirmation from the customer alone or the branch manager to whom he is reporting. But it is here, he could not ask him. I mean, the vendor is so, towering personality or so many days, he went by the vendor's words and landed this complaint. So the corrective action was he circulated to everybody. You never go by the vendor's instructions. You should always check with the customer design engineer or inspection engineer for correctness revision status before you go ahead with the inspection. Next one is the fraudulent slips. This comes a mental if you go into the Mahabharata, if you go to the chapter 2 of the Bhagavad Gita deals with this very nicely. Arjuna was a warrior like any one of us. He came to the battlefield to fight off and finish off the Kauravas in no time. And he can do that. But that exactly he did not do that. He sat down, said, "I will not fight." What is the point was, seeing the enemies on the side, he did not see the enemies. He saw his friends and relations, his own gurus, he is with all these things. So he had his mind was shivering and he sat down. I cannot fight. Then it was the Krishna's process of getting through the process of PDCA. That is, plan is getting to action and do, check, act. You are doing what is his issue of not fighting. His mind was disturbed. He was seeing in place of enemies. He was seeing the friends. He has to tell him, you are not fighting with them. I have already killed them. So when you are killing, the results of our killing comes to me. Then he come to the stage to the total action where he said, yes, I will fight. So Friday slips comes very often. The mind is disturbed. We can never apply our knowledge. Goal obsession. Many times we are given with a job for which we are not prepared. We are maybe 4 hours job, 3.5 hours. 4 days job, 2 days. Also here, I got a case to quote from the Challenger 86. You must have gone through the failure analysis of Challenger. Challenger 86, there is nothing like a job like the NASA to have a knowledge-wise, competence-wise, anyways, salary-wise, anyways. But it is here the real goal obsession has taken place. Within 62 minutes of launching, Challenger went into flames, including Kalpana Chawla. The reason they have brought out was there is an O-ring which prevents the leakage of liquid fuel into the booster motor mechanism. 2 days earlier, they were advised you have to redesign the O-ring, but authorities had a fear of public criticism and the postponement. Result was they ordered launching and went into the flames. It's a typical case of goal obsession and also fraudulent slips. Now, these are the factors which influences defects and failures, and depending upon the extent of deviations, there is a customer experience, or it may be severe, he may not come back, or he will run away to somewhere, or he will settle with us and improve. These are some of the cases, same cases we have come out. The first case is lack of knowledge. it is we do extensive sampling, but when we use sampling, we do with a sample size and where to sample random sample. It's typical cases happens. And it is here what I Okay. It is a case of a bus duct. A bus duct is a media, is an enclosure of aluminum constructions, enclosing the bus bars, which is connected to the generator to a transformer, first level of transformer. So it is enclosed in a bus duct. There is a painting process for the bus duct. Now there is a specification for the painting. It is 85 microns minimum. Now the customer complains, it is only 26 microns. Now the inspector here checked up, he has given an inspection reports, he has measured more than 85 microns, 86, 90, 92, 93, has measured like that. So where it has gone wrong? Is it means the customer has not measured correctly or inspection has measured correctly? Both, not both of them. They both are the experts. Where they have gone wrong is, how do you take the sample size for evaluation of dry film thickness? There is a standard ASTM. They have to divide each area into 1 meter square size, and each meter size they have to 6 spot sample checked up. They have to do spot check. If they do that, the variation on account of painting with the operator can be detected or can be minimized. It can be detected and found out. So this 26 should have been come to the inspection engineer, provided he has taken this method, which he did not do. Normally, they follow the quality assurance plan. Sometimes they code the ASTM, sometimes they do. But intelligent inspection engineers, they go round and round. There's the 4 phases of the bus duct, all along across, they check it up. This is typically, again, a painting process. It is not exactly a single homogeneous process. A 2 or 3 people can paint it, or same person, different type. So it is a multi-model. It will not take the same uniform. Another case we have come across, when you are giving the lot for inspection, they may not have the space for exposing all the items. It has happened one of the places, conveyor belts. Conveyor belts space was not there, so inspection engineer with all the faith, he has shown 1 or 2, he is gone by the 1 or 2 samples, what he has able to see. This is exactly mistake he had done. He has all the vendors spread it out and take random samples all along across. So the sample size he is taking, they are representing as the total lot he is inspecting. This is one case regarding sampling arrays. Next one is a lack of design. It's a typical case of a superheater coils. We use extensively boiler systems. Within 2 to 3 days of receipt of the supercoiler site, the customer complains the weldings are cracked. Now, we had a chairman who was working there. He stood up and pounded on the man who had delivered the message. He complained, did you do this stress relieving level joint? He is a metallurgist and a very knowledgeable person for ASU, gold medalist, Ritchie and all those things. Then he said what he did was, he explained the case. These superheater coils are made of a material known as T91 series, 9% chromium, 1% molybdenum. One case, it is developed specifically for preventing weld cracks in the superheater coils. And one condition is they have to do the stress relieving after welding. Now, he asked him, so inspection engineers, he said, the stress relieving is not called for in the quality assurance plan. He asked him, so what?
Another 5 minutes time.
Yes, sir?
You have another 5 minutes time.
Okay. Okay, I will finish. Okay, so what? You know pretty well stress relieving is critical part of a welding process T91. You must have asked, we cannot do that because a vendor is committed to a process specification which is approved by the customer, is not called for stress relieving, he will not do that. What he could have done was call up the customer, tell him stress relieving is not done. He may have to do the commercial settlement with the vendor and go into stress relieving. Then a person was called for, he had deputed to the vendor's work, went to the customer, trained them what is the stress relieving T91, and the result was the customer so delighted as the Kano model. Next 8 jobs they gave to the customers without any review or evaluation. One more shall I tell you? There is another case what you have come across. It is a resistance used in the extensively in the modules, electronic control modules in the control systems. What happens? We have a system of feedback systems in the shop floor. They set the 10 ohm resistor mark is more than 100 ohms. How is it possible? So what you say is, we check up the resistor, check up the batch limiter. There is an identification. Go to store, measure it, go through a specification. What is called for? We found the specification having adhered to the conformance level. Inspector checked it. Then went to the purchase order. Then he found there is a deviation from the standard. That is, he has gone to routine parameters, but what is the batch acceptance test? What is called for resistance have to be evaluated to stand the ability to temperature, humidity, all those things. There is a batch and process is there, which was not done. He took the samples, he tested, do the process, and it failed. Then we have to call the vendor, ask him. He said, look here, you are asked for values on this one. We have given you what you said. If you want this specification to military specification, I can give you, but my code will be different. So when they tell the vendor what we want, we should be clear and tell him completely considering all the application processes. This is how the performance varies company to company. When you see the variation in the same ISO 9001, 1020, there is wide variation performance of the companies accredited and audited and checked by them. But still you find variation. Same companies go through various variation with the time. There is a reason for this. I have quoted only some books which details what factors influences performance excellence. Each context goes wrong. There is an interesting book here, Black Box Thinking. These books deal with many people do not learn from mistakes, some do. He quote examples of an aircraft black box they are using, where the crash takes place, exactly what happens, can pinpoint what is the reason. But whereas he quotes with surgeries, other areas, this system is not there. Getting the root cause is a big challenge. Shall I go further? Or?
I think now you can conclude.
Okay. Nice. Thank you very much. Dr. Ivizio, the chairman of the session. Dr. Joby K. Jose, the chairman of the session. Satish Kumar for organizing the whole program. Professor Mr. Perumalu, who was introduced me to the program. Kerala University and the organization participant for the active patient listening and feedbacks. Thank you very much. Any queries?
Thank you, sir. Any questions to the speaker? If there are no questions, I think let us thank the speaker.
Okay.
Let me thank all the 4 speakers once more.
Yeah.
Thank you all. Also,
thank you.
Thank Dr. Satish sir for giving us an opportunity to organize a session here. Thank you very much.
Thank you, sir. Thank you.
Okay.
Thank you so much, Dr. Jijo, for organizing a very wonderful session, in fact, on the a hot area, in fact, of this, our statistical applications in business and industry, and with the potential speakers. I utilize this occasion to extend our gratitude to each one of the speakers. And let us give a big clap to each of the speakers this session. Yeah. And once again, we extend our gratitude to Professor Dijo for chairing this session, and Professor Dr. Joby K. Josh for acting as a co-chair to this session. We expect your support and blessings in future also. Thank you all.
Thank you, sir.
Thank you.
Thank you. I hope now it is the time. It is stopped at the very right time. The talk session. Our next session in this platform will start at 6:15 p.m. 6:15. So there is 10 minutes time. You can interact among or Professor, our speaker, Subramania, Shiva Subramania Iyer. You have to say something. You can. We are a few minutes. Everyone is, because your talk was very informative.
Thank you.
Thank you, sir. Thank you, especially to our youngsters, young researchers in the area of statistics. It is very motivating also. Certain dialogues in or sentences, certain ideas are very motivating. Thank you so much. If you want to, or otherwise, like we can start the next session at 6:15, because otherwise the speakers some people are expecting that time. Anyway, Professor Muralidharan sir is here. Professor Muralidharan?
Yes, I am here.
Yeah, Professor, you are here. And what about the speakers? Dr. Eliama Matthew? Professor Eliama Matthew? What about Preeti? Dr. Preeti?
Madam, sir, I am here. Jagat is here. Eliama Madam and Preeti Madam will join soon.
Okay. You have, in fact, Dr. Jayadevan informed me in the last minute he has some health problems too, and he is not able to speak. That's why.
Okay.
I hope he will not join this group this time. He extended. He assured in the next time. So you can take that much time also for your deliberations.
Okay, sir. Okay. Just I will inform them.
Yeah.
Okay. Meanwhile, just a minute. I will inform Eliama Madam.
Yeah, please. Dr. Mariam Anthony?
So Jagannath is there.
Oh, okay. Jagannath,
yes, sir, I am.
Jagannath is contacting Professor Eliama. Yeah.
So Jayadevan is not the right? Sadish, it is muted. Unmute.
Sorry. Jayadevan has some health issues.
Okay, no issue. No problem.
At present, he is not in a mood to. It is difficult for him to talk.
Okay.
That's the idea.
So other three speakers are there.
Yeah, Professor. Other three speakers are there.
Okay.
So the timing is from 6:15 to 8:25 p.m. So we have a lot of time.
Yeah. If
So
they
we
need
leave.
it, otherwise
We will leave the speakers to speak.
Yeah.
They want to have extra time, fine, they can. So shall we going to start now?
What about the time in 8:07? So let us start at 8:10. 8:15 is the time. We have put it in the 8:15. So just introducing all those things, then we can.
No, 6:15. 6:15. Let me correct you. 6:15 is the.
6:15. 6:15 is the correct
starting time. Okay.
Now it is 6:07 or 6:08.
Yeah. We can wait for maybe 5 more minutes.
Maximum 5 minutes.
Okay.
That's
പാരലൽ സെഷൻ്റെത് 6:15 ആകുമ്പോഴേ തുടങ്ങത്തുള്ളൂ കൃത്യം.
Parallel session same time then starting. We'll start it at the 6:15 itself.
Oh, you have a parallel session also. Okay.
Okay. Or otherwise you can join there. I shall check whether whatever the position there. If they in parallel session, if the earlier session is over, let us start it. No problem. Since it is an invited session, we have to wait a few minutes.
Okay.
Let me to check there.
Professor Iyer, sir.
Yeah. Yes, sir.
You are based at Chennai, sir?
Yeah.
I
can hear you.
Yeah. Okay. Speak, sir. There is no voice coming up, sir.
Wait.
Okay.
I kept it open. I have removed.
Okay.
Are you able to hear?
Yeah. I can hear you now. Yeah.
Yes, sir.
So you work on Six Sigma concept, right, sir?
You mean?
You are working on Six Sigma concepts, right?
I am retired, sir, 20 years back.
Yeah, okay, I know.
I am retired 20 years back, but I am doing this job because keep myself busy.
That's
I
right.
do some readings,
Some
webinar, all those things. Keep in touch with the people who are update myself. 6 Sigma, I have followed it.
Yeah.
I know something about these basics.
Okay.
Critical characteristics, operations, variance, and all those things. We have done it. But I am not a black belt or any belt with
Right. Sir, I am a Keralite working here in Baroda, MS University of Baroda.
Oh, Baroda, I know.
Yeah.
We got an office there.
Yeah.
RC Datta Road, there is an office, opposite Express building.
I see.
Yeah.
Okay.
Our ROD is there.
Okay. These days I am working on Six Sigma, Lean Six Sigma concepts.
Oh, Lean 6, right. Very popular.
Yeah. I just had a very recent publication with Springer, a book.
Yeah.
Book on sustainable development and quality of life.
Oh, nice.
Concepts, yes.
Right. Can I ask you a clarifications? I ask everybody. In the measurement system, see, critical to quality characteristics.
Yeah.
The measurement system, measured values are very, very critical.
Yeah.
Now, we are using a calibration instrument. When you are using calibration instrument, the calibration certificate gives the expanded uncertainty.
Right.
When I studied that expanded uncertainty from the literature, whatever measured values are to be adjusted for this expanded uncertainty, only those values are we have to take.
Right.
But I was trying with many labs. They don't tell me what they are doing. They give the expanded uncertainty calibration certificate.
Right.
I wrote a letter mail to NABL. I was chasing with them, but it appears it is not very much in use.
Okay.
Because the vendor will not agree for that. You will say 170 expanded uncertainty, 165 only can be useful. He will say no, drawing calls for only 170.
Right.
Especially with the hardness measurement, we had this issue. I started chasing them, pursuing them. A calibration expert, he is taking classes. I asked him, anywhere in the world, can you tell me lab, you can advise me what is the correct value, you can take it based on expanded uncertainty.
Okay. Now, this measurement system, you mean it's done by manually or through machines?
Manually, machine both. If you are using a CMM, they use, but everything you don't require a CMM. You can use a vernier caliper or a micrometer or even tensile testing machine. You're testing in a complex. We had a problem on this. Recently we had a problem. The customer complained because what happened? The 4 specimens you take it for tensile testing on a casting.
Okay.
4 coupons. First 2 coupons, one inspection engineer gone there. He rejected. He got 270 like that in place of 285 Newton per meter square. Now next another engineer has gone. He accepted. Balance 2 coupons, but customer said, "How do you accept? Your own man has rejected earlier. Your own man accepted." Now IS says you have to take 4 coupons from the casting. 4 coupons from the casting. 2 coupons if you fail, another 2 coupons test it. If that passes, you accept the material.
Okay, sir. Now I think it is time to start the next session.
Oh, thank you. I'm sorry. No apologies.
It's no issue, sir. No issue. We can talk.
Yes, sir. No. if time permits, you can discuss.
Yeah, we can have discussion. Okay, no issue.
Later. So let us start this session in which especially even though we have scheduled 4 speakers, I hope there will be 3 speakers only to participate. And to chair this session, we have our Professor Muralidharan is here. I hope we arranged Dr. Rakhi to support you, sir.
Okay, thank you.
Rakhi, please introduce Professor Muralidharan, sir, and thereby help him to if needed for further procedures.
That's fine. I think 2 days ago I was introduced by you. I don't need any detailed introduction. Anyway, you just give few lines. That's all.
A brief introduction, please give, because in that time some speakers may be probably some of the participants missing.
Yeah.
Let us try. Let us start the program. Okay. Thank you,
sir. Thank you, sir. Good evening, one and all. Welcome to the present session. The session is chaired by Dr. K. Muralidharan, who is the professor in Department of Statistics, MS University, Baroda. He is an eminent researcher having more than 125 research publications in several reputed journals. He has several areas of interest in research such as probability theory, stochastic processes, statistical inference, regression analysis, and so on. So I humbly request Dr. Muralidharan sir to chair the present session. Welcome,
Thank
sir.
you, thank you, thank you, madam. Thank you
Yes, sir.
once again to Satish Kumar for inviting me for chairing this session. Although it's a stopgap arrangement, I readily agreed to it. Okay, it's my pleasure to be again here to address some of the researchers here. Now we have 3 speakers in this session, and the time allotted initially is for 35 minutes each, I think. Yes, it is 35 minutes, but we can have some flexibility in timing. I leave it to the speakers to adjust the time. If they want to have 40 minutes talk or 45 minutes, we don't mind. But it's not, there is no compulsion. There is no compulsion. If they want to complete it in 30 minutes, that's fine. Or 35 minutes, fine. Okay, now I think the first speaker is Aliamma Matthew. Is it? Sadish? Is the order same? Aliamma Matthew is the second. Preeti Sara is the third, and Jagannath Krishna is the fourth. How do I go? Sadish, your microphone is mute.
Okay. Sorry, Professor. Sorry.
No issue.
Or, Professor, you can give to them. You can ask Professor Eliamma.
Okay.
In what way?
Okay. I invite Eliamma Matthew to have her talk. I don't have any material to introduce them, the speakers. So I hope they will be introducing themselves. The first slide will carry their name, details, and affiliations, etc. And she's going to talk on comparison of propensity score methods on the risk estimation of breast cancer. Over to you, madam. Madam Aliamma, are you there?
I hope
Madam
she has joined. She has already joined.
She has joined, I saw. Yeah, somewhere I saw she joined.
Jagannath, whether any network issues or anything like?
Oh, yeah.
You can manage them because all the 3 are from our same institute.
Same institute, yeah.
Trivandrum,
Yeah.
Jagannath is also from your department, okay.
Yeah. So okay, I will check. I will check with
and
them.
they are a very active research group.
There is no doubt about it.
Yeah.
No doubt about it. Kerala University Department of Statistics is very active. What about Preeti, Sarah, George?
She also will be joining soon, sir.
Yeah. Or else we will start with Jagannath.
That's fine.
ഇല്ല മാഡം ഡെസ്ക്ടോപ്പില് മ്യൂട്ട് ഫോണിന്റെ കാണുന്നില്ലേ?
Jagannath, are you ready? Jagannath.
I think they are discussing
each the problem with the internet and all those things. Okay.
Network issues may be there.
Network, yes.
Probably.
Yeah.
Anyway, Jagannath.
Yes, sir.
Yeah. In what order you wish to present?
Would you like to have the first talk?
Actually, I contacted Eliamma Madam now. She couldn't. The microphone and video is not working. So I asked her to left and again rejoin. So she will be joining again.
Okay, let us wait for. We have buffer time also. No problem.
Yeah. Yes.
we should not keep waiting the audience also. They will also move.
Dr. Jagannath, what is the present status?
I am talking to her, sir.
Okay.
No issue, no problem. Can you talk the first speaker, Jagannath? Sadish, all these candidates are working under you?
No, sir. All these are our research group from the Biostatistics Department of Regional Cancer Center. That is what
Regional Cancer Center. Okay.
Yeah.
Trivandrum. Okay.
Yeah. Our group are there.
Okay.
And earlier, two researchers. In fact, we have coordinated.
Sir, one thing we can do is I will start my presentation.
That's what I am telling. Yes, please do that. Please do.
Yeah.
So Jagannath will be talking now. He is going to talk on estimation method for survival function, a loss to follow-up approach. Please, over to you.
Yes, thank you, sir.
Welcome.
All the three are our alumni, sir.
Okay, alumni. Okay. Okay, it's visible.
I'll make it full screen.
Yeah, full screen. Yeah.
Okay. Thank you, sir.
Can you put it in the slideshow mode?
Now it's in slideshow full screen mode only, sir.
Is it
visible?
It is visible.
But it is not. It is slide by slide now.
Yeah.
Not in full. I mean, show mode.
Now, whether the second page displayed?
No.
First, okay. Now it is visible, right?
It's visible, but it is not in the show mode, slideshow mode.
Jagannath,
yes, sir.
While you present the sharing the at that time, whether you chosen the entire screen, your entire screen.
No. I have chosen.
Please do it.
I have chosen the separate window. It is open in the separate window.
No. Please, I mean, close this. Close the presentation.
Okay.
Then open it in entire screen.
Yeah. While choosing a pop-up menu in which three options, first is your entire screen. Got the idea?
Entire screen, yeah.
Entire screen, but okay.
Click on the entire screen. Then a small window comes. Just to click on that window. The share will be active.
Yeah.
Thereafter, you can move to the slides. Yeah.
Okay.
Now it's fine.
Yes.
Now we can move to your slides.
Yeah. Share presenting. Okay.
Not stop. Not stop presenting.
Just open your PowerPoint. That's all. Open your PowerPoint now.
Now you can. You move to your open. Yeah. Yeah. Open it.
Is it visible now?
Visible. You can make a slideshow.
Yeah. Okay.
Above there is a slideshow. Yeah.
Yeah, it's okay.
Is it fine?
Fine.
Okay.
Go ahead.
Okay. Thank you, sir. Thank you for the introduction. And first of all, I would like to thank Sadish sir and the organizing team for giving me the opportunity. So,
I'm proud of you, Jagannath. You are my student.
Yes. Shall I continue?
Yeah, please.
Yeah. Yes. Okay. So, title of my talk is on weighted estimation method for survival function.
Somewhere around 7 o'clock, we will stop you. Okay.
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 Okay, fine. So weighted estimation method for survival function, a lost follow-up approach. So my talk is scheduled as with a motivating example I will start with, then go to the background, then show some existing methods and a proposed method. Then the maximum likelihood estimation procedure for the proposed method will be detailed, and properties of the method, then data analysis, simulation, testing, and finally discussion and conclusion. So with the example, I have taken a breast cancer patient data. The patient who has been registered in Regional Cancer Center Trivandrum during the year 2009 to 2010, they have been followed up to 2015. That is, those who have registered during the period 2009 and 2010 till December have been followed up till December 2015. So that we will have a follow-up of 5 years. So you can see from this table 1, the fifth column, that is 5-year survival probability, that is for the data set that has been followed up till 2015. The survival probabilities are given for stage-wise as well as overall. And we can see that it is 0.96 for the stage 1, that is early stage breast cancer, and stage 2, 0.915, and so on. And the overall survival probability is 0.852. And what we have done is we have followed it the same set of patients for additional 2 years. That is till 2017 December. So that we got the survival probability as shown in the last column of the table. That shows that compared to the survival probability what we have obtained during the follow-up up to 2015, it shows that there is a decline. That means the survival probability is reduced. And that's a question what make us think of to see what is exactly happening for the same patient. The survival probability is declining. Then we looked at the total cases and the number of events. So we can see that the number of events initially was given here as given here. The total number of events is 176. Among that, stage 1 has 3, stage 2 has 56, 81, and 36. But when we have followed them for additional 2 years, we got the event. Event means death. Death is the event considered here. And that event is 4 for stage 1. There is slight difference, whereas there is a huge difference for the stage 2, 3, and 4. That shows that there may be a death happened either within 5 years or beyond that. The possibilities are there, and that is not sufficient to make any inference. So what we have done is we have looked into the follow-up percentage. So the 5-year follow-up percentage initially was lost to follow-up, not the follow-up proportion. The lost to follow-up proportion we looked at, and that is nearly more than 50% for the initial data set. That shows that most of the people are lost to follow-up in the case. Lost to follow-up is a serious issue. We notice that, and that can be clearly seen in the data set which has followed up till 2017. So here we have additionally followed up the patient for 2 years. So the lost to follow-up proportion has reduced. So this shows that because of this, we noticed that because of this lost to follow-up, this may be the reason this survival probability there was a difference or decline.
Jagannath,
Yes.
can I intervene?
Yeah.
What about the age of the BC patients?
Age
of the BC patient. What is the age or range of the patients?
Range is from 20 to 80.
20 to 80.
Yeah.
Okay,
So,
maybe I may ask you a couple of questions at the end of the talk. Okay, you please continue.
Sure. And okay, with this, we thought that loss to follow-up is we come to know that loss to follow-up is a serious issue, and with that motivated us to think of modeling a loss to follow-up weighted Kaplan-Meier method to solve this issue. And with this, the background, we know that Kaplan-Meier method is the most commonly used method in medical research for estimating survival probability in presence of censored observations. And we also know that the Kaplan-Meier method is very unstable for estimating the tail function in presence of heavy censoring. The cancer survival data are typically subject to right censoring and forms the main factors affecting the cancer survival estimate, which includes patients who are either withdrawn alive or the closure study or lost to follow-up. We have seen the serious issue of loss to follow-up in the previous slide. So to overcome this issue, there have been many weighted Kaplan-Meier method has been proposed in literature. And among them, 2 of the methods has been taken for comparison in this study also. And coming to the loss to follow-up, cancer hospitals in India now reaching an alarming proportion of loss to follow-up proportion due to inadequate follow-up system and thereby incomplete follow-up information. So the survival of right censoring data was largely influenced by the loss to follow-up proportion, because we are having only right censoring in cancer survival data. So loss to follow-up is considered as non-informative if the associated factor for loss influences study outcome, that means which is random. So hence survival probability estimates which account the loss to follow-up proportion received attention to reduce the bias. So we focus on this topic, this area. And the methods, coming to the methods used, the Kaplan-Meier method, the first one. Here let n be the total number of participants in the study and T1, T2, etc. Tn are the observed times. The survival time of some of these patients may have been censored, and let T1, T2, etc. Tn be the patient's ordered event times, and let the number of patients who have survived before Ti, which includes those who have died at the time, is Ni, and the number of events death at Ti is Di. So the Kaplan-Meier estimate in the interval less than T is given by equation number 1, that is product Ti less than T, Ni minus Di by Ni. So the second method we looked at is the weighted Kaplan-Meier method defined by Jan et al. 2005. Here they have introduced a weight, that is weight on the non-censoring rate, and that their survival probability is given in equation 2. Survival function is given in equation 2. And the third method we have taken is the empirical weighted Kaplan-Meier method introduced by Huang 2008. So the survival function is given by equation 3, where they have given the weight Pni, where Pni is defined as in equation 4. It takes the empirical functional form W equal to 1 by root of n into n minus 1 for I equal to 2 to n minus 1, and for 1 and n, it takes the form 1 by 2 into 1 minus n minus 2 times W. And coming to the method, what we have proposed is the loss to follow weighted Kaplan-Meier method. And for that, we have defined Li be the number of patients lost to follow up at time Ti. And we have introduced the term R, the duration of the study period, that is end year of the study period minus end of the registration year. And Ci is the number of censored events at the time point Ti. And the weight Wi is then defined by Wi equal to 1 minus Li by R into Ci. Here, Li, the weight is defined in between 0 and 1 for I equal to 1 to n, and R is restricted to a minimum of 1, that is it should be greater than or equal to 1, and Li is less than or equal to Ci for all I, and the Li, loss to follow-up Li is equal to Ci minus 1. That is, those who are censored today is considered to be lost to follow-up tomorrow. So then the loss to follow-up weighted Km is defined by us in equation 6. Now, if R tends to infinity, that is the duration of study period increases, then the limit R tends to infinity W, the weight will reduce to 1. Hence the equation 6, that is the loss to follow weighted Kaplan-Meier method, will reduces to Kaplan-Meier method. And we have found the variance of this weighted loss to follow weighted Kaplan-Meier method, and is given in equation number 7. And this has been derived using delta method and Greenwood's formula, and the corresponding confidence interval also obtained and is given in equation number 8. So now we will look into the maximum likelihood estimation of the loss to follow weighted Kaplan-Meier method. Let Ci denote the number of cases censored between Ti and Ti plus 1, and let Di be the number of cases that die at Ti. Then the likelihood function takes the form given in equation number 10, where the product is over the m distinct times of death, and we take T naught as 0 with S of T naught, the survival function at T naught is equal to 1. To estimate m parameters representing the values of the survival function at the death time, T1, T2, etc., Tm. So let define pi I equal to STI by STI minus 1, which is the conditional probability of surviving from STI minus 1 to STI. Then STI can be represented in terms of pi I as pi 1, pi 2, etc., pi I, and the and the likelihood function becomes as in equation number 12 as the product of pi i's. Here, note that all the cases who die or are censored between Ti and Ti plus 1 contribute a term pi I to each of the previous times of the death from T1 to Ti minus 1. So in addition, those who die at time Ti contribute 1 minus pi I, and the censoring cases, it contribute additional term pi I. Thus, when there is a weight Wi, now we are introducing the weight also into the likelihood function for each pi I, then the likelihood function is redefined as in equation number 13, and the log likelihood function is given in equation number 14. So which gives the maximum likelihood estimate pi I cap. That is, here we take the partial derivative with respect to pi I, and equating to 0, we will get the corresponding estimate pi I cap as Ci by Wi into Di plus Ci, where pi I is Sti by Sti minus 1. Now we will look into the properties of the estimates. So the relative efficiency of Kaplan-Meier estimator with respect to loss to follow weighted Kaplan-Meier method estimator is always greater than or equal to 1. The proof is straightforward from this equation under the condition that 0 less than or equal to weight less than or equal to 1, that is 1 minus Li by R into Ci less than or equal to 1. And equivalently, we can also show based on the variance expression as given here. And the second property is the survival estimator of loss to follow weighted function Sn tilde of T possesses a bias. The proof follows from Norman and Nacho 2018, and this is the proof for the theorem. And we found that it is not equal to the S of T, so it possesses a bias. And third, we looked at the consistency. If the survival T of the distribution function S and the censure C of the distribution function G are independent and under the conditions the duration of the study period tends to infinity, loss to follow up Li is less than or equal to Ci for all I, and Li is Ci minus 1, and Yn cap of T convergence probability to infinity sentence to infinity, then the supremum of over 0 less than or equal to S less than or equal to T of absolute value of Fn cap star of S minus Fn cap star of S converges in probability to 0 as n and r tends to infinity. The proof follows from Shorak and Wellner 1986, and with the assumption of Li less than or equal to Ci for all I and for large R. And further, the uniform consistency also can be proved by using theorem 4 of Neumann and Nacho 2018. Next, we will look into the data analysis. Here we have considered two data set. One, I have already shown that the breast cancer data. So the date of diagnosis was considered as the starting date of the study or the entry time of the patient into the study. Stage at diagnosis, follow-up time, and status at last follow-up were abstracted from patient's medical records. And here, the first data we have taken for breast cancer patient who have registered in 2009 and 10 and followed up till 2015 and further followed up till 2017. And the second data set is the cervix cancer patient data, which registered during the year 2006 to 2008 and followed up till 2016, and then additional 1 year till 2017 has been taken for validation. Subjects who died during the course of their follow-up were accounted as event, and all other patients were considered as censored. So information on patient outcome was obtained through periodic follow-up. The follow-up time was calculated by subtracting the last follow-up date or date of death, if any, from the date of diagnosis. And coming to the data analysis part for the breast cancer data, we can see here we have looked at the stage-wise as well as the overall survival. We can see that for the initial follow-up percentage, for the 4th year onwards, for overall it is less than 80%. For stage 1, as well as stage 2, stage 3 and stage 3, up to 3 years we are having adequate follow-up, whereas stage 4 we have only for 1 year we are having adequate follow-up. Adequate in the sense we fix randomly, it is not a gold standard one. A minimum of 80% follow-up is there, then we consider it to be a reliable estimate. We will get a reliable estimate. So if it is here for stage 4, we have only for 1 year follow-up is sufficient, that is 82.6. And looking into the survival probability using the KM method, this is a weighted KM method by Janet et al. And this is by Huang, and this is our method. And we have compared, once you look into the survival probabilities, once you compare, we can see that Kaplan-Meier estimate is slightly overestimated compared to that of lost follow-up. And whereas this weighted KM and empirical weighted KM is little bit underestimating the survival probabilities. And this has been further justified or further clarified using taking the additional follow-up. That is the validation. We have taken additional 2 years follow-up. And if you look at the survival probabilities for Kaplan-Meier method for the updated data, we can see that it is closely matching with what we have obtained with 5-year follow-up. So it shows that our estimate is performing, our survival method is performing better compared to the other method, and the efficiency also has been given here. And for especially for the stage 4, at early stages, mostly there won't be much difference, or almost all are having better, showing equal survival for the first 2 or 3 years, first 2 years. For the early stage disease, that is stage 1 and stage 2, that is early stage we call, and stage 3 and stage 4 we are called advanced stages. For that is for poor prognosis, the survival probabilities are very high, much higher for the KM method and much lower for the weighted KM and empirical weighted KM, whereas our method is performing showing a consistent estimate. That consistency can be seen by looking into the lost follow-up method for the initial data and the updated data, that is given in column number 6 and 7. So this is a graphical plot comparing between the methods. We can see that for stage 1, empirical weighted KM is totally underestimate, and then followed by the weighted KM. And loss to follow weighted KM and KM method and the updated KM method are giving almost the same survival probabilities. Stage 2 also KM, updated KM and loss to follow weighted KM is giving almost the same. And empirical weighted and weighted KM are slightly underestimated. And here in stage 3 also we can see that updated KM and loss to follow weighted KM are giving almost the same result. And KM is slightly overestimated. And weighted KM and empirical weighted KM are underestimating. And that is evident in overall survival also, and in stage 4. And coming to the next set of data, that is cervix uterine cancer data. Here, the reason why we have chosen this data set is here it has a longer follow-up period, that is nearly 9 years of follow-up. So longer follow-up and we are looking at only 5-year survival probability. So there may be sufficient follow-up in this case. So this the table 3 shows the follow-up, the first follow-up, that is up to 2016, and table 4 shows the additional follow-up details for all the 4 methods. So here we can say that as there is the follow-up proportion is adequately good. That is, for stage 1, if you look at the survival, the follow-up proportion is, for all the cases, it is more than 80% we are having. Stage 2 also we are having more than 80%. Stage 3, it is nearly 80% for the 5th year. And stage 4 also we are having a minimum of 75. So it has a good follow-up for the survival data, for the cancer cervix uterine data. And hence the survival probabilities what we are getting for the KM method and loss to follow KM method are almost similar. And whereas for the WKM and EWKM method, there is a bias when it comes to 5-year or 4-year. And for the stage, for the cervix uterine cancer, which has been updated for additional 1 year, you can see that the follow-up has been increased slightly. There is an increase in all the cases. And stage 4 also we are having from 75 to 77.18. Here also the survival probabilities, you can see the probabilities are almost similar in both the cases. That means if you are having sufficiently good follow-up, then your loss to follow weighted KM is nothing but your KM method. And if in the presence of loss to follow-up, higher proportion of loss to follow-up, then KM is an overestimate, gives an overestimated survival, whereas loss to follow-up estimate can give a consistent and a reliable estimate. And coming to the simulation study was conducted with 1000 iteration with the survival time generated using viewable random variable with the scale parameter 0.75 and shape parameter 20. And censoring variable used using uniform random variable use 0.4 and 1 to get a lower censoring rate of 20%. Then to get a medium censoring of 50%, we have chosen variable 1.2530 parameters. Sorry, we have chosen 2.75 and 50 as variable parameters and uniform 0, 1 for getting a medium censoring of 50%. And to get a 70% of censoring, that is higher censoring rate, we use 0.7. So a simulation for the sample size 2500, 500 were generated with a duration of the follow-up fixed at 5. Here also we are fixing the duration as 5 years to just for a comparison purpose. And the root mean square error for the 5 years for KM and other methods were estimated. And the data analysis and the simulation studies, everything was done using our program. And for the censoring, 20% is censoring. We can see that this censoring, the average follow-up is also obtained. Here we have almost all the cases up to whether it is 2500 or 500. The follow-up percentage is adequately good, sufficiently high, and hence the KM method, the RMSE have shown that there is not much difference. Even then, KM method is giving the better RMSE. Then followed by loss to follow-up, weighted KM. And in some cases, EWKM and weighted KM also showing some smaller RMSE in censoring with 20% censoring. So that means if it is censoring is low, KM method is performing better. And for 50% censoring, we can see that most of the situation, most of the cases, loss to follow-up weighted KM is giving the least RMSE value. And there are some few cases in which the other methods also performing, giving a least RMSE. And majority, and also on point to be noted is, for small sample size, LFU weighted KM is the best one. And for censoring cases with 70% rate or higher percentage of censoring, here we can see that the average follow-up is only for 1 year we are having as adequate follow-up percentage, and rest the follow-up is very low. And hence we can see that most of the situation loss to follow weighted KM method is giving the least. That is nearly around 70% of the cases loss to follow-up is giving the least RMSE, and for especially for the small sample size and large sample size, almost EWKM is also performing better because it is an empirical weighted Kaplan-Meier method. So it depends on as the sample size increases, it performs better. Even then, our model is performing equally good for the large sample case also. Now we will look into the testing problem of this particular weighted method with the null hypothesis that the two survival curves are identical against the alternate. They are not identical. Yes, sir.
You will have 5 more minutes.
Okay, sir. I will stop with that. Yeah. So to incorporate the information due to loss to follow-up, the simplified form of log-rank test is modified to form the loss to follow weighted log-rank test, and is given as in equation here. So WI1 represents the weightage to the first group, and WI2 represents the weightage given to the second group. And here this weighted log-rank test was compared with respect to the original log-rank test using the power function and effect size, and is given in the graphical representation. Here the power and effect comparison of log-rank test and loss to follow weighted test was given for stage 1 versus stage 2. You can see that for stage 1 versus stage 2, that is early stage or poor, that is having good prognosis. Here you can see that the log-rank test is having better power, but after during the follow-up period, the loss to follow weighted KM also merged with that of the log-rank test and shows a similar power. And the weight, if you look at the effect size, it is almost going together for KM method and loss to follow weighted KM method. And comparison with respect to stage 1 and stage 3, we can see that the power is almost or exactly the same for both the method, and the effect size is slightly higher for the loss to follow weighted Kaplan-Meier method, but that is negligible. And comparison of stage 1 versus stage 4 also, we can see that the power is almost the same for both the method. And when you look at the effect size, the loss to follow weighted KM method is giving slightly better effect size. And in stage 2 compared to stage 3, the power is slightly higher for the loss to follow weighted Kaplan-Meier method, and the effect size is showing the it is evident from the effect size. And comparing for the stage 2 versus stage 4, here also the power is almost the same, and we can differentiate it from the effect size. There is slightly difference is there. Stage 3 versus stage 4 also we can see that both has equal power, and the effect size is higher for loss to follow weighted KM. From this we can say that even though when we introduce the weight to the log rank test, the power of the log rank test is not declining or decreasing. So this is equally good, or equally we can apply this weighted log rank test if there is a high proportion of loss to follow up. And coming to the discussion and conclusion, as the proposed weighted KM method estimate provided adequate weightage to the loss to follow up and duration of the study, overestimation of the survival probability was greatly reduced. Irrespective of the loss to follow up rates, disease with good prognosis will provide similar survival estimates, whereas disease with poor prognosis, that means the advanced stage of diseases, will have overestimated survival when their data with loss to follow up rates are high. Further, the simulation study also supports the findings of the real data analysis. The test for comparing the significance between survival curves showed that the power was almost similar for log rank and the loss to follow weighted log rank test in most of the cases. So whereas for stages with poor prognosis, loss to follow weighted log rank test showed comparatively larger effect size. In conclusion, when factors for follow-up loss influence the study outcome and the proportion of loss to follow-up is high, the proposed loss to follow weighted Kaplan-Meier method and for comparison, loss to follow weighted log rank tests are better alternative. There are some references. Thank you.
Thank you. Any questions from audience? Audience, 1 or 2 questions we can have. Okay, I will continue with the same question.
Yes. Yes.
See, I think you should propose a method.
Yeah.
Maybe you can call it age-dependent Kaplan-Meier.
Okay.
Okay, because
yeah,
it depends. If you look at the data,
yeah,
there are all chances that there is a dependency of age, because when you talk about breast cancer, generally it happens after 40 years of age, right?
Yeah.
Okay, let us assume that this is the time period from where it starts, I think. So the early age before 40, maybe you can segregate the data in terms of 2 classification, before 40 or after 40 and sense.
Yeah.
So I think what you can do is,
yes,
the WI you have defined, somewhere in the same WI you have to bring that age factor also.
Okay.
Okay,
sure.
You will have a new model altogether. New model Kaplan method.
Okay.
Okay, so
Yes,
that's my suggestion for you.
Oh, thank you, sir. Thank you so much.
Welcome. Okay, I hope there are no other questions. So let us thank the speaker then.
Thank you, sir. Thank you once again for giving me the opportunity. Thank you, sir.
Thank you.
Thank you.
So I now request Aliama, George, madam. Are you there, madam? Aliama Matthew. I hope your network issue is over. All problems are fixed.
Yes, sir.
Okay, you are ready, madam? Are you ready?
Good evening, sir.
Yeah. Now, okay. So it's over to you. You can start your presentation.
Right.
So you are also from the cancer center, right?
Yeah. Myself, the head of the department.
Okay, you are head of the department. Okay, fine. Glad to meet you.
Department is cancer epidemiology and biostatistics.
Okay, yeah.
I have been working in the RPC for the last 32 years.
So, okay.
Immediately after my graduation, I joined in RPC, and from there I got an opportunity to do. I got an opportunity to undergo doctoral program. First doctoral degree is from Finland,
Oh, Finland.
That
Okay.
is in cancer in epidemiology.
Okay.
And then later on, I got another opportunity to undergo postdoctoral program from the National Cancer Institute, US.
Okay.
And then thirdly, I had taken PhD in statistics from KK Josar, Pala.
Oh, okay. Good, sir. Okay.
So this and almost my publications are related to cancer epidemiology.
Okay.
So I have more than 100 publications in cancer epidemiology. Is it?
Yeah, it's visible. It's slowly coming up. Okay, you can share. Okay.
My slides are. My
slides have not appeared so far. The screen is coming up. Okay. Okay. No. There is. Okay. Madam, can you put it in the slideshow mode?
Yeah, that's what. Yeah.
Okay, fine, perfect. You can start now. Thank you.
At the outset, I wish to mention that my presentation is not purely statistics, theoretical, any modeling.
No issue. We can enjoy the practical exposition also.
Okay, my presentation is risk estimation of breast cancer in Kerala, propensity score methods. Next. Some technical issues. Next.
It's okay, no problem.
Okay. In fact, my computer is not here. So shall I use this slideshow? It's difficult. I will show.
Okay. Please do.
So by seconds.
Yeah.
And before coming to the topic, I just is it audible, visible? The slides. These slides.
Yes.
This
visible.
Is actually. Next slide option slide show next slide.
Slideshow is possible. What you can do is
I'm using my daughter's tab, so I'm asking her.
Okay.
Slideshow I can. I'm stuck. Where to the next arrow key?
Okay.
Slideshow. And then
you have to open. It's okay. Now it's okay. It's in slideshow. Okay.
I need to move to the next slide. Okay. 1 second. Let me. This slide is showing the cancer incidence rates of this is showing the leading cancer sites in South Kerala. We will straight away see the leading cancer sites among females. You can see that. The South Kerala, Trivandrum, Kollam, Alappuzha, and Pathanamthitta districts. So, in fact, these are cancer registry rates, cancer registry data. We have operating cancer registries covering 4 districts in Kerala. Then in all the districts, you can see that the leading cancer site is breast cancer. Almost 30% of our cancer load is breast cancer. Then, this slide shows worldwide breast cancer is the leading cancer. You see the incidence and the top bar showing the worldwide breast cancer incidence rates. Nearly 1.9 million cancer cases occur. This is an estimated figure, and nearly then lower bar showing the mortality rate. The lowest figure showing the M bar I ratio. That indicates mortality to incidence ratio. Worldwide data which shows 31. That indicates that 31% of breast cancer patients die in the same year itself if you see the worldwide data. The right side figure shows the Indian data. So there, in fact, the MI ratio 50 means 50% of women die in the same year itself. Then, this shows the trends in incidence of female breast cancer in selected countries. This figure shows the trends in incidence rates showing upward, except in a few countries, the declining trend. Almost in all countries, incidence rates are increasing. Whereas mortality rates, if you see the mortality rates, except in India and in a few other countries, the mortality rates are declining, which shows that the detection of this site is the early detection and thereby reduced mortality rate. This mortality reduction indicates that this disease has been detected in early stage. You see, this is trends in from the available data in National Cancer Registry Program. In almost all the cancer registries, breast cancer incidence rates increasing in India. So this cancer registry program, National Cancer Registry Program, it is under the ICMR. ICMR publishes regularly this kind of reports, cancer registry reports. And now, in fact, these reports data, earlier only report, now this data, they have been made available in the their website also. These reports earlier only hard copies, now soft copies of the data is also available. So similar reports, RCC also, we also publish annual report of this kind of cancer registry program. In fact, the hospital-based cancer registry program has been started since 1982. In 2012, we have completed 30 years, and this year we are going to complete 40 years, and we are in the preparation of a 40-year consolidated report of the hospital-based cancer registry. And for calculating the incidence and mortality rates, we have population-based cancer registry. That is that has been started since 2006. This figure shows the density map of breast cancer in Trivandrum. In fact, this work is this is Dr. Preeti Sara George, next speaker. This is her work. In fact, the cancer registry figures which I have shown earlier, we get only the summary figures. Which area the cancer is? In fact, that you can see that the first figure, some earlier figure, I showed the cancer incidence rates of breast cancer. In Trivandrum, it was 50 per 100,000 women. When we see the specific areas, this figure shows more than 100 per 100,000. So likewise, we can point out the area. In fact, Preeti's geographic information system, by finding out the longitude and latitude, then using this Google Earth, and this project work, this is only a pilot study, and only the Trivandrum Taluk, and she has been doing this program in all the other areas in South Kerala. And once this program has been completed, we will be able to find out the area where the highest cancer incidence, and thereby, in fact, this kind of information will be very useful for epidemiologic risk factor identification. So this is all, again, I have in Kerala also, this is Trivandrum data. This disease has been increasing, and this yellow bar is a projected figure. This publication is in 2016. And we projected these figures, and now we compared these projected figures and realistic figure. In fact, it is almost you have seen that 2000 17 data, it was nearly 60, and the bar also, this realistic data also similar to this prediction. Fortunately, this increase is among the disease incidence rates by age group. Sir has already earlier mentioned that age is a confounding factor. It definitely affects the cancer incidence. So we have taken the age-specific incidence rates, and you can see that the trend is higher, the highest among the older age population, older stage population. And fortunately, the curve is plateau in under 40 years. So, as I mentioned earlier, as Jagat has also pointed out, that cancer, it is generally expressed in 4 different stages. Stage 1 is called localized, and then the disease spreads to the nearby organ, that is called regional metastasis. If disease spread to the distant organ, it is called distant metastasis. So for breast cancer, if the disease is detected in the earlier stage, you can see that the localized figure, the right side, 5-year survival, it is almost 99%. It is this 5-year relative survival means survival due to breast cancer. It is almost 100% if disease is detected in the early stage. And in 4th stage, it is less than 25%. This is our Trivandrum data, almost by stage distribution by age. Breast cancer stage distribution by age. Okay. Yeah. Survival, breast cancer survival with respect to stage. Here also we can see that our RCC Trivandrum data, if in early stage almost 99%, this is 5-year survival almost, and if the disease is detected in the later stage, it is less than 20% 5-year survival for stage 4 cancer patients. Okay, coming to the breast cancer risk factors, in fact, this is mainly a hormonal and lifestyle related risk factor. Almost 60 to 70% of this cause factor, we cannot say cause factor, associated factors can be identified, and less than 20% it is genetic factors. These are the identified factors: close blood relatives, certain gene mutation, close blood relatives have had a high chance for developing this disease. A woman with breast cancer has 3 to 4 times greater chance of developing a new breast cancer. Then radiation exposure, in fact, if any chest radiation treatment, their chance for developing breast cancer is high. And genetic factors like BRCA1, BRCA2 mutated gene, if such mutated gene, then their chance is also very high. Then these hormonal factors, menstrual history, women having her menstrual periods early and who went through menopause late. So early menarche and later menopause. Then women having no children or have their later age at the first childbirth. All these are all biological related. You can see estrogen, their longer duration of estrogen activity. So it is since it being a hormonal related, these are all hormone related factors. Early menarche, late age at menopause. So their duration of estrogen activity will be high, and less number of children or nulliparous, then later age at the first childbirth. These are also estrogen activity will be high. Indirectly, these factors are related to the development of breast cancer. Then other hormonal lifestyle factors, obesity. In fact, obesity is studies have shown body mass index, then weight in kilogram to height in meter square. That is called body mass index. So Western studies, in fact, body mass index have shown increased high body mass index, or more than 30 body mass index. We call it as obesity. So it increases the risk, especially postmenopausal women. Then exercise, lack of exercise also, it increases the breast cancer risk. Then lower breastfeeding, the alcohol consumption, then long-term use of estrogen receptor treatment, hormone replacement treatment, and then slightly women using birth control pills. These are the established risk factors for breast cancer. Almost all these studies have been carried out in Western countries. In India, in fact, almost we can say that limited studies, and that too also very small, based on the basis of the very small sample size. This kind of risk factor identification studies have not been carried out. So, based on considering this emerging problem, Government of India, ICMR, has initiated a task force study to compare the genetic, clinical and epidemiological risk factors for breast cancer in India. I am also involved, myself and Preeti, we are involved in this study. And this study objectives, first objective is to identify the lifestyle, clinical, hormonal and other risk factors. In fact, we went through the literature, and you have seen that these are the identified risk factors. On the basis of this identified risk factors, we have made a questionnaire to collect the various details. Initially piloted that questionnaire, then we validated the questionnaire to check the consistency in the results, and then the second objective is to identify the mutational, that is exome and transcriptome analysis with the validation. Though we are in our department, this first objective we have been taking care of this to meet the first objective. In fact, these are the just questions which we used. I will skip this part. Various risk factors which I mentioned previously, epidemiology questions, and this physical activity, various physical activity. And we made a manual also to see the okay, these are their body size, to see the body size, and this also I will skip. Okay, coming to the results, in fact, we can say four different categories. You can see that the second column, ER plus PR plus, it indicates estrogen receptor positive, progesterone receptor, ER/PR, that is positive, and HER2 negative, then ER negative, receptor negative, and HER2 positive. Then again ER/PR, that is receptor negative, HER2 negative, and receptor positive, HER2 positive. So in fact, breast cancer, since it being a hormonal related cancer, these are the four different hormonal related categories. You can see that this is almost same. Average age at diagnosis is almost same, and almost similar standard deviation for this. The sample size is 1071. In fact, now the study has been continuing. We are in the 5th year. So it is almost 2000 breast cancer case data. And in fact, this is a 1:2 masked case control study. Because of this COVID pandemic, these controls are, in fact, it is collected from the field. For any case control study, control selection is very crucial. In fact, the study design is a masked case control study, that is a 1:1, 1:2 matching. we are unable to get this matched controls for the study. And just I will, on the basis of this 1000 odd breast cancer cases, these are the summary of preliminary analysis. In fact, this results the 4 different categories. These are the risk factors, significant factors we identified. This is no age adjustment or no other confounding factors have been adjusted. This is only single variables. We have seen no confounding effect can be identified on this basis of this analysis. So HR positive, that is ER/PR positive, HER2 negative group, several risk factors, age at menopause, family history of breast cancer, family history of other cancers. Other cancers means so other than breast cancer, like ovarian cancer, colorectal cancers. This it is mainly ovarian. In fact, we call breast ovarian syndrome. So more chances for developing ovarian cancer also. The etiology is almost similar for breast cancer and ovarian carcinomas. Then fried food, moderate activities we call the physical activity, and WHR is waist to hip ratio. In fact, in this finding waist to hip ratio, in fact, we can see that our women, this body mass index, in more than body mass index, our waist to hip ratio is higher. That is waist to hip ratio is an indirect measurement of central obesity. So central obesity is higher in our Indian population. So we have noticed the difference in waist to hip ratio, and we can see that in 4 different categories, this waist to hip ratio have shown significant difference. The odds ratio was significant for all these 4 various in all the 4 different categories. Now coming to the propensity score analysis, case control studies, we know that it is a common method for analyzing the outcome with the potential risk factors. In fact, the association with cancer, it is a multifactorial etiology. That is why, in fact, cancer epidemiology is an emerging field, and a lot of statistical applications. In fact, it is involved in cancer epidemiology. See these multiple risk factors, the chance for development disease. In fact, risk factors of interest can be, we can estimate the various risk factors, and after adjusting the various confounding factors. So confounding, in fact, it occurs when the risk estimates of a particular exposure, it is mixed up with the real effect of another exposure on the same outcome. So confounding is largely we see in cancer epidemiology. So to predict the outcome, logistic regression method is commonly used. In fact, binary outcome is common in disease, yes or no. So and survival, yes or no, vital status, yes or no. So this kind of binary logistic regression model, or if follow-up is available, Cox regression model, such predictive models are commonly used in cancer epidemiology to find out the risk for development or risk for death, finding out. So conventional method, in fact, used to adjust the baseline differences between disease group and observational database. It is covariate after adjusting several factors of interest. So coming to the propensity score methods, in fact, the association between risk factors of interest and disease that may be confounded by other factors. So confounding occurs when the risk estimates of a particular exposure that is mixed up with the real effect of another exposure. So propensity score methods are another emerging statistical technique. The probability of risk can be estimated. to compare the impact of exposures on developing disease, it has become a standard practice to use propensity score methods to correct the selection bias for potential confounding when examining the relative risk or in terms of odds ratio or hazard ratio of outcome. So this preliminary analysis, we have used only a few variables like physical activity and obesity. As obesity is waist hip ratio, we haven't used BMI, body mass index. We used waist hip ratio to indirect measure for obesity associated with the development of breast cancer in this particular case control study. And then, okay. So this population-based case control study, cases are obtained from the Regional Cancer Center Trivandrum, and the controls are in fact age-matched, age and residence matched controls we selected from the population. And in this data coding, menopausal status, yes or no. Physical activity, in fact, physical activity measurement, there is a manual for how to include various activities, vigorous, moderate or light intensity. Likewise, we have prepared a manual, and this data is collecting by a project nurse. These are the various data coding. BMI is, we considered normal is 18.5 to 24.9, and waist hip ratio, normal is if it is less than 0.085 and abnormal above that. So baseline factors, in fact, all the factors that you hear, sorry for, I don't know whether it is readable, then this shows the, anyway, I will summarize this slide. So,
okay, no problem.
The variables, all the variables are significantly, this is physical activity, various physical activities I have mentioned, and then menopausal status, education and physical activity, all the variables are shown significantly associated with developing breast cancer. And in this study, we have taken only 457 cases and 562 controls. This is only from, these cases are only from Trivandrum district. And logistic regression analysis, you can see that this odds ratio, exponent of regression coefficient, and the corresponding 95% confidence interval, almost all variables are, you can see these results. It shows significance, that is the null value 1 is not included in most of the variables. Okay, then so there are 3 different methods for the risk of developing disease in a case control study may be influenced. Then compare it. Conventional method, that is covariate adjustment, that is before using this propensity score. Then other 3 methods, propensity score method, that is 1:1 matching, then inverse probability of weighting, and then propensity score as a single covariate in a regression model. Then conventional method, it is understood. Then propensity score, then to control confounding by to match the 2 samples. This computer itself matching will be done. It is computer generated matching. Our propensity score is subject's probability of being a part of each respective sample. So for each case, corresponding matched control will be selected by the computer itself, propensity score. Then this is to minimize the selection bias. In fact, in a case control study, I have mentioned it is originally the study designed was 1:2 matching. Matched variables are age and residential status. So we have to find out manually these controls 1:1. So suppose a 550-year-old breast cancer patients, when we obtain from RCC, then we need to get 2 similar controls from, suppose the patient is from Alappuzha district, then we need to get 2 controls from Alappuzha district. So that is the study design. So original study design. Then this propensity score matched analysis. So this is the propensity score formula. Exponent of this left side of regression coefficient divided by 1 plus exponent of this beta 0 plus beta 1 x1, etc. That is, it is same as 1 by 1 plus e raised to minus of, and then it is logic transformation, and then right side will be xi dash beta plus epsilon j. The beta are the vector coefficients of the covariates. Then second method is inverse probability of weighting. That is, it generates a pseudo population with a near perfect covariate balance between the two groups. This weighted propensity score, it is 1 by propensity score for patients in the case group and 1 by 1 minus propensity score for those in the controls. And then the other is propensity score as a single covariate in a regression model, and then all the three methods we have compared using AIT and BIC criteria. I will just show you.
Madam, please conclude in another 5 minutes.
Sure, yeah. So then after propensity score, the sample size, it is 365 cases and 365 controls. This is propensity score 1:1 matching, and this is the important result from this analysis. You can this diagram which shows that 4 different methods. The star, can you see it is propensity score 1:1 matching, that their odds ratio, it was lowest. Is it visible to? That is the important finding, and we can see that the AIC and BIC values are also lowest for propensity score 1:1 matching. I am talking about the figure which I showed on the right side. Then here also for moderate activity, then propensity score 1:1 matching. Here also the lowest incident or odds ratio, and the corresponding AIC BIC values also the lowest. Then here this is also the other factor, and I will skip. This is leisure. All the different variables we have sleeping time, and this is waist hip ratio and physical activity, that the one, and the propensity here waist hip ratio. Here also in this particular analysis, the lowest odds ratio corresponds to the propensity score 1:1 matching, and lowest AIC BIC values also have observed. So to conclude that age of patients, it is these are the various then univariate analysis of covariates that we have used. Age, education, and menopausal status are significantly associated with the breast cancer. Physical activity and WHR, in all the 4 different methods we have observed statistical significance. Lowest AIC BIC values for propensity score 1:1 matched analysis. This, in fact, we have obtained the optimum value, and the overestimation of odds ratios are overestimated in other 3 techniques. So this is one 3 potential covariates. We have used only 3 potential covariates in this analysis. This is just a preliminary analysis. In this method, 1:1 matching was used. Then more matching combination can be used when we have a large data set. These results are based on only one data set. In fact, we are doing this analysis. Results it may vary, but this is to show the importance of this propensity score method. In fact, this method is to make the population more homogeneous. In fact, we don't need to do the matching factors manually. That is the importance of propensity score methods. These are the pros and cons of these 4 different methods. That's all. Thank you. Thank you.
Thank you, madam. Thank you. Over to the audience for questions.
Okay.
Audience, we can have 1 or 2 questions. We have time. Anyways, I have one or two questions, madam.
Yes, sir.
How do you administer the questionnaire to the respondents?
It is a project nurse is there. At the time of registration, in fact, when for breast cancer patients, at the time of registration, this questions is asked, not self-administered.
I see. In person. That's right.
Questionnaire, in fact, it is not just a survey. Questionnaire is prepared on the basis of, we made an exhaustive review of literature and identified all the risk factors. In fact, family history of cancer, we can make a decision tree analysis on the basis.
It's not based on sharing of questionnaire with somebody. It's not like that. Okay, that's what I wanted to know.
Not self-administered questionnaire. It is an interview-based questionnaire. Information is collected by a project nurse. They have provided staff for collecting information.
Okay, that's good. Now, another point is, now, health sector in Kerala is one of the top performing sector if you look at all other.
Exactly. Correct. Agree.
Now, still, breast cancer patients number is increasing. Why is it so?
Yeah, breast cancer. So as I mentioned, in fact, you are asking in Kerala?
Yeah, in Kerala only. Kerala.
Yeah. So far, in fact, breast cancer, it is hormone-related cancer. And then it is lifestyle. Partly we can explain lifestyle related. So
lifestyle, okay.
Lifestyle factors. This moving to the sedentary activities. So more mechanized lifestyle.
Right.
We can compare the earlier women and now more housewives. Even housewives also. We are all dependent on machines.
Right. Modernization, right? Modernization effect is also very high.
Mechanization and more urbanization. That could be one reason. Then secondly, this more fatty food. In fact, non-vegetarian food. So we cannot say directly for more this non-veg consumption. That is also one factor. Then another factor is this. I have mentioned this reproductive history. We can see that age at first marriage. This is indirectly first childbirth is related to the age at marriage now. So there is a shifting of age at first childbirth. So it is that is one reason. Then parity is also earlier. In fact, women. We are having one among four, now only one or two. So that also this estrogen activity number that I have mentioned this higher number, increased estrogen activity. These factors are indirectly related to the increased estrogen activity. These could be the reason. These changes in the society. These could be the reason for increased incidence. But one thing we can do, this kind of primary prevention programs, once we can find out, this information can be disseminated to the public, in fact. So more early stage detection, even now also, stage 4 breast cancer, and that too also among working class people. So people, when they see some abnormality in their breast, it should be immediately reported. That people still hide their information, this kind of abnormality, and when they by the time they seek medical advice, the stage will be 3rd or 4th. Now also 4th stage diseases have been diagnosed in our population. That is bad, sad situation. That people should be more alert to diagnose the disease in early stage. I have shown slides that if the disease is detected in early stage, the curability is almost 100%.
Yes, I think, madam, you need a very strong campaign, public campaign across the state.
Yeah. So
like
that
any other program, there is a strong campaign, right?
Now cancer is made as a notifiable disease.
Okay.
Government has assigned RCC Trivandrum to compile the cancer registry statistics in South Kerala, and Government of India provided the funding support. Also, we have Government of India is providing funding support largely for cancer statistics compilation. I am, in fact, I'm involved. I am the principal investigator of this registry program. So, doing it.
That's good. Now, even I received a very interesting comment from a message from Shiva Subramaniam's year, sir. He also admit that is very, I mean, what I said is correct. So I think the sectors, even if you see the sustainable development goals, I've seen a very recent report there again, related to SDG 2, goal number 2, number 3, well-being of people, and any other goals, Kerala is performing on top.
Yeah.
When you compare with all other states. But still, this is really a matter of concern. Health is definitely one of the most important sectors. Still, the cases like breast cancer patients, even in any other patients you look at, maybe because of the effect of modernization or urbanization, as you said. So I think, anyway, I feel that there should be a very strong campaign for educating the people. Anyway, thank you. I think we can stop the discussion here, I think.
Oh, okay. Thank you very much, sir.
Thank you very much, madam. And thank you, Subramaniam Iyer, sir. Thank you. I think we should give a very good applause to Madam Aliam. Now I request the third speaker, Preeti George.
Yes, sir, I am here.
So you are here. Okay, fine.
Yes,
you are
yes,
also
yes,
from
sir.
the same institution?
Yes, I am here, same
So
institution.
you will be continuing the work of Madam Aliam, right?
Yes, sure.
Okay, you are.
Okay.
So why don't you start with a small introduction and then you
Okay,
get into
sure.
the presentation. Thank you.
Okay, I'll do.
Yeah, please. Over to you.
Is it viewable, sir?
Yeah. And nothing is seen. Nothing is seen. You have not
Nothing is
shared, I think. Please start sharing. You can see on the bottom panel there is an arrow mark.
Yes.
Sharing.
Yes.
Yeah. It's coming up.
Is it coming up, sir?
Yeah. It has come. It has come.
Okay, sir.
Thank you.
Sir, I am Preeti Sarah George. I am working in the same division of cancer epidemiology and biostatistics, and our division conducts cancer registry program also. And may I start? Before that, I have to thank Muralidharan sir for giving me this opportunity to present. And also, I want to thank Sadish sir for supporting me for everything, for your patient support, for all of the opportunities you have given me in my career. And also, I wish to thank special appreciation to all the faculties of Kerala University for organizing this meeting.
Okay, madam. Thank you very much. Continue.
Okay. May I introduce, start with your permission?
Please.
Yeah, okay.
Yeah.
Actually, my topic is statistical methods for spatial distribution of cancer incidence. Trivandrum Cancer Registry reported the second highest crude incidence rate, and thus the Cancer Registry receives many requests from the government of India and Kerala about the geographical distribution of cancer and its risk factors, particularly environmental. As Cancer Registry data collection is active, by visiting hospitals and address of the patient is not geocoded, registry unable to provide the geographic distribution of cancer. So we proposed a study to ICMR about the geographical artificial intelligence (GeoAI) modeling for predicting the cancer incidence based on environmental and socio-economic factors. This kind of study, by utilizing cancer registry data and GeoAI modeling for predicting cancer incidence geographically, is first in India. And this study will assess cancer density mapping to pinpoint the area where high incidence has been occurred using the integration of the geographic information system and the advanced tool of machine learning techniques, that is artificial neural network. And this project is sanctioned in 2020 and under ICMR under ad hoc project for 2 years. And we have a collaborative institute, Center for Environmental and Development, Trivandrum. So first we start with some terms and what is the methodology of this study. This is not a complete study. We are just starting. We started this study in March 2021, and this is our plan. These are the statistical tools that we are incorporated in this study. So first we give you some notation. For this, person, place, and time are known as the three key components in every descriptive epidemiology research. Spatial analysis mainly focused on clustering and cluster detection analysis. Several spatial tools such as geographic information system, that is this, remote sensing, that is RS, and the novel spatial statistical analysis such as machine learning algorithm played an important role. Also, this helps to collect, organize, integrate geospatial data from various sources and in different formats. It has enabled conducting a very complex analysis in public health in conjunction with the population and environment. And the remote sensing is another term, that is to obtain some characteristics of an object without making physical contact with it. That is through an aerial sensor. So high resolution satellite image can help to investigate geographic variation of disease at a small area scale. And another term is the global positioning system. This technology has made collecting massive amounts of spatial and attribute data in surveillance of disease faster, easier, and with an affordable cost. Statistical tools that are used to mainly map, explain, and predict the spatial distribution of health problems. That is, mapping means visualization of the disease count or rate. And the second one is the clustering and the cluster detection analysis, that is the exploratory spatial data analysis. Third one is the correlation analysis. And fourth one is the modeling, that is the explain to predict the disease rates, count, etc. The very first step in spatial statistics is linking this disease counts or rate data to their respective location and visualize them as maps. The mapping helps to reveal some useful information and also conceal the actual affected areas. Therefore, some statistical analysis are required to evaluate the offset pattern of disease occurring statistically. So spatial clustering and cluster detection technique can consider location and attributes by identifying these hotspot and cold spots of the disease. So using a proper model, the possible relationship between the disease frequency, rate, and several explanatory variables, such as environmental and socioeconomic factors, can be explained. A properly developed model can also be used to predict, that is spatially, temporally, the disease distribution. So this is the disease map. Disease mapping means the disease map can disclose the spatial patterns in the data that are not readily detectable in a tabular format. Actually, we cancer registry provide only the rates, that is the only value of incidence rate, count, what is the distribution of in this age group, what is the distribution of the cancer, breast cancer, lung cancer, and what is the rate of that. Only that much information. So some application of disease mapping are basic description of the spatial disease distribution, hypothesis generation of possible relationship between factors and health outcome, and response areas representation useful for the budget and resource allocation. But limitation, some shaded mapping for areas with a small population can lead to high variation of the estimated risk compared to the large population. Or for this Bayesian model, which can be useful for this alternative. It provides a more robust solution as it can avoid unstable estimates of rates and risk. These models are increasingly applied in the small area estimation and disease mapping by spatial epidemiologists. An exciting feature of Bayesian method is that they can help to remove random components resulting from the correlated and unmeasured factors from the maps. Another technique is global clustering techniques. That is spatial dependence or spatial autocorrelation. Spatial autocorrelation SA. Actually, it is provided by Tobler in 1979 to evaluate the pattern. So spatial autocorrelation can be a positive. That is, similar attributes are close to each other. Negative, that is, different variables are close to each other, or none. That is random distribution. To evaluate the presence of this spatial autocorrelation means that the overall pattern, that is known as the global clustering techniques. So here also the null hypothesis, the random distribution, I tested against the clustered alternate hypothesis clustered distribution. Another technique is the global Moran statistics. It is most widely used measure of the spatial autocorrelation measure. It is also a spatial autocorrelation measure in continuous variable, which relies on both the variable's location and the similar time is the attribute role. So the index range from -1 to 1, and this value is close to -1 indicate the dispersion, and +1 it shows the clustering, and the value 0 to 1 indicates the random pattern. And this is the equation. So here the number n is the number of spatial units, and x is the variable of interest. Suppose our interest is incidence rate, and Wij, the weight shading of border or point of the nearest neighbors. So that is the buffer in environmental. So another techniques are local clustering detection techniques. And global clustering technique has some limitation. That is, it uses only a single spatial autocorrelation value, which is assigned to the entire pattern. And it is also unable to identify the location of clusters. So another measure is the local measures of clustering. That is the cluster detection technique, and it is an autocorrelation is calculated for each aerial unit, and its significance is evaluated with the statistical test. Identify hotspot, cold spot, or outlier in the pattern, etc. Another method is the kernel density estimation, that is KDE. It is also to visualize the location of clusters. A weighting kernel function is fitted over each point or line. The weight decreases as we move away from the point line feature and not providing statistical evaluation of the result. Another method, geographical analysis machine, that is DA, and the automated cluster detection technique of Openshaw et al. In 1987 for point data. So Openshaw et al. In 1987, they identified the spatial clusters of childhood leukemia incidence. So it is a two-dimensional grid is superimposed over the study area. A series of different circles with various sizes generated and scan over the whole study area. The observed intensity of events within each circle is compared with a threshold based on a Monte Carlo simulation. If the observed intensity exceeds this threshold, it draws a circle on the map. The final output of JAM is the map of significant circle. No conclusion can be drawn about the significant level of clusters. So another popular method is the JETS or that is Wsta statistics. It is most popular hotspot detection method, and Sun et al. 2017 provide these hotspots of the dengue fever epidemic in Sri Lanka also. Actually, it is a polygon-based method, and the points even can be aggregated by superimposing of a grid. So the GI star standardized to Z score, normal distribution, so that the large Z score is correspond to a significant hotspot, and Z score greater than 1.96 standard deviation, a large negative value of Z score associated with a cold spot. That is Z score less than minus 1.96 sigma, and value close to 0 shows the location that is neither hotspot or cold spot. Another method is the spatial scan statistic, called of 1997, provided for point and polygon units in the StatScan software. Actually, this is software, and this assesses find the significant clusters of the individual health events, case control studies using the Bernardin model. And circular windows with varying radius size or ellipsoid windows in different shapes and directions are drawn around each point or centroid of polygon data. So size of the window is changed from 0 to the specified cluster size. For each window, a maximum likelihood test is applied to compare the risk within the window within the outside. And here also Monte Carlo simulation is used to test for the significance level of cluster, and the cluster with the maximum likelihood is considered as the primary clusters, and the rest of the clusters are considered as the secondary clusters. And it can take also confounding into the account by adjusting for the variables also incorporated here. Another method is the space-time clustering techniques. Space-time analysis of disease clusters are used to find the direction and the periodic patterns helpful for predictions. And NOS in 1964 examining the space-time interactions expected by the chance. Also, although this correlation analysis can indicate association between the factors and disease morbidity or mortality, the association do not indicate causality. So, modeling disease occurrence helps to describe the incidence rate and identify the underlying factors. It can also be used for predictions, classification, that is the presence or absence of factors, or regression, that is the predicting disease rate or count. This prediction can be spatial or spatio-temporal, that is future or near for status of the disease, or for other areas, that is the projection. And data modeling techniques, that is the data-driven model. It is based on the statistical analysis to quantify the relationship between the disease morbidity and the underlying factors also. Here we develop the modeling. There is a classification and regression tree. That is the CART. It is a decision tree based method that can be applied for solving both classification and regression problems in spatial epidemiology. It is more flexible and modeling variety of response variables such as categories, survival, and continuous data all can be incorporated together, and it is easily interpretable. One limitation is this, that it is attributable to the low predictive ability and high variation in data sets. So, in ecology, we solve this problem by bagging, boosting, and random forests. These algorithms generate numerous decision trees by random selection of variable and random selection of samples with the replacement. That is bootstrap sampling. So the bagging also, in each repetition of sampling, 1/3 of the data is used for testing the model performance, and boosting is like also a bagging. In bagging, samples have equal weights. Random forest is also a type of bagging. And another models are support vector machine, that is SPM. That is also another data-driven model that is used for binary classification problem. In SPM, a data set of high-dimensional points viewed as vectors, where each point belongs to one of the two classes correspond to the presence or absence of the point. So, if we assume these points to be linearly separable and can be separated by a linear boundary, The goal of SPM is to find the d-dimensional hyperplane maximus margin. So the distance between the closest point or support vectors. Another method is the artificial neural network. Are among the most popular machine learning technique is used in recent years in environmental studies. This ANN knowledge about the data for driving the patterns. The ANNs are simplified mathematical models that can map the relationship between the input and output layers by receiving several examples, that is training data. A properly trained network can further be used to predict outcomes from new data, that is test data. So our study objective, the proposed study objective is to generate the cancer density maps in South Kerala by gender using geographic information system, and also to assess the socio-demographic, environmental and epidemiologic factors associated with the cancer incidence in South Kerala. Also to predict the cancer incidence in South Kerala based on this environmental socio-demographic factors using this explain the GeoAI techniques. Our study design is spatial ecological and ecological study, and we are a project office is Cancer Epidemiology Division itself, RCC Trivandrum. Duration of the project is 2 years, and our study period is period means the recruiting of the patients. Recruiting of the cancer patient is 2019 to 21, and we got the institutional approval. So this is our area. It covers the 4 districts: Trivandrum, Kollam, Alappuzha, and Pathanamthitta. And around the sample size is 44,000, more than 45, around the 45,000 expected cancer patients will be diagnosed in South Kerala during this period, 2019 to 21. And we have some exclusion criteria, that is cases with a no complete address or difficult to track the patient or patient address are outside the study area, we exclude the patients. Also, we will collect population-based cancer registry, we collect the patient address and socio-demographic factors, age, gender, education, religion, etc., vital status, etc., also obtained from the population-based cancer registry. The Eliama madam is the PI of this project, and she is also the co-PI of this project. So population-based cancer registry, we got the data from through this project, and the epidemiologic risk factors are tobacco smoking, chewing, consumption, or obesity, family history of cancer, and other comorbid conditions. And for this, we first Google Earth software is used for locating latitude and longitude, etc., from the Google Earth software for geocoding of the cancer cases. And the Kerala State Pollution Control Board provides us the air quality of data, and the water groundwater department provide the water quality of the way, whether there is any increase in the risk in any area, is there any significant risk is there, we will collect the water from there and we will test it in the groundwater department. Also, administrative boundaries and remote sensing, etc., are obtained from the Center for Environmental and Development, that is CED in Trivandrum, Thoduvanko. And population, we use this census 2011 and 2021. Based on this, we estimated 2019-21 population, and we use QGIS software, ISPS, and Python program is also included. So GeoAI techniques will be used to assess the association of the socio-demographic, epidemiologic, and environmental factors with the cancer risk by generating density maps in South Kerala. The obtained risk map will be then classified into 5 classes, risk categories ranging from very low to very high, risk areas for prioritizing the cancer control intervention. And this is our flow chart of the work plan. And we will do statistical analysis, exploratory spatial data analysis, ESDA, determine the distribution of the pattern in cancer of each year of data, Moran's index, evaluate the local clustering and spatial autocorrelation, and ANN analysis to identify the environmental, socio-demographic, epidemiologic factors in cancer incidence distribution. Also, we first did the pilot study about that. It is based spatial distribution of cancer in the population living in Trivandrum and Taluk was assessed and identify high-risk areas using cancer density mapping. And we got some, first we provide some land cover classification, coastal, residential and agriculture area. So in that study, we obtained that breast cancer occur more in residential area, and the thyroid cancer occurred more in the coastal area. And we presented this study in the International Association of Cancer Registries, Mumbai and Netherlands. And we expected outcome of this study is to identify the population at high risk for disease potentiality, providing new insight into the novel risk factors by visualizing of cancer density. And these technologies have potential translatability to advance public health promotion by mapping regional differences in cancer burden, environmental exposure, access to healthcare service by suggesting priorities for public health intervention and comprehensive cancer control. And also the scalability of this program is to, if we succeed in this program, modify the algorithms to accommodate more big data like aesthetic modeling to predict different environmental exposure in different geographic area. I think that is also that. Thank you.
Thank you very much, Madam. It was really a good presentation. You have a very good findings based on machine learning algorithms.
Yeah, okay, sir.
Okay, let me ask the audience to, if they have any questions to raise. Questions?
Hello.
Yes.
Very nice presentation. There is one question, sir. How to analyze the spatial? You have using some spatial analysis.
What?
Spatial analysis, okay?
Spatial analysis, yeah. We are using, we will be using. We are not started. We are more on size statistics. That and the spatial correlation will be used for that. Yeah. And for modeling, we are planning to do artificial neural network and artificial neural network modeling. With the actually we did the artificial neural networking in our raw data with the cancer registry data, but not incorporated these environmental factors, social demographic factors, etc. in artificial neural networking. So we are trying to do GeoAI techniques for modeling.
GI, yes, ma'am.
GeoAI,
techniques. Okay, ma'am.
Okay. Let me ask.
Actually, I have also worked on that area, ovarian cancer data. Okay, thank you, ma'am.
May I know where are you? Where from?
Dr. Manoj Kumar, you are from which place?
I am
from which institute?
I am from Central University. Central University, Haryana.
Haryana, okay. Thank you, sir.
Haryana, yes. Central University.
Okay.
I like very much your presentation. Okay, thank you.
Okay, let me ask you a question, madam. You have now identified 2 areas, right? Using machine learning algorithms.
Not okay. Many areas more than we can find the high risk area in many area.
Yeah, that's what the same question, the same point, same context. One, the high risk area you identified as the urban side, right, within the city.
Yeah.
And the other one on coastal side, right?
Yeah.
You are identifying high risk area. Now my question is, what is the probability that a woman identified there having breast cancer?
we can identify probability of developing cancer can be obtained.
No, what is the chance?
Can be obtained based.
You identified the
Can be
area. Now, my question is, how do you, what will be the probability of a person's...
First, we will collect the urban area, and we will boundary it as a urban area. And there are some pocket areas in the urban area where the breast cancer is low breast cancer.
Okay.
The same thing is here also. Breast cancer is high probability.
Okay.
Okay.
Dr. K.V. Baiju is faculty of Department of Statistics, Government Women's College, Taika, Trivandrum. And he is a very active researcher and also a teacher. And he, with the help of him, several gets, in fact, raised to the different levels, both in research as well as in other professional levels. And I'm proud to have a friend like Dr. K.V. Baiju, and to chair and also to speak in a session in which he is chairing. This is my privilege. So I wish to invite Dr. Baiju to chair this session, and I'm not extending too much about him. All details are there. You can just Google and we'll get more details. It's a versatile fellow, personality. I invite Dr. Baiju to chair this session, please. Please note that in this session, the speakers have not much time. There is a limited time only. You have to allot that way. The minimum time will be allotted to me, and others to have, we can learn more. That's okay. Okay, thank you.
So, Dr. Satish wants the minimum time because he has been speaking for the last 4 days. That is why.
Yeah.
Okay.
Okay. Thank you, Satish sir, for your invitation. Good evening, all. Welcome to the final showdown session of the 4-day-long full-fledged webinar sessions as a part of the National Statistics Day celebrations. And I would like to thank my sincere thanks to Professor Satish Kumar sir for giving me this privilege to chair the final session, that is TS36, an invited session. So as per the schedule, there are 4 speakers in this final session. And without wasting much time, because as Balakrishna sir said, you have been here for the last 4 days, spending at least 10 hours per day. So everybody is tired, but we have to go to this final session. So in the speakers list, the first one is Akanksha S. Kashigar from University of Pune, and the topic of her lecture is quite interesting. It is entitled, "Writer is known by the words he writes." So before inviting Professor, let me give a brief intro about the professor. She has a brilliant academic career as well as professional experience in the field of statistics. She did her MSc in statistics at the Department of Statistics, University of Pune, with first rank, and also qualified had to crack CSIR JRF examination with an All India rank of 16. She has been awarded with the PhD by the same university, that is University of Pune. Her research works mainly focus on random process, including time series analysis, and also many areas of applied statistics. She has been publishing research articles in reputed journals And with a short span of time, she has published more than 15 publications in national as well as international journals. And you can see, even in this pandemic's time, she got publications in 2020 and 2021 in reputed journals, and clearly it reveals her interest in research. And also she bagged the Young Statistician Award and also many awards in her kitty. She has more than 10 years of teaching experience in Department of Statistics, University of Pune. And of course, another interesting thing that I have to give you that she possesses a JLPT special diploma in Japanese language. JLPT means Japanese Language Proficiency Test. And you know that Japanese language is one of the very difficult languages to learn. And I don't know how many Indian statisticians do possess this special degree. And in that sense, it seems to be a rare event. You can also watch some interesting YouTube videos by the professor, like Statistics in COVID Land, etc. So in short, she seems to be a right choice in the final session by Professor Sadish sir. With your permission and on behalf of Wsta 2021, I invite Professor to this online platform. And Professor Akanksha, now the online stage is yours. Please carry on. Thank you.
Hello, everyone. Am I audible?
Yes, yes.
Yeah, okay. First of all, I would like to thank the organizers for giving me this opportunity to interact with all of you. And I would also like to thank Professor Baiju for this very nice introduction. Thanks for all the nice words that you said about me. Let me now share my screen and start the talk.
So, Akaksha, you are speaking in German or in English? Sorry, in Japanese or English?
I think it's democracy, so majority is for English, so I'll go for English.
Okay. So don't put us in trouble.
No. But you are going to have to revise Marathi now from my talk.
No. Why? Okay, you are talking. Okay, good.
Yeah, I'm talking about languages, so Marathi is there, so you can revise.
I can recall, yeah.
Yeah. Okay, so can you see my screen?
Oh, yeah, yes.
Yeah. So title of my talk is Writer is Known by the Words He or She Writes. So why did I choose this topic? So this is one famous Marathi science fiction writer, Dr. Bal Phonke. So he has this book on science fiction called Karna Pishacha. So basically what he does is his protagonist in this book, Dr. Kaushik, is supposed to be a detective like Sherlock Holmes. The only difference is he uses techniques from science. This Dr. Kaushik uses techniques from science to solve crimes. And interestingly, one of the story is about use of statistics in linguistics. So it's very, rare to, all of us know that it's very rare to find statistics in popular culture and especially in local language. But in Marathi, we do have this interesting thing. So there is a story where what happens is, in this story, there is one famous academician who is working on some Oriental ancient history, etc. And then, there is some rumor that he has written something bad about our country, and then people start, complaining against him, and actually they protest inside his institute, they vandalize the institute, etc. And everyone who knows this academician, they are surprised because they feel that this person is a very rational, reasonable person. He won't write any such provocative things. And basically, he won't write anything without giving proper evidence. So they feel that this must be, someone's way to unnecessarily implicate this person in this scandal. So this becomes a police case. And then this protagonist of our book, Dr. Kaushik, uses stylometry to compare the previous articles written by this academician to this latest one, which is causing problems. And he proves that this could not have been written by this person because the style is completely different. So then I started thinking why to restrict things to popular culture, why not actually explore what has been done in really literature? And unfortunately, for local languages, quite less research has been done, even on the data analysis front. Most of the work in linguistics is focused on, obviously, English linguistics. So where are the applications? So why to study writing style of a person? So first of all, the major thing is history of literature. So there are many works in literature which have unknown authors, or the authorship is debated. So if we want to confirm, then in such cases, we need to worry about that. In fact, even in Indian languages, for example, in Sanskrit, on Atharva Veda as well as on Rig Veda, there are commentaries by a scholar named Sayanacharya. And there are debates whether both these Sayanacharya, who has written both the commentaries, is it the same person, or are there two Sayanacharyas, because the name could be repeated? So one has written commentary on Atharva Veda and another one has written commentary on Rig Veda. So there also we did some work. I'm not going to present that today, but some such open problems are there where we need to apply statistical techniques to assess writing style of an author. Then criminal investigation, of course. So if there are any harassment notes or that are being sent, then we need to identify the author. In fact, nowadays with cybercrime rising, emails also need to be analyzed for locating the author of the email, etc. And academicians are very well aware of plagiarism detection. So that is another thing. So plagiarism, we all know, is copy pasting someone else's work without giving due credit. So if I have an article, I can actually try to search for paragraphs which are possibly written by someone else. So hence, these are the three main types of analysis that can be performed under this branch. So first is authorship identification. So you have some piece of text where author is unknown, and then you compare, you might have a list of probable authors. So you compare their other works, known works, with this, and you try to see whose work is most similar to the given text. Then authorship characterization. So for comparing such work, you need to have some profile of that author. So you need to characterize the writing style of that author. So that can be done here. And then, as I said, similarity detection. So similarity detection would tell me that if I have, say, an article of 1000 words, is it written by a single author, or are there parts of it which could possibly be written by someone else, which would be helpful in plagiarism detection. So today I'll be presenting some analysis on Marathi newspaper writers, mainly editorial articles. And this is actually, this was actually MSc project done by three of my students, Kabir, Prajakta and Divyanshu. So I would like to thank them, and we'll start with the actual talk. So any such linguistic study has to first start with corpus collection. What is a corpus? Corpus is a set of large amounts of text in a language. So we know, as a statistician, we always need data. So here this corpus would become our data set. So what we did is we have collected 64 articles from 5 different authors. So roughly 10 to 15 articles from each person. These are the authors: Anand Bagaitkar, Jagdish Patwardhan, Kumar Kepkar, Girish Kuber and Subhash Naik. If there are any Marathi people in the audience, they would be familiar with these names. And many of these are basically editorials from popular newspapers such as Sakal and Lok Satta. And some other articles are from a website called Marathi Srushti. We have some limitations on corpus because we need that corpus to be, in an editable Unicode text format so that we can input it and extract features from it. Otherwise, manually extracting features would be a very, very, very mammoth task. So that's why we couldn't have a very large corpus. We had to have a Unicode text which is editable. Now, of course, the next task would be variable selection, or in today's language, feature selection and feature extraction. So given a text, we can have hundreds of things that can be measured about a text. So we need to identify which are important for us, and hence feature selection and extraction becomes very much important. So we start with some pretty basic pre-processing first. For example, we remove titles, dates, author names, and extra paragraph spaces because we are going to extract features via a computer program. So we need to have all the articles in uniform format. Then we also remove the decimal points. Why remove the decimal points? Because we may want to compute number of full stops, number of periods. So the decimal points might get confused with the periods. Then in Marathi, there is a concept called as Zodakshar. So what is a Zodakshar? Zodakshar is basically formed by combination of two letters. For example, if I say the word Krishna, you can imagine. So Krishna, Kru is basically K plus Ru from Rushi. Similarly, Shna is Sh plus Hna. So such Jodakshars, so here when we are counting say letters, they'll be counted as say two letters. So if they are formed from combination of two half letters, we would be counting them as two letters. Another important task in any stylometric analysis is actually stemming, which unfortunately we haven't been able to do so far. Now, what is stemming? So stemming is basically reducing the word to its root form. For example, when I say, I have given you something. So the word given, we all understand that given is basically a form of verb give. Similarly, we know that gives, gave, these are also forms of give. So in English, when stylometric analysis is done, words like given, gives, gave, all these would be converted to give. So that when we are talking about vocabulary of an author, we don't give unnecessary credit, because we know that give is single word and all these are forms of that word. They are not new words. So in Marathi also, ideally, the same thing needs to be done. But unfortunately, we don't have involved computer programs which can do that for Marathi. For English, they are there. So right now, we have not done any stemming. We have considered every word as it occurs as a new word. And compound words are treated as one. So if there are, like, for example, for parents, for mother and father, we would say Ai Baba. So Ai Baba would be treated as one word if there is no space, even though they are basically formed from two different words, mother and father. Now, what are the features that we used? So we started with some basic things like number of words in an article, then average word length and standard deviation of word length. So we would like to see whether a person has a tendency to use long words. Then, and is there variety in the word length? Then number of special characters that are used, hashtag, @ etc. Number of section headings. So because some people may have a habit of dividing an article into sections and giving titles, others may not be that habitual to it. Then punctuation frequency. So how many punctuation marks does a person use in an article? And then punctuation entropy. So punctuation entropy would basically measure diversity in use of punctuation. So there may be one person who uses say 20 commas and 5 say semicolons. So then the person has used 25 punctuations. Other person may have used 10 commas, 10 periods, and then 5 semicolons, and then 5 inverted commas. So he's using more variety. So punctuation entropy is measured. And then total punctuation. So here in punctuation frequency, we count for every punctuation mark. And here we give the total of it. Then number of sentences, average sentence length and standard deviation of sentence length, number of paragraphs. Because again, some people might have a habit of forming very short paragraphs. Others might have a habit of forming long paragraphs. So average paragraph length and standard deviation of paragraph length. And then frequency of stop words. So what is a stop word? So basically, stop words are those words which are very, very commonly used in a language and they're not specific to the topic of the text. For example, I'm saying this, is, are, all these things. So whichever topic you are talking about in English, you are going to use these words, are, is, am, all these things. Hence, they will be stop words. So basically common verbs. So in Marathi, we could find a list of stop words in this paper. So we have computed frequency of these stop words for every person because choice of stop words is also affected by the person. For example, someone might be using, in fact, I'm using for example too often. So this is our habit. So that's why choice of stop words is again specific to author. and then total stop words. So how many stop words does the person use from this list in all? Then unique stop words and stop word entropy. So this would again give me diversity of stop words, and then how many unique stop words from that list has the person used. Then type token ratio. So type token ratio is ratio of total number of unique words to total number of words in any given article. Okay, so this is basically taken as an indicator of richness of vocabulary for an author. So an author who has more rich vocabulary would have higher type token ratio. Okay, for example, if you have an article written by a small kid, say school going kid, then type token ratio might be low, whereas an experienced academician might be writing an article with higher type token ratio. Of course, because we have not done stemming, currently our type token ratio would not be a perfect indicator of vocabulary richness. So then we have another feature called Hapex legomenon. So this is basically ratio of number of words that occur exactly once to the total number of words, and Hapex dyslegomenon is the ratio of number of words that occur exactly twice in an article to total number of words. Okay, so now we get some plots for each of these features, and then there are some issues. For example, we saw type token ratio is an indicator of vocabulary richness. So it is giving me ratio of total number of unique words to total number of words. But see, if I keep on writing, so when I'm writing an article, I might use certain number of unique words. But when I'm writing my thesis, it doesn't mean that my number of unique words that, or the number of new words that I'm going to use would be directly proportional to the length. In fact, we saw that as the length of the article goes on increasing, the number of new words that we are using, the ratio goes on decreasing, because there is a limitation as to how many new words you are going to write in a single article. So if the number of words is increasing, then obviously you are going to repeat most of the words sooner or later. Hence, type token ratio, if we take it as it is as a feature, then it would create bias against those authors which write longer articles, because here we have taken every article as one unit. So we have not used articles of uniform length. So some people may have longer articles, and hence if we use type token ratio as a feature, it might have this problem. So then we do a small adjustment. We take moving average type token ratio. So what is a moving average type token ratio? Instead of considering entire article as a single entity, we have some moving overlapping windows. So we have considered a window of 500 words. So we start from word 1 to word 500. In word 1 to word 500, we see how many new words are there, how many unique words are there, and divide it by 500. Then we move our window. So we consider word number 2 to word number 501. And in this window of length 500, we again compute how many new words are there. And we go on moving this window till the last window. And then we can see that in such case, the type token ratio does not vary much. It remains more or less stable. So then we take average of all these windows, and that we take as the type token ratio for that particular author for that particular article. Okay. So the interesting thing is, moving average is relatively a very simple concept, but it turns out to be very useful here. Okay, so now, just like this, some of the other variables are also going to have problems because of the length. Hence, we modify those variables to take care of the length issue. So number of special characters, we make it number of special characters per word, because of course longer articles would have more special characters. Similarly, punctuation frequency, we divide it by total number of words or total number of sentence. Total punctuations also we divide by total number of words. So similarly, we adjust those variables which would be affected by length by dividing them by number of words of an article. Okay. And now here are some exploratory graphs. So why Violin plot and why not box plot or some simple plot? First of all, yes, students nowadays like to do fancier things. This is one reason. And it does give us many interesting things. So this half part of a violin, if I consider, it's a symmetric plot. So if I consider, say, right half or left half, it is like a density plot, because at every point it is giving me relative frequency. So it is like a density plot. So a density plot is of course giving me a lot of information. Now here we can see word count for each author. So we can easily see that Anant Bagaidkar always writes short articles. So all his articles are mostly between 600 to 900 words. Whereas compared to that, Kumar Ketkar has a very long spread. So his articles range from around 500 words to almost 3000 words. In fact, he's the one who tends to write long articles. Others are mostly below 2000. Then violin plot of average word length. So interestingly, number of words for Anant Bagaidkar is very less, but average word length is higher compared to others. So he tends to use bigger words. Okay. And on the other hand, Subhash Naik tends to use quite shorter words. Similarly, this is violin plot for type token ratio. More or less, all of the authors seem to have similar type token ratio. We are not sure whether it is really because they have almost same vocabulary, or is it because we have not done stemming. And I'm actually more inclined towards the latter conclusion. So I feel that had we done stemming, probably we would have gotten a better picture here. So we will try to do it if, let us see. Then, okay, another interesting thing. So this is original TTR and this is moving average TTR. So we can see here that for Kumar Ketkar, in the original TTR, we can see some articles for which he seems to have less vocabulary. But then when we take moving average, that problem gets reduced. See, now all his articles show that, okay, he has good vocabulary, above average vocabulary. So this problem of, and we also saw that Kumar Ketkar actually was the one who writes longer articles. So his type token ratio was getting affected, which is fixed by this moving average type token ratio. Okay, similarly, we have paragraph counts. So again, we can see that Anant Bagaidkar uses very less paragraphs, this number of paragraphs, and of course, then they are longer. So such exploratory analysis is done. And now we go for some further slightly involved techniques. So we have PCA. So using PCA, if we use few major variables and if we draw the score plot, here things don't seem to be too distinguishable. But if we focus on only three authors, Anant Bagaidkar, Girish Kuber and Subhash Naik, then we can see that there are three separate clusters. So PCA does tell us that yes, there is a difference between these three styles of these three authors. And now we go for machine learning models. So we have to worry about accuracy, interpretability, complexity, and redundancy, because higher accuracy many a times is achieved if you go for complex models, but then interpretability suffers. So we first try with random forest. Why? Because it gives us a better way of measuring variable importance. And then using that variable importance, we can shorten our subset of features for further algorithms. So with random forest, we get this type of classification accuracy. So almost 89.06% accuracy. And we can see most of the problems are with Kumar Ketkar's articles. Other people, we could classify their articles quite good, in quite proper way. And now we use the variables which are marked by random forest as important variables. So these are the variables. So total punctuation per word seems to be highly important. Then we go for commas per word and average sentence length. These are another important features. And some stop words come in picture. So ver is basically like and. Nahi is no. Ki is something like, I don't know, English equivalent. He said that, so that would be like ki. Then hota is was, and ani is again another word for and. So these 5 stop words come in picture. Then sentence count, inverted commas per word, average word length. These are also important variables. And now using these variables, we try other techniques. So naive Bayes, which is basically application of Bayes theorem, but assumes independence of features. So independence of features is not really satisfied here, but still it surprisingly gives us decent accuracy, almost same accuracy with only 23 variables. Then support vector machines are supposed to be more effective in handling more number of variables. So they do improve our accuracy a lot, and we get 95.31% accuracy with 59 variables. with linear kernel, and then with radial kernel also we try this. So finally, this is a summary. So here we can see that naive Bayes with 23 variables gives us this much accuracy, and if we go for higher accuracy, then 59 variables and this. So, but as I said, this is not enough. Lot more work is still pending. So right now we find that these are important variables: total number of punctuations, number of commas, etc. But if we do stemming, then probably we can get better results. So here Kumar Ketkar was the most difficult author to identify through all the algorithms. So now what is the meaning of this? One meaning is probably he has such a diverse style of writing that maybe depending on topic his style changes, and he can actually defeat all these machine learning things. But there is another possible aspect of it. He is a very senior person, so probably he is he has a lot of assistants, so maybe they write some parts for it or he edits their parts, etc. So that could possibly give rise to more variation. So that is also one possibility. So we don't know. Now, as I said, we have a very small data set because we had limited corpus and we have not considered this stemming. And then again, the set of best features that we have got may be specific to these editorials. If we go to other types of articles, we might find something more. So these are the limitations. And now I think in the interest of time, I will go towards conclusion. So this is basically a picture of Samudra Manthan. We have a story in our mythology that gods and asuras, they did Samudra Manthan, and from Samudra Manthan, they found out 14 ratnas, 14 gems. So Samudra Manthan was done with the help of this Mandar Parvat, this mountain, and then this snake. So here we are, trying to basically do Samudra Manthan, but with the text. So we are doing text mining with the help of statistics and computer programs to get quantifiable things. So these numbers are like gems to us because these numbers are going to tell us the entire story. So let me thank my students. This is Kabir, this is Prajakta and Divyanshu, because they did all this work. I just gave them some ideas. So let's thank them. And of course, any language related study is always inspired by Professor Rajarshi. I have a lot of discussions with him on language related things. Of course, statistics related things also, but specifically linguistic things. So I would like to thank him. And now let me stop here. Thank you.
Thank you, Dr. Agamsha, for your distinguished representation. And I told you at the beginning that the title seems to be quite interesting. So after the presentation, you can feel that it is a distinguished presentation. Okay, thank you. Now the session is open for discussion.
Can I ask a question, Dr. Baiju?
Questions or doubts or suggestions to the professor?
Can I ask a question, Dr. Baiju?
Oh, sure. Why not?
Yeah. Hi, Akanksha. This is Ravi from Mysore. Did you consider the covariance or correlation between these variables? Because in linguistics, I think they also give more importance to these correlations between, the type of usage and so on. Did you consider?
Sir, except for naive Bayes, all the other methods do take covariance between variables also in picture. So, in fact, PCA was basically that. PCA was modeling covariance matrix, and it does give an interesting picture.
Okay, thank you. Nice work. Thank you.
Thank you.
Thanks.
Hello, Professor. Hello.
Yes, sir.
Can I ask a couple of questions?
Okay, please. Sure, sir.
First, Akanksha, this is a nice piece of work. I enjoyed listening to.
Thank you, sir.
I was going to say that when I was a undergraduate or master's student, there was an article published in the Journal of Royal Statistical Society in which there was a contested article between Shakespeare and another author, and they were sort of an analysis to make the conclusions whether that write-up. So that is what it reminded me of.
Yes,
First, a quick comment. In the naive Bayes, you need independence. You are using independence when that is not true. But what you could have done is done the naive Bayes on the principal components. The principal components are always uncorrelated,
Uncorrelated,
right?
correct. Yeah. Yes.
It's not independent, but uncorrelated.
Correct.
So
correct. We might get better results. Yes. It's a very nice suggestion. I'll try it.
Number one. Number two is more of a fundamental question. This is just to sort of pry your brain on this issue. I look back, I think there is nobody else in the audience who has written for such a long period as I have done. I started my writing in 1979, and it's almost 42 years now. I have to say that when one of my students asks me, saying that, oh, I read this in your Scandinavian paper in 1981, I have to go and look at it because I have forgotten 40 years ago.
Correct.
But when I look at it, I always come out with the impression that my writing was awful. My vocabulary, my vocabulary was pitiful because. So one of the things I was going to ask you is, for these writers, you know when those articles were written, so you have a time frame.
Yes.
Right? So one quality characteristic may be to connect, for example, the introduction of new words, etc., over time. So you may be able to ask whether some author's writing has remained stable over time, whereas some other author's writing has changed dramatically.
Correct.
For example, my own writing now, I use at least some words in my vocabulary. I would have never used it 20 years ago.
Yes, correct.
It may be a good angle for you to look at, and that will tell you how the writing of these authors as an evolutionary process varies.
Yes.
In this case, a quality author will always evolve in writing, whereas an author who doesn't evolve remains stale with the same vocabulary.
Yes. Actually, sir, in this we saw this Kumar Ketkar style was varying. So we are thinking that this time factor could possibly be an angle. So currently the students are actually working on that. So they are recording the exact dates of the articles, but we had not thought in this way. So this also we will now incorporate. Thank you.
Actually, you alluded to briefly in your comment that he is a senior person.
Yeah.
So that means he may have written over a span of 20 years.
Correct.
Yeah.
So,
by the way, just as a pitch, I like this article very much. I have a journal, Communications, in which we have a case studies and data analysis. If you are interested, when you finish this, you may consider submitting it there. I would like
that. Definitely, sir. We will consider. Thank you.
Enjoyed that. Good.
Yeah.
Good presentation.
Thanks a lot.
Akanksha.
Yes.
Is it meaningful to consider the time series of this moving average TTRs? Because that is of this, I think Professor Balakrishna suggested it is the time dependent kind of behavior.
With different articles, means when we are considering like separate articles written across time, then yes, we can consider time series. But currently in a single article, I don't think time factor would come in picture. Currently, we have taken over single article, all windows.
Yeah.
So in single article, I would say time won't be a factor.
No, not with single article, no.
Yeah.
Over the time.
Over the time, yes, we will definitely consider that.
One another side comment.
Hello.
Sunday teacher is trying to say something.
Oh, Akansha.
Sunday teacher, please.
Okay. This is
Satish is speaking, not Sandhya.
Her husband. It's okay. Akansha, my query is.
Okay.
You consider journalistic writing, right?
Yes.
So what about can we do the similar analysis for creative literature?
Yes, definitely. We can do same type of analysis for creative authors also.
So do you think the parameters or the variables that will be considered in that case would be different?
I think if we are considering writers who write mainly for like mature adult audience, then I think it should not change much. They can remain same. But if we are comparing authors who write for children with, say, authors who write for others, then some of the parameters would change. Yeah. Otherwise, I think parameters would remain the same.
In the same category, say novels or short stories.
Yes.
Poems.
I think they would remain the same. Yeah.
Okay. Thank you. Very nice presentation.
Yeah. Thank you, sir.
Balaji sir, can I ask?
I was going to say just one comment. You were looking at the moving averages within 1 to 500 words, 501 to 1,000 words, etc. In your plot. A more common technique that is used in EDA, in exploratory data analysis, is what is called as median polish. And a median polish was introduced by John Tukey in 70 in his classic book, and that is commonly used in order to assess what you were looking at, except it uses the median instead of the mean.
Okay.
Yeah, and there are some advantages to it because
of course,
it is less sensitive to
outliers and all. Yeah, correct. Yeah. Okay, I'll look into that also, sir.
Yeah. Good. Well done.
Thank you, sir.
Anybody else to ask any questions?
Yeah, I would like to thank the audience for being so patient at such a late hour. At least for Indian audience, this is pretty late hour. So thanks a lot.
We have 3 more to go.
Yeah.
So Satish is active from 9 a.m. to 11 p.m.
Yes. Okay. So I think I'll now mute myself.
Satish sir, do you have anything to?
Satish, mic is.
Sorry. Excellent ideas. In fact, congratulations, Akanksha.
Thank you, sir.
Excellent presentation.
Yeah, thank you, sir.
A big clap to you.
Yeah.
Okay, thank you, Ravi sir, Balakrishnan sir, Satish sir, and Satish sir for activity participating in this discussion. We are all fortunate to have listening to your words. And once again, I thank Professor Akanksha on behalf of Professor Satish sir, Wsta, and also the various stakeholders of this seminar. And once again, I thank you, Akanksha, and we expect your future cooperation in our endeavors also. Satish sir, can we move to the next?
Yeah, please.
Yes. Okay. So the next presenter is Dr. Dias George, Associate Professor at Catholic College under MG University, Kerala. So the topic is entitled A Study on Poisson-X Family of Distributions. Let me give some introduction about the activities of Dr. Dias George. Professor Dias George is well known in the statistics circle. So she took MSc in statistics from MG University, MPhil in statistics from Meerut University, and also got PhD from MG University. And the title of her PhD thesis was A Class of Heavy-Tailed Distributions and Their Applications. She has more than 2 decades of teaching experience, and also she has been guiding many students in their PhD works. Her research area mainly focused on distribution theory, and she has undertaken various major and minor projects from UGC also. She published a couple of books and also presented her research works in India and abroad. With your permission, and on behalf of Wsta 2021, I invite Dr. Dias George for the presentation. Thank you.
Good evening, respected participants and respected sirs. First of all, let me thank the organizers of Wsta 2021 for giving me such a good opportunity to be a part of this event. And especially Dr. Satish sir, and for the uplifting words of Dr. Baiju. Actually, this type of seminars helps the younger generations to update their knowledge. Now let me share my screen. So the screen is okay? Is it
Yes,
visible, sir?
yes, very much visible.
So here I am talking on the topic, a study on Poisson's family of distributions. Recently, we can see a deep interest from the side of the researchers in constructing new family of distributions that brings greater flexibility to the existing models. And we know there are different methods for constructing new families of distributions. Introduction of a scale parameter leads to the accelerated lifetime models. And taking powers of the survival function leads to the proportional hazard model. Introduction of a pathway parameter leads to the Q-type distributions. And some of the other well-known families of distributions are beta G family introduced by Eugene et al. In 2002, Kumarasamy family by Cordero and De Castro 2011, and McDonald gamma family by Alexandra et al. 2012, gamma G type 1 family by Socrates and Balakrishna 2009, gamma G type 2 by Ristica and Balakrishna 2012, and gamma G type 3 by Torabi and Monsori 2012, then exponential generalized family by Cordero et al. 2013, TX family by Alsara et al. 2013, logistic G family by Torabi and Montessori 2014.
Can move the slides.
Teacher, please move the slide. Teacher, please move the slide.
Sir, I have not entered to the slide,
Yes.
that is why.
Teacher, next page, next.
No, she is not.
Yes, yes.
I have not entered to the slide, that is why.
Now she's speaking without slide. I mean, not referring to slides now. Yeah.
Yeah.
Okay, teacher can continue.
Okay, then Poisson X family by Tahir et al. 2016, Weibull X family by Ahmed et al. 2018, and this Alpha Sobax G family by Kutchi et al. 2018, extended alpha power transformed family by Ahmed et al. 2018, and exponentiated TX family by Ahmed et al. 2019. Then again in 2020, some more generalized families are introduced like Jamal Weibull X family, Nasser Weibull generalized family, Nasser logistic X family, and so on. So there are a new generalized farm, and these last listed families are new generalized families introduced by TX family. And when considering the Poisson X family, we know that there are great interest of researchers on count data modeling. And this count data modeling has much importance in various fields of study, and especially in insurance modeling and queuing theory. Most of the real data sets, including count data sets, are not EQ dispersed. So ordinary Poisson distribution is not suitable for modeling such count data sets. And only a few compound, truncated, and mixed Poisson distributions are developed in Poisson X family so far. And in order to model such data sets, we have to generate more distributions from Poisson X family, especially because of its applications in queuing theory and insurance modeling. And this Poisson X family is a subclass of TX family of distributions introduced by Asra et al. 2013. And the TX family of distributions are derived using the technique by using any PDF as a generator. Let capital X be a random variable with the PDF small f of x and CDF capital Fx, and T a continuous random variable with the PDF RT defined on interval AB. The CDF of the new family of distribution is defined as g of x equal to integral a to w of f of x RT dt, where w of x satisfies the conditions w of fx belongs to AB and it is differentiable and monotonically non-decreasing, and it tends to be as x tends to minus infinity and tends to be as x tends to infinity. And the corresponding PDF associated with one is given by Tx. The PDF RT already defined is transformed into the new PDF Dx through the function w of fx, which acts as the transformer. That is, the random variable capital X, the transformed, is used to transform another variable t, the transformed. And the resulting family is known as transformed transformer or Tx family of distributions. And if the random variable capital X is discrete, then we get the family of discrete distributions. The Dx will be the family of discrete distributions. A large number of distributions, continuous and discrete, can be generated by applying any two existing univariate distributions based on this method. Asra et al. 2013b gives several choices of w of fx depending upon the support of the random variable t. And some of the examples given are when the support of t is bounded or support is of up to 0, 1, then this will lead to the beta generated family of distribution. And when the support of t is a infinity a greater than or equal to 0, then we will define w of x as given in the second case. And when the support of t is minus infinity infinity, we can define the Tx form. In Tx family, w of x is defined as that given as third case. And different w functions generate different families of Tx distributions by taking w of fx as minus log 1 minus fx. Two continuous distributions of the Tx families that have been studied are gamma Pareto distribution, and it is studied by Asra et al. 2012a, and Weibull Pareto distribution studied by Asra et al. 2013a. When x is discrete, the Tx family is discrete. And the T geometric family generates a discrete analog of the distribution of any continuous random variable T. Again, Asra and Knight 2013 introduced gamma half normal distribution, and exponentiated Tx family is also introduced by Al-Saghal 2013 by including an additional parameter which provides more flexibility to the existing distribution. Then Asra et al. 2014a introduced T-normal family of distributions, and Alja et al. 2014 proposed the use of quantile function to another random variable to define the W function. And Alsay and Koch 2015 proposed Weibull X family of distributions, and recently the logistic X family of distributions and Poisson X family of distributions are introduced by Tahir et al. 2016. Now we are coming to the Poisson X family. Consider a company formed by capital and systems working independently at any given time. Each system consisting of C parallel units, so the system will fail if all units will fail. We assume that the random variable Zi1, etc. Tzic representing the failure times of the parallel components of the ith system, and they are independent and have the same uniform distribution. Let Yi denote the failure time of the ith system. Consider n as a random variable having a truncated Poisson distribution defined by the probability mass function. P of capital N equal to n as lambda raised to n by n factor into e raised to lambda minus 1, n equal to 1, 2, 3, etc. Further, suppose T represents the time to failure of the first out of the n functioning systems. Then T equal to minimum of I1, Y2, etc. Yn. the CDF of T, say RT from the conditional CDF of T is obtained like RT given T n equal to 1 minus of 1 minus T raised to C all raised to capital N. Then the unconditional CDF of T becomes RT equal to 1 minus e raised to minus lambda T raised to C by 1 minus e raised to minus lambda. And the corresponding PDF is given by equation 2. And now consider let RT be a PDF of the random variable capital T belong to AB for minus infinity less than or equal to A less than B less than or equal to B. And capital F of X be the CDF of the random variable X such that the link function W01 will mark to AB satisfies the following conditions. W1 is differentiable and monotonically non-decreasing, and W of 0 tends to A and W of 1 tends to B. Then the CDF of the TX family can be family is defined by Asra et al. As Gx equal to integral A to W of F of X RT dt. Now we will consider on Poisson X family. Here we will take W of X as capital Fx as a support of T is bounded as 0, 1. Then the CDF of the Poisson X family follows from 1 as U of X is I equals integral A to Fx lambda C by 1 minus e raised to minus lambda T raised to C minus 1 e raised to lambda T raised to C dt, all the parameters greater than 0. By setting lambda equal to 1 in 3 and on solving we get capital T of X is I. And the PDF corresponding to equation 4 is given in equation 5. And these are the PDF and distribution function of the Poisson X family, where Fxi is the baseline PDF. Equation 5 will be most tractable when capital Fx and small fx have the simple analytic expressions. Hereafter, the distribution of capital X is Poisson X C psi. Further, we can omit sometimes the dependence on the vector psi of the parameters, the baseline parameters and C, and write capital F of X as Fx psi and G of X, small g of X as G of Xc psi. The survival function, hazard rate function, the cumulative hazard rate function are given by the expressions of Sx, small hx and capital H of X. And the quantitative function of the Poisson X family is given by Q of U. The tail behaviors of the PDF and CDF of capital X in 4 and 5 are also given to the expressions. The Shannon's entropy of the Poisson X family can be expressed as eta x equal to eta g plus log c into 1 minus e raised to minus 1 minus c minus 1, that can be expressed into expectation of log g of x plus expectation of log f raised to cx. G of x and small g of x, capital G of x can be expressed as through the linear representation given in equation number 6, and by differentiating equation 6, you get the PDF G of x, where h I1 of cx is the density exponentiated fx with the power parameter I plus 1 into c. Then here the lemmas. If x have the density function of the form 5, then the random variable capital T equal to f of x has a density of the form RT. Then the converse is also true. That means if T has the density of the form equation 8, then the random variable x equal to if inverse T has Poisson X distribution with the density described earlier. Then based on the Poisson X family, the Poisson power quotient distribution is also introduced, and the 2-parameter power quotient distribution with the capital F of x and small f x are given by expression 9 and 10. Then inserting equations 9 and 10, equations 4 and 5, you get the PDF and CDF of the Poisson power quotient distribution. A random variable having PDF 12 is denoted by x follows Poisson power quotient distribution with the parameters C, alpha and sigma. The survival function, hazard rate function, cumulative hazard rate functions of the Poisson power quotient distribution is given by the expressions Sx, Hx and capital Hx. The following lemma gives a relation between the power quotient distribution and the compound Poisson distribution. That is the random variable if random variable capital T follows the compound Poisson distribution with the shape parameter C, then X follow, then the distribution of X is Poisson power quotient distribution with the parameter C alpha sigma. It's quantile function. Quantile function of the power quotient distribution is given, Shannon entropy is given, and the CDF and PDF are also given. Now come to the Poisson uniform distribution. If this is a newly introduced distribution, if the parent distribution is uniform in the interval AB, then the CDF and PDF of the uniform distribution, it is X, CDF is X minus A by B minus A, and the PDF is 1 by B minus A less than X less than B. Inserting the equations 13 and 14 in equation 4 and 5 of the Poisson X family, we obtain the CDF and PDF of the Poisson uniform distribution as equation number 15 and equation number 16. And the graph of the Poisson uniform distribution is given like this for different values of the parameters A, B, and C. This is the shape of the graph. Then the properties of the Poisson uniform distribution. The survival function of the Poisson uniform distribution is given by equation 17, that it is e raised to minus of x minus a by b minus a all raised to c minus e raised to minus 1 by 1 minus of e raised to minus 1. The hazard function of Poisson uniform distribution is given as hxcab equals, given by equation number 18. The HRF graph of Poisson uniform distribution for different values of the parameters are also given here, and this is the HRF graph. It has J-shaped, reverse J-shaped, and for a fixed value of A with the different B and C values, we obtain the reversed J-shape. This is the graph. And for a fixed value of A and C with a different B, for a fixed value of A and B with the various values of C, we can see a decreasing failure rate, and we can obtain a U-shaped curve for a fixed value of B in the situation. We can also obtain the increasing failure rate. The cumulative hazard function of Poisson uniform distribution is given by equation 19, and the reverse hazard rate function is given by equation 20. The residual lifetime of Poisson uniform distribution is given by equation 21, and the corresponding survival function is given by equation 22. The past lifetime of Poisson uniform is given by equation 23, and the corresponding distribution function is given by equation 24. Using the concept of exponentiated distribution, we can derive some useful expansions for equation 4 and 5. A random variable with an arbitrary baseline CDF dx is said to have an exponential distribution with parameter b greater than 0 if its PDF and CDF are b, hb equal to bg raised to b minus 1 x dx and hb of x equal to g raised to bx respectively. The exponential function equation 4 can be expanded, and then we have obtained expression 25. By differentiating 25, we obtain equation 26, and we can write 26 as g of x c a b equal to sigma equal to as a linear expression where hi plus 1 of cx is the density function of the exponential uniform distribution with the power parameter I plus 1 into c. The equation 20 number reveals that the Poisson uniform density can be expressed as a linear representation of the exponentiated uniform density. Then see the lemma. If y follows uniform AB, then x equal to a plus b minus a into minus log of 1 minus y into 1 minus e raised to minus 1 all raised to 1 by c follows Poisson uniform CAB. Now here we use the inverse probability integral transformation for the simulation of t, so that we have RT equal to 1 minus e raised to minus t raised to c by 1 minus e raised to minus 1. That can be expressed, if it is expressed as y, then t equals minus log 1 minus y into 1 minus e raised to minus 1 all raised to 1 by c. Hence, by substituting the value of t in 28, we get x as expression number 29, which follows Poisson uniform with the parameters c, a, b. Then the quantile function and median is given. If x follows Poisson uniform 3, 1, 4, with p equal to 0.5, then the quantile function and median is obtained. Likewise, then the moments of the Poisson uniform distribution, the kth row moment is given, and the measures of skewness and kurtosis is also given by equation 31 and 32. Skewness measures the degree of long tail, and kurtosis is a measure of degree of tail heaviness. When the distribution is symmetric, then it is left or right skewed. For the TX family, Galton skewness and Morse kurtosis can be computed by using the quantile function. These measures for the Poisson uniform distribution are calculated, and different values for different parameters are given in the table. For the fixed value of C with the different values of A and B, the measure of skewness will be the same, but as C increases the skewness will also increase, and see the table. Then the order statistics, suppose X1 to etc. XZ is a random sample from the Poisson uniform distribution, and let XZ denote the nth order statistics, then the PDF of XR is expressed by equation 33. And using some algebra, it can be expressed as 34. And the largest order statistics Xn is given by Gn of Xc given by 35, and the PDF corresponding to 35 is given by 36. And the CDF, smallest order statistics X1 is given, and its PDF is given by equation number 18. And we use the maximal likelihood method of estimation for estimating the parameter. We are using the NLM method for using R software. We did the estimation, and then we conducted a real study for illustrating the flexibility of the new distribution using a transformed real data set. And these are the two data sets used: bladder cancer patient data set corresponding to the remission times of a random sample of 128 bladder cancer patients given in Lee and Wang 2013. And here and it is compared with the Springsheet uniform and Laplace uniform, and the MLE minus log ISPS and K statistics and p-value for the fitted models are given in the table for data set 1, and this is the graph. Again, the numerical values of the fitted models of the data set is presented in the table, and from the graph and from the table, it is clear that the fitted PDF plot of the Poisson uniform family is the better fit for the data set. And this is the second data set that we are used. It is the exposure trans failure at 90% stress level data is given, and it is again a secondary data obtained from Andrews and Hesberg 1985, Barlow et al. 1984, and the data is given here. And this is the MLA, ICBC, and K statistics and p-value, and this is the graph. Here also, Poisson uniform distribution is found to be a better fit than the logistic uniform and exponentiated uniform distribution. So here we consider the Poisson X family of the conclusion. Here we consider the Poisson X family of distribution as a plus of the TX family. A new member of the Poisson X family called Poisson uniform is introduced, and some of its structural properties are investigated. The maximal likelihood method is used for method of estimation is used for estimating the model parameters, and the flexibility of the new distribution is illustrated by means of two real data sets. And we can see that Poisson uniform distribution provides a better fit than the other compound distributions for these data sets. And this is one of my work of one of my students, and she just started the work, and now she is concentrating on modeling this, using this distribution for modeling in multi-server queuing system and in this in insurance modeling. And I'm thankful for the student also. Thank you. And these are the references.
Thank you, and congratulations, Dr. Dax George, for your awesome presentation regarding the Poisson X family of distributions. And now the session is devoted to the interaction session. attendees can ask any doubts or questions to Dr. Dias yours.
Actually, I am having, sir, actually I am having some throat infection problem. That is why.
Okay. We can realize it.
Yeah.
Can I ask a question?
Yes.
Can you show me the Poisson uniform distribution that you had,
Yes, sir.
where you have the probability or the CDF or density function, etc.?
Yeah, this is a sir.
That's the uniform. There.
Yeah, yeah.
Yes, exactly.
Yes, sir.
You had one before too. But this is nothing new. This is the truncated Weibull distribution.
Yes, sir.
So you have e to the power minus x minus a because you have a lower threshold a. So when I subtract x minus a, this becomes 0.
Yeah.
And then the upper limit is b minus a. You have divided. So it is a truncated Weibull distribution, truncated at 1. That is why you have a denominator 1 minus e to the negative 1.
Yeah.
If I'm not... So there should be a sort of a version of this is the same distribution where you have truncated Weibull, you have truncated it at an upper end.
Okay.
So all the properties about the reliability function, estimation, etc., would follow from the truncated Weibull distribution.
Okay.
The other thing is, can you go to the definition of the TX family of distributions?
Okay, sir.
Where it is, yes. Look at this distribution 1. Actually, it is unfortunate because I see a lot of papers that call this as Alzathre's distribution or whatever. This appeared long time ago in the work of Eric Lehman and Van Zwedt. In fact, that leads to what is called as star ordering. You see capital F of x, you think of a distribution, a random variable which has a distribution function capital F of x, so that capital F of x will be uniform.
Yeah.
Right?
Yeah.
And that is in the interval 0 to 1.
Okay, sir.
Then what is done there, W, in Van Zwert's work, he calls it as H inverse. That's a quantile function.
Yeah.
So the W, you look at all the examples you took. Can you go to the next page? Where you give some choices of W.
Yeah, WFX choices.
Yeah, look at this. No. Next page. Yeah?
Before one.
Where you had the choices of W listed. Yeah.
Okay, sir.
If you look at the choices of W, you see minus log of 1 minus u, it is a quantile of exponentia. U by 1 minus u, it is a quantile of logistic distribution, etc. So this is nothing but, in my view, Van Zwert's distribution. All you have done is, all Alzatre did was to take a quantile function of f of x. That is what Van Zwert did in 1958, and it is actually called star ordering of distributions. Depending on H inverse f, what is its shape, you will call it a star ordering. It is unfortunate it is called after somebody else when this was present in 1958 due to Willem Van Zwert. I recommend you to look at the paper of Van Zwert. You will see exactly the same form.
Okay, sir. Yeah, sir, really good suggestion, sir.
Can I suggest one more thing?
Yeah.
There's a paper by Barlow and Doxman and Barlow in 72. It also uses transforms like that and various properties. That may also help. That's a Berkeley Symposium.
Right. These kinds of transformations you may not be aware, but if you work with something like reliability orderings, etc., it is usually used, this kind of convolution of G inverse F or H inverse F is commonly used to construct alternatives. In fact, that is how Eric Lehman introduces in his theory of ranks. He considers probability integral transformation and then take a quantile function. Instead of just u, uniform, he will consider a monotone function of u, like u to the power alpha, etc. And they form the alternatives and for non-parametric statistics. So what you should look under is actually, like Hira mentioned, is about orderings and applications. There you will find all these are present in the form of transformations of random variables.
Okay, sir.
Yeah.
Okay, sir. A very good suggestion. Thank you, sir.
Good luck.
Yeah, thank you, sir.
Any more doubts or clarifications needed? Please ask. Sadish sir, do you have anything? Okay. Thank you, Balakrishnan sir and Kaul sir, for your valuable suggestions. And I also thank the participants and attendees who have put their comments in the chat box.
Really, thank you, Harish sir, for the valuable suggestion that I had to rethink.
Okay. Thanks once again, Dr. Dias George, for accepting our invitation and presenting such a wonderful topics on before the audience. Okay.
Thank you, sir.
So let us move on to the next speaker, Dr. Bindu Krishnan. Bindu Krishnan, are you there?
Yes, sir. Yes.
Okay. She is currently working as professor and head of Department of Data Science, Jain University, Cochin. And today, Dr. Bindu Krishnan is going to present a paper entitled Parameter Estimation of Verbal Model Using Heuristic Algorithms. Let us give a small introduction about the presenter. She did her MSc as well as MTech from Cochin University of Science and Technology, and also took PhD from Bharatiyar University. Her PhD title is A Study on Certain Heavy-Tailed Distributions and Their Applications in Time Series Modeling. She has more than 2 decades of teaching as well as research experience in the field of statistics. And she mainly focuses on distribution theory and time series modeling. She has published several articles in various national as well as international journals. And also she published a book entitled Probability Distributions, Random Process and Numerical Methods. And she has a sound knowledge in the theories and practices in statistics, and also an expert in statistical software such as ISPS, R, Mathematica, and so on and so forth. And with your permission and on behalf of Wsta 2021, I invite Dr. Bindu Krishnan to present her contributions before the audience. Thank you.
Thank you, sir. Thank you, sir. So first of all, I would like to express my sincere thanks to Dr. Sadish sir for the opportunity given here in delivering this talk. So here, let me share my screen. Is it visible, sir?
Yes, it is visible.
Okay. So the parameter estimation of a
maybe you can
variable
go to the presentation mode.
Okay. Sure. Okay. So parameter estimation of a variable model using heuristic algorithm. So the objectives of my study are a method based on bare-bone particle swarm optimization algorithm is presented here to estimate the most appropriate parameters of variable distribution with censored data, and its performance in different situations is evaluated using Monte Carlo simulation method, which shows that the algorithm based on this PSO, particle swarm optimization, outperforms the other methods especially in terms of bias, root mean square errors, coverage, etc. And 2 data sets are used to demonstrate its performance. So Weibull distribution, of course, we all know it's one of the widely known lifetime distribution that has been extensively used, especially in reliability and survival analysis. And the probability density function and probability distribution functions are given by equations 1 and 2 respectively. Okay. So this is the main focus of my talk. Recent years, this meta-heuristic algorithms or simply heuristic algorithms are used to solve many real-life complex problems arising from different fields such as economics, engineering, then politics, management, engineering, etc., etc. So most of the heuristic algorithms are actually inspired from biological evolution process, then swarm behavior, then physics law, etc., and so on. So these are the popular optimization, advanced optimization algorithms: particle swarm optimization algorithm, genetic algorithm, ant colony algorithm, then artificial immune algorithm, differential evolution, cuckoo search algorithm, then artificial bee algorithm, bee colony algorithm, and so on. Now, evolutionary algorithm, it's an algorithm that's inspired by Darwin's theory of natural evolution to solve optimization problems. And the main components are representation, it's a definition of individuals itself, then evaluation function, that is fitness function, then population, then parent selection mechanism, variables operators, recombination, mutation, recombination and mutation, survivor selection mechanism or replacement. So there are many different variants of evolution algorithms. The common underlying idea behind all these things is we are given a population of individuals, and the environmental pressure causes natural selection, which causes a rise in the fitness of population. And these evolutionary algorithms are population based. This mostly use recombination to mix information of more candidate solutions into a new one. These are stochastic, etc. Okay, so let me move on to my algorithm. Not my algorithm, of course, it's a part. Here in this talk, I'll be focusing only on particle swarm optimization algorithm, which is a well-known meta-heuristic algorithm, or we call it a swarm intelligence. It's developed by Eberhart and Kennedy in 1995, inspired by social behavior of bird flocking and fish schooling. So let me give a brief on this particle swarm. Particle swarm algorithm actually imitates human social behavior. And we observe collective intelligence in many natural systems. Say, for example, ants exhibit an extraordinary level of collective intelligence. So in such systems, actually, intelligence does not reside in individuals, but instead distributed among a group of many individuals. This can be seen in, say, flock of animals,